like I said, by now. Okay. All right. Okay. It's asking me if I want to be recorded.
I'll learn by tomorrow.
It's all right.
Your
Yeah.
answer is it's there in linear response.
It's there in linear response. Yeah, exactly. So you can do, yeah, exactly. So, and by now it's well established in various ways. And okay, so it was very surprising at the time because I mean it's not an exotic model, right? It's just a very simple. It's just an Heisenberg magnet. It's as simple as it gets, and it's not like some exotic, operator spreading or whatever question. It's just like transport, and it's kind of baffling to me, at least, that this was not missed before, right? And so this was missed by previous numerics theory. So if you do Luttinger liquid stuff, you're going to miss that, and also experiments. Right. So there were some spin like neutron scattering experiments before, and they also missed that. Okay.
Missed that one, like the Luttinger liquid is insufficient to capture.
Yeah, that's right. So if you do Luttinger liquid, it will predict ballistic transport. Okay. Yeah. Okay. So this is from a while ago, and so by now we understand that you could also think of this point as some kind of phase transition. So if you deform your Heisenberg chain in an XXZ spin chain, as a function of anisotropy, this kind of a phase transition in transport. So note that there's of course a phase transition at delta equals 1 in the ground state. But here we're talking about a phase transition at high temperature or finite temperature in 1D, which of course should not happen. And so you go from like ballistic to diffusive transport, and there's this transition in the middle. And on top of it, there's also some work claiming that it's related to the celebrated KPZ universality class. So that exponent 3/2 is not like in a vacuum. So we'll hear, I won't talk about KPZ. I think we'll hear more about this tomorrow morning. Yeah.
Like this happens at high temperature.
Yeah.
So
any
temperature.
temperature. It happens at any temperature, actually. So any finite temperature, you'll see this. But at low temperature, there's a crossover. You'll first see Luttinger liquid physics, and then there's a length scale, which is just a thermal length scale. That's 1/T, and you'll see KPZ physics eventually, yeah.
And Luttinger liquid physics consistently gives you infinite everything.
Yeah. Yeah.
So if you put that the band curvature effects in Luttinger, do you still miss it? Or?
Yeah, you will. Yeah. You won't get this.
The linear response is in.
Yeah. Yeah. No, as far as I know, there's no way to fix the Luttinger liquid theory to get that. I'll tell you about how we understand it. Let me also briefly mention that by now there's a bunch of experiments that have been done, and that I've seen this both in solid state systems by neutron scattering. The key difference with what was done before is now it's done in some hydro regimes, so at relatively high temperature. Some of those plots have 300 Kelvin. This is like the structure factor at 0 or low frequency. There's also some cold atom experiments from Emmanuel Bloch and collaborators that saw this pretty much doing that domain wall. There's also a recent experiment from Google, and again, we'll hear about this tomorrow, I assume, so I won't really talk about it. So, but if you're interested, so by now it's well established both numerically, experimentally, as long as you look in the right regime. Okay, so in this talk, what I want to talk about is integrability breaking. So this model, right, is integrable. And the physics like this z equals 3/2, I'm going to claim it has to do with integrability. However, it's not really the end of the story, because what appears to be true, at least empirically, is that this superdiffusion appears to be very robust to integrability breaking. Okay. So what do I mean by this? Well, first of all, you see it in experiments. If you take like, I don't know, just like the solid state experiment, clearly there's a lot more going on in this material at 300 Kelvin than just like this Heisenberg spin chain. Also numerically, I think it was observed pretty early on that integrability it does play a key role, but it's not that obvious numerically. So what you're seeing here is some conductivity as a function of time. So think of it as a time-dependent diffusion constant. And this is for a spin 1/2 Heisenberg magnet, and this is for a spin 1 Heisenberg magnet. This one is integrable, and this one isn't. Okay. And so this goes as t to the 1/3. That's the prediction of the z equals 3/2. And you see that if you look at the non-integrable spin chain, at pretty much any temperature, this keeps growing. at least numerically, right? I should note that like at low temperature, at low temperature, like the field theory description of this is an O3 nonlinear sigma model, which is integrable. So you could think this has to do with that. However, like you see, you can go to temperature 10, and this looks almost identical to the integrable case. And there's been a lot of numerical work. So there's a series of very nice papers by Roderick and collaborators, where they study classical spin chains, where they start from an integrable point and they break integrability. And what you're seeing here is that if you look at energy transport, it's purely diffusive. So at the integrable points, energy transport would be ballistic. But they break integrability so that if you look at now energy, it's just diffusion. However, if they look at spin, they still see that exponent 3/2. Okay, so there's something going on here. Like you can basically break integrability. If you look at everything but spin, it looks like a chaotic system. But if you still look at spin transport, you still see that is equals 3/2, maybe KPZ like physics. Okay, so as the claim I'm going to make is that it's very robust, and we want to understand that. Yeah, so let me, in order to do this, I'm first going to tell you briefly how we understand this equals 3/2. This is relatively old work, so I'll go quickly, and if you're interested, you can ask me questions about this. So the way we understand 3/2 is in terms of like the quasi-particle excitations of integrable systems, right? So one way to understand integrability is that there are systems in which you have stable quasi-particle excitations at any temperature, right? Even at infinite temperature. And those quasi-particle excitations are well established from Bethe ansatz, right? I'm just going to give you like a cartoon of what they would look like in XXZ if you take delta larger than 1. You can imagine you have a vacuum, which is like a ferromagnet, and excitations would be like magnons, like single spin flip, or bound state of magnons, which in a cartoon way would look like this. I'm going to label them with S, those bound states, and the claim is you have bound states of any sizes in those systems, and those are stable at any temperature, right? So they're not just like low excitations above a ferromagnet. They're, even at infinite temperature, they continue to be nice excitations. And, the claim is that those guys behave like nice semi-classical particles. And so this is where I'm going to quote at least some thermodynamic Bethe ansatz results. I should say that also relies a lot on this field of generalized hydrodynamics. So those guys at the Heisenberg points, they don't look like that at all, but they still exist, and they come with some density in thermal equilibrium. They have some velocity and they carry some charge, right? And so once you have quasi-particles, it's tempting to just write down like a Boltzmann type equations, and this is in some way what generalized hydrodynamics is. So once you have quasi-particles, you can understand transport in terms of those quasi-particles, right? So of course, like if you have quasi-particles moving ballistically and they carry some energy or charge or spin, the natural conclusion would be like transport should be ballistic in integrable systems. Okay, they should not like shock you. If you have an integrable system, you have infinitely many Korsov quantities. Chances are like your current will overlap the Korsov quantities and will not decay, and therefore you'll get ballistic transport, which is indeed the generic case if you're not at like special points. But so for this Heisenberg spin chain, there's something more going on. And the way we understand this is that those quasi-particles move around, but they are effectively neutral. Okay, and so again, I'm going to draw a cartoon of this in a just ferromagnet. Think of like, take an XXZ spin chain when delta is large. So when delta is large, like say your ground state would be like, your ground state would be like a ferromagnet state, and you'll have like domains, ferromagnetic domains like this, and those guys are essentially frozen if delta is large, right? They move at very high order in perturbation theory in delta. However, you can have like single magnons moving around, like a single spin can hop, right? And say you can have a spin up moving in a sea of spin down, and you can ask what happens if this guy collides with like a domain of spins up. And what happens, you can just look at this picture, is a series of allowed moves that preserve the constraint of delta large. is that this will convert into a spin down in a sea of spin up. Okay. So if you want, this is a scattering process between a magnon and like one of those domains. And so, as a result, this is shifted, but the important point is like this magnon, we usually say magnons have spin 1, but it's either spin 1 or -1, and this kind of oscillates with time. This ends up being true also at the Heisenberg point. So basically, like those quasi-particles moving around, they dynamically become neutral, or like their charge oscillates, if you want. And that's the key mechanism, at least that's how we understand it, of like why we have this equals p hat. I mean, there are different ways to understand it, but at least that's how I like to think of it. So here you see like a magnon, for example, like is again flipping its charge if it collides with an object bigger than itself. And so this remains true, like at the Heisenberg point. And you can do a back of the envelope calculation that if you take like one of those bound states, it will become neutral effectively on the time scale that scales with its size to the cube. Okay. And so this tells you that at time t, yeah.
So this is for magnon, but if you have bigger cluster, then you're thinking about
Yeah.
magnons will make something bigger, or
Yeah, so that's true. Like so this is for a bound state of S magnons, and I'm saying that this guy will effectively become neutral on the time scale S cubed. Okay, so we have like more serious calculations of this, but this is the outcome of the calculation. Yeah.
you're using perturbation theory to describe its condition.
No, you can use Bethe-Ansatz. So yeah, so the velo, all of this follows from Bethe-Ansatz results.
Wait,
Right?
can
Yeah.
you just say again? So the reason it's S cube and not S to the 7th power is because one of the things that you wrote on the previous slide.
Yeah, so it follows from like those, like this data, like the density, the velocities, so you can, like the screening, yeah, so as I wrote here, like, okay, the quasi-particle S will get screened if it collides with things bigger than itself, so that gives you a density, and we know its velocity, so you can get a time scale out of that. So it's all like, yeah, just from basic scaling. Okay. So anyway, so that's pretty much how, like, that's a lightning review of how we understand anomalous transport. So at time t, basically you have like only bound states of time t to 1/3 contribute to transport, essentially. Like bound states that are smaller than this are screened, they end up being neutral, and bound states a lot bigger than this, they're very slow. Okay, so you can like plug this into a Kubo formula if you like. This is a cartoon Kubo formula. You have like a sum, think of it as a Boltzmann type approach where you sum over quasi-particles, you put a matrix element, and so on. And so you can put all those ingredients, and that gives you a diverging conductivity. Okay, and that exponent is the same as the z equals 3/2. All right. So again, I'm going relatively quickly because it's a relatively old result. Let me mention one thing that will be important is that transport is dominated by giant quasi-particle at long times. Like if you take T large, it's dominated by bound states of many magnons. And those giant quasi-particles, they're essentially classical in nature. And so this is something we showed a while back. They're like solitons of this classical lambda Lipschitz equations. And they look like Goldstone modes. And this will actually be important for later. What I mean by Goldstone mode is they're like soft excitations. They're like slow rotation of the vacuum.
Are they rare or they're?
No, they're everywhere. Yeah. So they have this density 1/s cubed. Okay. Yeah. Okay. So let me now like break integrability. Okay. So let's think about what happens if you break integrability. I don't want to be fine-tuned at the integrable point. I want to break integrability. So let's think about it, right? So the most naive thing you should think is, okay, now if you break integrability, those quasi-particles will acquire a finite lifetime. They'll decay. Most naive thing you can write down is the Fermi-Golden rule estimates of they'll decay with the rates scaling with matrix element squared, some density of state factor. And maybe generically, if you like break all symmetries, like you can estimate this rate, but you could imagine maybe like, let's take this rate to be independent of the size of the bound states. And if you do this and you plug this in your favorite Kubo approach, it will just give you diffusion, right? So basically, if you make those giant quasi-particles decay, they will just die and everything I told you about will go away. And so this is something you can see in numerics. This is a time-dependent diffusion constant for different like integrability breaking rates. And what you see here is it saturates, giving you like regular diffusion. Okay. So this is kind of the standard approach. But so one important point that we realized already a while ago is that if the perturbation preserves the spin rotation symmetry, something different happens. And the reason is like those giant quasi-particles I mentioned, they look like Goldstone modes. And so because of this, if you perturb them, if you take a perturbation that preserves SU2, it will be suppressed, right? That's what Goldstone modes do, like just like energy is. So if you take a bound state of size S, like the matrix element will go as 1 over S, because locally it's very close to the vacuum. Okay. So this tells you that at least if you preserve like spin rotation symmetry, this equals 3/2. If you just do a naive like a Fermi golden rule approach, looks stable. Okay. And so we did numerics at the time. So for example, you could take an Heisenberg chain, perturb it by some next nearest neighbor interaction. And okay, we cannot go to super long times, but like this is an extracted dynamical exponent. Even if you break integrability in a sizable way, you still see like 3/2. You don't see like really diffusion.
How was the light in the integrable case? How was the effect of the lifetime scaling with S? Yes,
Sorry, so that S cubed.
it's cubed. So this is a faster decay. Right? So when you say stable, you
Oh, so,
don't
sorry.
mean strictly stable, right? This would give it a lifetime.
Well, there's also like density of state.
Hmm?
Yeah, there's all. Oh, you're thinking of the 1 over S. Yeah, so you're saying that will give you 1 over S squared in the Fermi golden rule. Yeah, and there's also density of state factors. Yeah, so 1 over S squared would technically give you.
Also,
Yeah.
even though you're at infinite temperatures, you're in the middle of the spectrum, I would assume the density space would be constant, but that's.
Yeah. So if you just put like naively 1 over S, so we did this. Okay, I'll get to that actually. I will talk about rates that go as 1 over S squared when you put noise and preserve it. So that does give you diffusion, but with log corrections technically. Okay. Yeah. Yeah. So I mean, you're right. If you just take 1 over S squared, that is faster than like the Fermi golden rule decay. Okay. So this brings me like to the more recent work. Okay. So the thing I did want to talk about, I just have a couple of slides on this because there's not that much to say. So we decided to try to do this more systematically, purely numerically. And so in order to access long time scales, we forgot quantum mechanics and went to a classical model. So going to focus on a classical version of this. So classical Heisenberg is actually non-integrable, but you can find a classical Hamiltonian that has SU2 symmetry and shows the same physics. And you can break integrability. So lambda will be my integrability breaking parameter. So that's integrable, breaks integrability. And in order to reach long times, I'm also going to use a discrete time version. So if you want, it's a Floquet model for classical circuits. And there's a version of this that preserves integrability due to Tomasz Prodan and collaborators. So this is nice because it means you can reach long times without worrying about Trotter step errors and whatever, right? So the upshot of this is like there's no truncation error or anything like this. We could do huge systems for very long times. And so we really went all in and on just spamming our clusters just to get a lot of good data on this. Okay. And so now so this is an example. This is a return probability, autocorrelation function as a function of time for integrable case where you see this 2/3 and you break integrability all the way where you see diffusion. And the claim that I'm going to make is now we have good enough data that we can actually see the crossover to diffusion. And so this is the first time we actually saw it. Previous data, even for classical systems, you never saw going to diffusion. So I should say I am preserving SU2. So here, this whole spin chain is isotropic. It preserves SO3, the spin.
Infinite temperature.
Infinite temperature. That's right. Yeah. So now we have good enough data to see that crossover. So we can extract a dynamical exponent as a function of time. Let me skip the detail. We do this by looking at fluctuations as a function of time. This doesn't matter too much, but we can extract a dynamical exponent as a function of time, which starts at 3/2 and goes to diffusion at long times. So we can clearly see first that we can see it goes to diffusion. There's no But not only that, we had good enough data as we can get enough statistics to get a nice crossover timescale for this. Okay. And so we can do this by kind of collapsing this data, or like what you see in the inset here is plotting what we call T star, which is the time it takes for Z of T to reach a given threshold. And you see it behaves as a polar with an exponent 6. Okay. So that's the claim, like purely from just numerical data, we see a crossover timescale for diffusion that goes as, integrability breaking perturbation to the -6. Okay. So 6 is a fairly large exponent. So which does explain at least why, you need to go to very long times to see it. So this is larger than your Fermi-Golden rule naive estimate of 2 here, right? So it's not exponential or anything, but it's still a fairly large exponent. And just to make sure we're not completely crazy, we did various other checks. Like, for example, we can extract the diffusion constant at long times by looking at the autocorrelation function. At long times, it's diffusive because it's 1 over square root of T. It has like hydrodynamic tail corrections. And, again, like we have to have a bit of a loving eye to extrapolate this at long times, but we can get a diffusion constant as a function of lambda, and it scales in a way, again, compatible with this. So as far as we can say numerically, everything is, consistent with that lambda to the 6.
Why it's 6?
Yeah, so that's my next slide. So now let me tell you what we understand or not. So this was purely numerics. So this will tie back to David's question. So I should say, so we did this both for like, clean perturbations that are like flow case systems. Also, if we have noise, so we put like space-time dependent parameters. So in the case where we have noise, we can actually understand this lambda to the 6 pretty well. So if we have noise, like if you consider noisy perturbations, even like a single soliton moving in vacuum will decay. Okay, so this is actually a plot of this. Like this is a soliton as a function of time. And, without integrability breaking, it would just propagate. But we put noise, and so it's basically evaporating. Okay. And we can characterize how it evaporates by looking at some kind of IPR, quantity that characterize how localized this soliton is. And so this decays exponentially, and we can extract the rates. Okay. And we can also, of course, like in the quantum case, we can estimate this using Fermi-Golden rule. And so that rates, it's not actually perfect numerically, the exponent is a bit larger, but we're pretty confident it goes as lambda squared and it goes as 1 over s squared. So that's the 1 over s from Goldstone physics that you were talking about. So in that case, we understand this rate. So note that this goes as lambda squared. But importantly, this doesn't set the crossover. What sets the crossover is comparing this rate to the 1 over s cubed of integrable physics. So you have this, so that's just going back to like this slide here. Okay, so there's this time scale. So there's a rate 1 over s cubed at which like those bound states get screened. And we should compare that to that, Fermi-Golden rule type rate. And if you do that, it gives you a crossover that if you convert it back to a time scale is lambda to the 6, -6. So this is probably something we should have realized earlier, but better late than never. And so so even if we have like a simple rate like this, it gives you actually a large time scale.
The result is classical. Is there a way to?
Yeah. So
say why the Fermi-Golden rule applies classically?
Yeah. So maybe people that know classical physics better than I do would do that, but we just do like all calculations in the quantum case, and we just cheat and do numerics in the classical case because it's easier. But I don't know. Maybe that's a question for people in the audience. So if someone can tell me how to do Fermi-Golden rule calculation for classical systems.
It's like it's more general than Fermi-Golden rule. You have a relaxation process, which is this one, and you have the screening process.
Yeah.
And presumably there is a classical version of the screening process.
Oh yeah, like all the physics. So that's okay. That's true. Like all the physics is classical. Yeah. The integrable physics is classical.
That's what I'm saying. So if you have 2 time scales, then you don't have to think about.
No, but to estimate this, I mean, okay, here we get it numerically, but the way I understand this is through Fermi-Golden rule. But there's probably a classical version of deriving this as well that I just don't know. I assume so. You could probably just do second order perturbation theory as well there, right? Like just.
It should be some more encouraging.
Yeah. That's just my, I prefer quantum systems, I guess. It's just, yeah. Anyway, so that gives you this lambda to the 6. Let me just like wrap up with like things we do not understand. So this was for noisy perturbations. So now if we take like non-noisy perturbations, now like single, like a single soliton will not decay, right? So you need like many body scattering things to happen. However, like numerically, we don't really see a difference in the data if we look at noisy perturbations and non-noisy perturbations, okay? So one conjecture is maybe like the small solitons moving around effectively act as noise, maybe. But of course, we also think there should be other many body processes going on that we don't fully understand, but somehow the time scale appears to be the same. One thing I should mention is like this rates here is not fully satisfying. If you put it in Kubo, it doesn't quite give you diffusion. It gives you like a log correction to diffusion that we don't really believe are real, at least at long time. So it means there's probably many body processes at higher order in perturbation theory that will restore diffusion eventually. And we don't fully understand this. And yeah, with this, let me just thank you very much.
To make this lambda large in the quantum case and
Yeah.
compare your numeric with this prediction will work.
Yeah, I mean, our lambda is, yeah. So I should say, like, in order to, this is technically perturbative in lambda, right? You would think. Of course, numerically, in order to actually see anything, we take lambda to be fairly sizable. So here it goes all the way to 0.4. And lambda, like, it's defined like, I'm also weakening the non-integrable case with this lambda parameter. So yeah. So like the, integrability breaking parameter is maybe lambda divided by 1 minus lambda, if you want. So this is a fairly large, we're doing fairly large perturbations. Because basically otherwise you just don't see anything. Like you never see the crossover to diffusion. I should say that was the conclusion of many other papers, like people never saw the crossover to diffusion. We do, but we kind of have to push it a bit in order to, yeah. Yeah, the time scales are ridiculous, I should say. Like, I mean, we really go to time scale 10 to the 5, right? Like it's a bit absurd. Like, and we really needed that to see even like remotely deviating a little bit from like, it's not really perfectly diffusive at all here, right? Like it's just on the way. Yeah.
And Sask, if I considered a two-leg ladder.
Yeah.
Dynamics of a two-leg ladder.
Mhm.
Is there a sense in which integrability breaking is more efficient there? Like, I'm trying to see the kinematics of 1D kind of just zero order.
I don't think so. I think we actually tried at the time, and that was with Braden Ware. Like at the time when we did this data, I think we tried ladders, but I don't think it's more efficient like than noise. Like so this here, like part of it, I said we did data with like noise, right? You would think noise is as efficient as it gets to, we're doing noisy perturbations with SU2.
No,
yeah.
This is surprising.
Yeah.
That's what I'm trying to say, that there must be something about the linear aspect of this and other perturbations. Basically, I was trying to think of other perturbations that would mimic a two-leg ladder.
Okay.
More efficient, but maybe.
Yeah. So. Yeah, so to be honest, we don't have like, we thought a lot about what higher order many processes could like give you similar scaling and so on. And the main conclusion that we have is that is all the physics that we see is kind of this rate, which you can think as a single body process due to noise.
This has to be SU2 preserving.
All of this is SU2 preserving. Yeah, that's right.
The data on the previous slide.
That is all SU2.
And with no noise. Classical model, you put a deterministic.
We do both.
Is.
Yeah, we do both. Sorry, so we do both. Like we did both noisy perturbations and non-noisy perturbations, and they roughly give you the same. So I'm not even showing, like, I can show you two plots that look almost identical. One is with noise and the other one without, and they look almost the same. Yeah, so that's the claim. That's purely numerical. It's just putting noise doesn't seem to change. It changes a little bit. It's even slower without noise, right? But that's just changes that prefactor, not the exponent. It's the claim. Yeah.
What's transaction, it's transactional symmetry in space important for anything?
Yeah.
Homogeneous.
Well, I mean, the noise is also like breaking, we haven't like, let me not talk about disorder, but like here noise is also like space-time, random, right? So we put it to be, it's random in time and in space as well.
But if I did have something which was, say, not random in time,
Mhm.
but random in space, so I wrote the probability in my line worksheet by making the J random.
Yeah.
What does the diffusion at infinity show that?
We thought about it at the time. Do you remember, Sarang, what the computer
Yeah,
was?
so
Yeah.
the kind of quantity is
That's
much
what-
easier because there's sort of a density of state singularity at like zero momentum or zero energy that like helps you with instant answers to decay rate. But yeah, we never looked at that systematically.
Yeah, I was gonna say we did,
This
yeah.
is better than this one.
But you suspect it'll be an exponent less than 6, or?
Yeah, no, I think that you probably get a 1/s by rate rather than 1/s squared, something like that. So it's not, it's slightly worse. Different exponent.
Yeah, we may want
But
to
It's
try
not,
that.
it's not too.
Yeah. But we haven't really revisited this, so let me not commit. Yeah, maybe we should actually try that, but yeah, Right. So when I say flow K, so okay, so it's a bit misleading. I wrote Hamiltonian, but we don't do anything Hamiltonian here. We really do like a discrete time. We have like a classical gates, if you want, like a brickwork pattern of gates or like that are classical maps. So when I say flow K, what I mean is that all those maps or gates are the same, both in space and in time.
There's really no noise.
There's really no noise. That's exactly. Whereas noise, there's a random parameter in those gates that we randomize both in space and in time. Okay, so that's effectively like noisy dynamics, whereas the other one is effectively what you would call flow K as a course of quasi-energy.
No question, that's fine.
Thanks.
Share your screen.
Left point.
Yeah, excellent. Sorry, getting there. All right.
Okay, our next speaker is Benjamin Brown, and we're going to talk about generalized relativity.
Yeah, thank you very much. So yeah, so it's going to be relatively basic talk about generalized hydrodynamics. Let me just make sure that this is view the screen. Okay, and yes. So, and if you have any questions at any time, please don't hesitate to stop me. Hopefully I managed to go maybe to more new stuff or more recent stuff. It's not that recent anymore, but let's see. Okay, so the plan is like that. So I'm going to talk about one-dimensional many-body systems. I'm going to give you a simple example with hard rods, but something quite general. Okay, and talk about emergence of hydrodynamics with the view of looking at integrable systems. So I want to go over first the general principles of emergent hydrodynamics, at least in one dimension, and then integrable systems in particular. Okay, so the point is, okay, start with earlier scale hydro, and then think about going beyond earlier scale with diffusive and with fluctuations. So and let's see how far I get. Okay, so so earlier scale equations. I want to just remind everybody. So what are the main principles? somewhat simple principle that if you look for deriving Euler hydrodynamics for many body systems, the main thing that you have in mind is local relaxation. Okay, so you have a many body system. This is my picture of that, and it's at very large scale. It looks homogeneous. Things happen in space and time. At very small scale, okay, there are particles at intermediate scale, mesoscopic scale. It looks homogeneous, but depending where you look in space-time, it will look homogeneous but different. Okay, and okay, what we say in hydrodynamics is we say that there is local thermalization or maybe local entropy maximization. So when it looks homogeneous, it's a very particular state, not any state, and it's these Gibbs states that should appear. That's the basic statement. And what are the Gibbs states? Well, there are states that maximize entropy, of course, under the constraints of all the conserved quantities admitted by the system, whatever they are, the energy, number of particles, momentum, and all. So these are the Gibbs states. Okay. So then okay, let me take the example of the hadrons. This was introduced already yesterday. So these are particles that interact with each other just by exchanging their momenta. It's very simple. And they have a little length, d here or something. And here I'm thinking about just having two different velocities. Of course, the velocities are preserved by this interaction. So here there are two conserved quantities, number of rods with plus and minus velocities. Okay? So the Gibbs states are pretty simple. There are two Lagrange parameters. And I can consider then the conserved densities and conserved currents for these conserved quantities, right? This is the base of hydro. And so these are my two, or they can be more than two, conserved densities, and they have associated currents, which I can calculate. I mean, there's kind of an X dot there, essentially, right? So, and then what I would like to calculate are the statistical averages in the Gibbs states, right? In hydrodynamics, you have local Gibbs states. So let me consider the Gibbs states of that system. Okay? So I want to calculate the average of this local density and local currents inside. Well, okay, here originally I have some initial state perhaps which is varying in space and time, which I didn't write, and I would like to evaluate these local averages in xt in space and time from some initial state. So the Euler hydrodynamic assumption, the first picture that I showed, was very simple, that the true averages that I would like to evaluate in my true macroscopic system can be approximated by the local relaxation idea. Okay, so these true averages are approximated by averages of these densities and currents inside some xt-dependent maximum entropy state. Right. So I need to know my maximum entropy state, because once I know them, then I just write this continuity equation for densities and currents. And these are the Euler equations of the system. So they're completely general, right? And I can do that for the hadrons. And it's not too difficult to do for the hadrons. I show you, forget about that for now. I'll show you here the currents evaluated in the maximal entropy states. Okay, these are the currents, which I can write in terms of the betas, the Lagrange parameters, but I can also write in terms of the average densities, right? Actually, there's a bijection between the Lagrange parameter and the density. But if you know the temperature, if you know the pressure and chemical potential, then you also know the energy, particle density, and momentum density, right? This is a bijection. So, okay, you can do this bijection, and then the current in this particular system, the hadrons, is very simple, can be written explicitly, and it has this form. And when you put that in the hadron equation, you get equation for the Qs, which you can rewrite in the so-called quasi-linear forms by calculating the derivative of G respect to Q, which is called the flux Jacobian. So this is the Euler equations. Okay. So this actually for hadrons has been proven rigorously. So that being easy to calculate, but the fact that this equation arises proven rigorously from a large family of slowly varying initial states. Right? You take initial states slowly varying, it can be proven that it's correct at large time and large space. Okay. Now this of course correct, not always, but really at large space time. There's a scale there, right? There's a scale of a variation of the initial state and a scale of where you look in space and time. And all these scales should grow together simultaneously as ballistic, right? And this is what is proven that is correct. Okay. And of course you can, so here I have the example of two velocities only. I can recast this equation into a completely standard form. The hadrons are Galilean, so I can take the total density and some kind of velocity, momentum average, from which I define the velocity, and I find these two equations. So this is just standard form where there's a particular pressure term there that you can calculate explicitly. Okay. Now, what's happening? So the general concept is that, right? You have some maximal entropy state, the Gibbs state, right? Actually, what are the Gibbs state? The basic definition is that these are states that should be clustering in space. When you have a Gibbs state, there are no correlation in space of finite temperature at 1D. So clustering, so correlation decay at large space, and space-time invariant because these are stationary, right? You have locally stationary homogeneous state. That's your relaxation. Okay? So these are the states you consider. Okay? And in fact, the proper understanding is that what you are looking for is the full manifold or space of all such states. And once you have them, then you can construct your Euler hydrodynamics. Okay, so that's kind of the question. And in principle, these are the Gibbs states. Okay? And the other thing that's important for this Euler hydrodynamics to hold, so you have to have not only the full set of states, but also the correct full set of conserved quantities, right? And that's actually not completely trivial. I mean, in principle, what are the conserved quantities? Well, okay, so you have some conserved density that could write some, but what tells you that you have them all, right? You need them all to have the correct Euler equations. Well, there is some mathematics to that, and I'm not going into this at all, but the mathematics there, so you should look for observables which are invariant in time and which scale linearly. I mean, there's no notion of how they scale linearly. Basically, correct notion is to take the cumulant, the second cumulant of such thing, and ask for them to scale linearly with the volume, or wherever in space they are supported. Supporting periods and all that. And somehow from this you can make a Hilbert space. And once you have the Hilbert space, you have a notion of completeness, and somehow then you can make a precise definition of what is the complete set of conserved quantity. Okay, but it's hard to calculate an explicit model. In principle, there's a definition. Right? Once you have that, once you have these states, then you have your Euler hydrodynamics. So general consequences, you can do basic thermodynamics on that. I mean, once you have these states, you can actually define your ambient temperature by standard thermodynamic quantities. You can define the free energy similarly. You can define an entropy, and then from general construction, it's preserved by the Euler equation. And the flux Jacobian, this derivative of current respect to densities, actually is not any matrix by general properties, again, of statistical mechanics, by clustering in particular. It's a matrix that has a real spectrum, which with the meaning of the sound velocity. So it always has a real spectrum. And in fact, if you multiply by C, the resulting matrix is in fact symmetric, some kind of reciprocity, but at the Euler scale, not the diffusive scale. Okay, so these are general consequences. Okay, now this is a picture that I have in mind, right? You have all these possible observables, and by relaxation, they kind of converge to some submanifold, and the Euler evolution is evolution on the submanifold, with the conserved charge being some tangent to that submanifold. I don't know how to make this mathematically precise. It's kind of general point of view. Now, I'd like to do integrable systems where the hardware doesn't are integrable, right? So if I have a lot of velocities, right? Not just two velocities, but a lot of them, maybe infinitely many. Actually, I have a density of conserved quantities. For every V, it is conserved. Okay, so I have to put them out, right? And this is a generic thing, right? And if integrable systems have many conserved quantities, so set of states is very large. These are the GGEs, the generalized Gibbs ensemble. Okay, and also there are infinitely many equations, right? So this is okay. Then, if you just apply blindly your equation, your idea or hydrodynamic ideas, that's what you want to construct, and that's what you write. Now, if I just had that, I wouldn't know what to do because there are infinitely many equations. How to make sure it's correct? Yes.
Sorry, I feel like you're shifting gears into like more
Yes.
technical stuff. So
Yeah,
the last cartoon
Yes.
is
The last cartoon. Yes.
I'm not even sure how to make sense of it because
Yes.
on the one hand, you're not generating entropy. You explicitly.
Yes. Wait.
But then the notion of course draining to me is generating entropy.
Yeah, for sure.
Somehow,
Those things
The definition of entropy, are there multiple definitions of entropy? So that
yes, of course there are. Indeed.
There always are.
Right.
They always
What
are,
I'm trying to
yes.
say is that like your first picture.
So
of
this is well-defined entropy. I mean, this is the basic thermodynamic entropy that you would think of from the point of view of local thermalization. That's preserved by the equation. But of course, you lose degrees of freedom here, so you must somehow generate entropy. So as you reach the earlier equation from your microscopic, something happened, like you lose information somewhere. Yeah. But I was saying is that once you're here, this is at the largest scale of space and time, right? So originally you have some large variation, diffusion is there, or maybe other things, other effects, right? Macroscopic effects. And then a lot of things happen. And then as you go to the largest scale of space and time, then you go to your Euler hydrodynamics. Then you would say, well, eventually you should just thermalize and it should be nothing. You should see nothing, right? And that,
But
that's
hang on,
true, but
again,
that's-
I want to make it precise,
Yeah,
so
yeah.
there's real time and there's some course RG time, if you like.
no, but,
I use coarse grain, I use.
no. There's just real time.
No, but how do you,
Yeah, okay, maybe
what
I-
allows you to draw your mesoscale,
Yeah, let me write,
cell?
the
Please do.
precise equation, right? There's a precise statement that you may want to prove that you may ask mathematician to prove, right? Which is this, so this average of Qi xt, okay? This is some density in your initial state, this is real time in your space. Okay? Now you scale your stuff, you put an L there, and you put an L there. And then you also scale your state. It's a mathematical statement. You don't do that in reality, but you scale your state. So your state has some initial density like that, and there's some scale there. And so your state is scaled simultaneously. Right? And if you do that, you look at the limit when L goes to infinity, and the question is, what does this limit exist? Right? What is the limit and all that, right? So the statement for the hydrodynamics is that this is some quantity Qi, something like that. You do the same for Ji, this is some quantity Ji. I put a little bar there, just different, or maybe I should put a bar on top, something like that, right? And the statement of Erlich Hydro is that these things, so these are the average in some xt dependent betas, right? With these betas satisfying the Euler equation. That's a statement. Okay. So this limit should go to something, and that limit should go to something, and there should be unique beta that describes both. In fact, should be unique beta for every local observable, not just Q and J. That's the statement, right? It's a strong statement. Maybe it's not true for every local observable, at least for Q and J. And these betas, they're not anything, they satisfy the Euler equation. So I didn't have to do cross graining, I just had to take large space and large time. Now, in fact, I'm not completely sure. I mean, there's no proof of that in any non-trivial model, except in the hardware there's proof, correct? Right? But you may have many things happening in that ring and other oscillations. That kind of things can happen, right? Depending on the model. So you might have to take some kind of further averaging. This is maybe your problem, right? You might have to take some fluid set averaging of that. Meaning maybe I should add some little y there and add some little tau there and do an integration over dy and d tau on some little kind of fluid set that's smaller than the L, maybe, I don't know, from minus square root of L to square root of L, or maybe some other power, and kind of a divide by square root of L square for the, some, so I might need to do that, or no, I don't know, right? So for the local averages, I think in most situations you don't need to do that, but when you start talking about probability functions, you do, yeah. So this is what I'm talking about. Make sense?
Food for thought.
Other questions? So, and then this picture is very abstract, and I don't know how to make it fully precise, but it's kind of what there is in mind. And now, so there's food for thought. There's already a lot, right? It's not completely trivial. And then I add a lot of non-trivial stuff in addition to that by they saying now there's infinitely many kinds of quantities, and I just blindly apply the same principle.
But here you must be taking the infinities in a certain order.
Yes, yes,
right?
for sure,
You
yes,
somehow have to take
yes. So
the system to infinity first before the number of
Yes.
conserved quantities. to
Indeed,
infinity.
indeed. So if you have n particles, the maximum is n conserved quantities.
Yeah,
And you want to do hydro, so you have to take your system to infinity. Now you have an infinite number of them. And then within that infinite system, you have to talk about relaxation. And then you have to talk about convergence of that sum. Or, something like that, right? Yeah. So these are very subtle things that people have
But
thought
in-
about a lot.
In
Yeah.
a quantum integral model, there are a number of conserved quantities proportional to the size of the
Yes,
system.
precisely, yeah,
Whereas
exactly.
here, you're somehow, to make Euler, you
Yeah.
have to.
Already be an
you
infinite
have to
system, yes.
already
Yes, because you want to scale
have these
anyway,
two
right?
Infinities be different.
Yeah, so I mean, my understanding is that you first take your system to be infinite size.
Yeah.
Then you may take your initial state to be, say, homogeneous everywhere, and then have some bumps there or something like that, and homogeneous or something like this. And then you look for the evolution of that. And your bump there, you can make it grow, like with a scale L, and your distance and all that. But already from the beginning, your system is infinite size. So you have available infinitely many conserved quantities. That would be the same. But then the question is that, as I go to this higher conserved quantities, they are not so local anymore. This is what you connect to your question. They are, I just want So,
Go ahead.
connecting to your question, why there's just, for n spins, there's just n constant quantities, because the nth one covers the whole spin chain, right? So it's actually not local anymore.
Correct.
And I was asking for local density, right? So as I have an infinite system, infinite spin chain, I go very high in these I, eventually they're not local anymore. So then you would say, well, this doesn't make sense, why I cannot do Euler-Hadro for that, right? So you hope that they will not contribute too much to the Euler-Hadro, and I don't know the full explanation, the full understanding, right? So for now, you just write that. It's a bit abstract. You go along with this, but you have to do something more about how to organize them, and I'll come to that just now. Okay, yeah. But yeah, so other questions, maybe you want to say something else, maybe. Or... So there are quite a lot of non-trivial questions, but then if you just blindly do that, then that's what you have. I should note that, for the hard rods, it's a continuum, right? So actually you don't have a sum or integration over V here, really, right? You have a density of constant quantities, right? In V, in velocities. Okay, another thing about integral models, and this is crucial to have this nice universal structure of GHD, is that it's not only you have constant quantities, the scattering of particles is very special. And this is what makes the whole thing, then you can work it out. So scattering of particles is very special in the sense that, well, this is the main thing, there is, so contrary to non-integral models, if you have many particles going each other and hitting each other with different momenta, the in momenta and the out momenta are exactly the same. The momenta are preserved. This is clear for the hard rods because the velocities are always preserved, they just exchange velocities. But it's a general phenomenon. Any many-body integrable system. Now, many-body integrable system in general will have maybe non-trivial asymptotic degrees of freedom. They can be waves, solitons, they can be particles, they can be, I don't know, some of the stuff that Romain was talking about, these kind of domain walls. Okay, but they are objects and they have momenta, and these momenta are preserved in scattering processes. And not only that, the scattering shifts, so the scattering matrix factorizes into two-body processes. So in other words, if you have a many-body scattering, you could think of that, you could kind of move your trajectories, change impact parameters so that the scattering occurs at very far separated points in space-time. And then the full scattering is just the sum of the scattering of each of these two-body interactions. So in a classical way, you think of a scattering shift like solitons time delays, and so when two particles they interact, maybe they get stuck together a little bit, and then they get out, and then it's the same trajectory, same momentum, but with a special shift. And then in a many-body process, the spatial shift is just the sum of the shifts incurred by all these two-body processes. Okay. So there's a factorization of scattering which is highly non-trivial, right? So there's no non-trivial three-body scattering. Then you can ask actually about extending that to have non-trivial three-body and no non-trivial four-body scattering. This model called three-wave model, which there are stuff like that. But this is kind of the most basic situation, right? No non-trivial three-body, it's just product of two-body. For instance, in the hard rod is the case because if you look at the rod scattering, what they exchange the momenta, and the correct kind of quasi-particles that you want to take is the tracer of the momentum. That's a nice quasi-particle. It has momentum initially, it has momentum at the end, the same momentum. But if you look at this tracer, when they hit each other, this tracer kind of jumps by a little length, which is A here or B previously. And this phi that I introduced in the previous slide, then it's just minus A. Okay. Now, so with this in mind, then you can construct the hydrodynamics. The first thing is the state. What is this manifold of states, right? Well, it's a large manifold. There are many constant quantities. Huge amount. In fact, it's a manifold of functions because you can consider, this is kind of the right way of seeing GGD. So you look at your fluid cell, right? You want to say has it relaxed, okay? Well, you take it out of the system, put it in the vacuum, and then let it expand. It's like a time of flight thought experiment, if you wish, right? And see what particles come out, okay? They will come out with some momenta and look at the distribution of momenta. And this distribution is what characterizes your state. So you have this, I don't know, Q theta here. This is my distribution of momenta. And so I have a manifold of state, which is large, which is just our possible function Q theta, okay? So your question about how you organize the constant quantities and all that, now I've kind of completely put that on the side. I don't care about what the constant quantities look like. All I care about is what the asymptotic momenta look like. and a function of theta, and this is what how I characterize a state. Okay. Then you can calculate the free energy from Q theta. That's using the so-called thermodynamic Bethe ansatz, but I don't need it here, right? So once you have that, you can calculate all quantity, free energy, entropy, and all that stuff. It's known stuff from the 60s and 70s, right? But for now, I just take that. Okay. So this is my set of states, large set of state. And the other thing is that, well, I want to calculate the currents in this large manifold, in all these states and manifolds. Well, it is more complicated, and I apologize to all the people who worked on that. I didn't put any reference, but many people worked on that. And it turns out, by using Bethe ansatz calculation, by using quantum field theory principle, by looking at soliton gas, by using all kind of calculations and all kind of different models, there's always the same equation that come out. It's a universal equation. And the equation is that J theta has the form of some velocity times Q, where the velocity satisfies a linear integral equation that involves a two-body scattering shift. I don't have an explicit form for the velocity, but it satisfies that. And I can show in many situations there's a unique solution. Okay. What does this equation mean? Well, it really means you look at your particle, right, and it interacts in a two-body way, right? And so it's come to you. So as you go to very large time, there's the velocity propagation and then some time delay accumulated. So you just sum out the time delays. That changes the velocity, and if you do that in a consistent way, you get this equation. The question.
Yeah, so initially you started with a Q of XT. So
Yes.
where did the XT go?
I'm going to come back just right now to that, yes. So because now I'm doing just the blind application of general principles of hydro. So I'm looking at the fluid cell and the maximum entropy state there, and what is it? So calculating the current and densities in there. And then I put that in the equation and I get my GD equation. So for now, it's just everything is homogeneous, like I'm thinking about the fluid cell. So I have this and this, so I have a relation between the current and density, like I had the beginning for the hard rods, right, with a simple equation. Maybe I come back to the beginning. This equation I had for the hard rods. Turns out the two are equivalent, not trivial to see, but the equation with the linear integral equation, I put the hard rod data and I get that, okay? But it's more general, so this is more general. This is in principle applicable for every many-body integrable system, quantum or classical. All you need to know is this particular function there, which is consequence of basic calculation from integrability. Okay, yes, the question?
Before Q of theta is a function.
Q is a function of theta, I see that as function of theta, and that characterizes state, yeah.
Are we just multiplying?
Yes.
Times theta? It's
Really just
it's
multiplication
not a-
time
it's not
directly,
like
no
Q is an
operator.
operator.
Yeah, just multiplication.
It's diagonal in theta.
Indeed, and this is an important point, essentially.
That's a-
These are essentially the sound velocities. It's like diagonalization. These are the sound velocities. Indeed, very good. So, okay, so this, now I put the X and T, but just really blindly, I haven't derived that in any way from macroscopic, right? Just apply Euler. So I put the X and T, and this is the equation I get, right? dtq dxj, J is via Q. And now everything depends on the X and T, the state depends on X and T. And that's the GEG Euler hydrodynamic equation.
So
Okay.
are these arguments generalizable to arbitrary dimensions?
Good question. So first of all, well, yes, I think so, yes. But to have something non-trivial, you have to have many course of quantity in higher dimensions. Now, there are field models in higher dimensions, indeed. So you can write something like that. But right now, people have not been able to calculate this current in terms of densities yet. Although I know how to do, I think. So we're working on this, yeah.
Is the converse code, you can start from this, it always has to be something underlying the non-integrable structure.
So-
below that.
Yeah, so I mean, the general arguments is should be always true, whatever your model is. You know your manifold of state, your constant quantities, bang, you write the equation, early equation should be true. There's not much controversy about this. I mean, diffusion gets much more complicated, but Euler scale, that should be true. It's very general. So integrability, then if you have many constant quantities, well, you put them in all these equations. If you have the scattering structure, that's what you get. And in a lot of many-body integral models, you have that scattering structure, and so you have that. And higher dimension, some similar principles, but different equations, then that will come out. You've got to calculate them. Yes.
But I thought it was important that you have clustering property of finite temperature. So it's
The
not-
what? Sorry?
The clustering property.
Yes, okay, very good, very good. So yes, indeed. So this is my understanding in a way. This is an important assumption within this construction. And if you don't have that, then you lose a lot of it. And perhaps if you have a continuous symmetry breaking in Gaussian mode, then something else comes out, not too sure, right? So you have to deal with that appropriately. We know Gaussian mode contributes in large scale, of course, right? But in 1D, it's a bit simpler. You don't have this continuous symmetry breaking and all this. So yeah, so it's a bit clearer. But yeah, clustering property is important. If you don't have it, it changes. Yes.
But that would be the only source of temperature dependence. This is all temperature independent.
Yeah. So the whole structure is completely
Purely dynamic.
correct. Correct. Yes. That's the only source of temperature can change the structure. Yes.
One more question. So are there any scenarios where you have some dynamical equation for the current also?
So it's well, somehow these are sufficient, right? You don't need more to get everything. In free models, the currents are themselves conserved density. So actually, then you have a dynamical equation. The currents in models that are free, in fact, the effective velocity there's still one, but it does not depend on Q, so they become linear. And then having additional equation for current not the dynamical. Yes, but something to think about. Yes, no questions. I don't know how much time I have, by the way.
Another point. Yeah.
I have another 20 minutes. Okay, thank you.
Chair.
Okay, thank you. Okay, so all right, so this is the equation. Now what I want to say. So it's kind of a universal equation, not provably, but just by observation in different models, always the same equation come out, right? So it's been looked at for classical and quantum systems, quantum spin chains that Romain was talking about, right? XXZ has this equation. Classical particles, field, quantum field theory, even soliton gases. So these are, so you take the KdV and then you make it random distribution of KdV fields and you evolve it in time deterministically. So you have a random initial condition evolved in time. If your random initial condition is kind of nonlinear enough, then these initial conditions will contain mostly solitons. And then the same equation that come out, and these are called soliton gases. And the effective velocity is determined by the phi, which is the soliton scattering shift. And soliton gases were done much before we started working on the quantum systems and all that. And they are seen in optic fibers, where you have nonlinear Schrodinger equation, the focusing regime. And also, they're part of the theory of nonlinear wave turbulence. Yes.
Is it obvious that Q is continuous?
So this is a very good question, actually. It's not obvious, no. So Euler scale equations, they are hyperbolic equations. They have all kind of weird properties. But GEG equations are so much nicer. It turns out we can show, actually rigorously right now, with my student, Philipp Hübner, that if you start with continuous or like differentiable initial condition, evolve it, it will stay continuous differentiable of whatever order you start with for all times. No shock emerge ever. This particularity of GHD, right? It's not, in general, shocks can emerge, not in GHD. If you start with discontinuous initial condition, you may start like Riemann problem, right? Some two charge, whatever. It will stay discontinuous, but the weak solution, if you formulate properly the weak solution, the weak evolution, the weak solution is unique, exists and is unique under appropriate formulation of a weak evolution. That makes sense, right? And so this is a property of a GGT equation. In fact, there are properties probably of what is called linearly degenerate hyperbolic equations, where the effective velocity does not explicitly depend. The velocity of the mode theta does not depend on the filling of the mode theta itself. So somehow the modes don't self-interact. So there's some structure within it, which is quite nice. And so this equation, of course, as written, is just for continuous, for differentiable. But you may look at non-differentiable cases. You have to reformulate the equation properly. You can, and then it's still nice, unique solutions. Other questions?
I'm a little bit the sort of the universal equation for the velocity.
Yes.
I always kind of interpret it as a kind of like effective medium Hartree kind of a expression where a given theta, there's a mean field that acts to shift the velocity. But then I'm a little bit confused because I thought the power of the GHD was that I can consider very, very macroscopically inhomogeneous distribution.
Yeah.
Where one of these I can think of these solitons, quasi particles, as Roman was explaining. You know, in real space, moving from one part of the universe to the other.
Yes.
And where is this, because that's how there would be like a more complicated renormalization that would be.
So it turns out, I mean, so you can.
Where is that in the equation?
I mean-
I've seen that equation to me.
Yeah, so you can do something like that, right? Instead of certain gas, people do that, right? So you create an ensemble of many solitons, small solitons, KdV, okay, small solitons, a lot of them, right? So some ensemble, they can be like maybe you see them separately, right? So maybe they're really dense, you don't even see the solitons, so the random field thing. And then you throw in it some big soliton that goes faster in KdV, the bigger soliton. So I'm looking at kind of very large, I don't see the solitons properly, but I throw it in big solitons, so it goes through it, okay? Now, if there was, so here is a situation where there's all the soliton, here is a situation where there's nothing, right? You go through it. Then after some time, it's gonna be here. In that situation, here after some time, it's gonna be there. It's gonna be at a different position. Okay? And the difference, you know, here and there is due to, its basic velocity v times t, and this is its effective velocity times t. So this effective velocity, exactly, that velocity of a trial soliton you would throw right in this soliton gas. It turns out.
No, but my question is
And-
that if it travels through a state that is very.
And then if you
homogeneous-
travel to a state that is homogeneous, what do you do? So now you have, okay, I don't know the picture. So now you have your particle there. It has a velocity. So this is space and this is time, right? So it has some velocity and then it's homogeneous. So it has effective velocity, but as the homogeneous effective velocity changes. So maybe it will have some curve or something like that. It will curve around.
So you're saying I should use that equation in a temporally kind of
Yes.
modulated, okay, fine,
Yes.
that's, okay. No,
Precisely, yeah.
V depends on T.
And
Right,
depends on X and
sorry, I
T, yeah.
misunderstood.
Yeah, it's fine, it's fine. And so basically, this triosoliton is the thing you should think of in order to evaluate the current, as it turns out.
So, I have a question.
Yes.
The first statement that you made, universality clause, so does it mean that all the weakly nonlinear equations like KdV?
Yes.
All these things
Yes.
are of the type of.
Yes, exactly. So if you do, so in the right perspective, right? So KdV is itself a fluid equation, right? So for waves and on a certain approximation and all that, right? But what you do with KdV to get that, you do a fluid of waves, is like wave turbulence, right? But it's not any wave turbulence if you want. Well, actually, you can do any wave turbulence. I mean, take KdV, take any random distribution, there will be an equation like that will describe statistically this random distribution of KdV field as it evolves in time under KdV equation. Yeah, NLS and other things. In principle, that's the thing. Now it's been worked out in the case of strong nonlinearity, where you just have so in KdV, if you have some random field and you see what's the content of it, you let it expand, you will see solitons and radiative modes. You see the two things. So this now is being worked out in the case you just see solitons. And that's true when you have really strong nonlinearity. But if you have some weak field, you will see mostly radiative modes, but you can add them in. So basically, you know, there's a theta there can be some other index, which is the set of asymptotic particles you may have. So solitons, radiative modes, or if you have some other theory, then you'll be many particle types. Okay. So if you add them in, then that should be the correct equation, but it hasn't been worked out in Czech yet. But yes, other questions. So yes, okay. So this question, rigorous derivation just in the hard rods. And in quantum models, of course, the particles are quasi-particles. One can see them maybe as wave packets. Okay, I'm not going to go into that too much, but I think actually Romain's talk made it quite clear. There are particles there, right? You see this particle, but they are quantum, there's quantum effects, but these are the particles and they interact and they have some scattering. Okay, so here, just a relatively old experiment by now, but I would like to show it, have the graphs for it, so I can show it, that in the group of Isabelle Bouchoul, especially her then student Max Schemmer did that. So this is cold atom gases constrained by magnetic field on this so-called atom chips to lie in one dimension. So it's one-dimensional cold atomic gases, and we know they are described by the Liebig-Binigel model, which is integral. So they can put an external potential to have some inhomogeneous initial condition and then turn out the potential. You can also keep the potential on, and then you have a force term which one can write as well. But for now, just kind of turn out the potential. Okay, so this is your picture of the rubidium atoms in the initial state, and then you let the whole thing evolve and look at the density. Just very, very naive comparison. You look at the density of particle compare what you would obtain if you take conventional hydrodynamics, which is just the standard Euler equation with the pressure, the energy, the number of particles, nothing else, or GHD. And of course, they give very different things. Conventional hydrodynamics eventually develops shocks, which are never seen in experiments. People don't see the shocks. And GHD does not develop shocks and follow the experimental line rather well. And so that's kind of the experimental confirmation of the equation.
Yeah, I actually always wondered about that experiment. Like, if you take a non-interacting version.
Yes.
Like, that experiment is weakly interacting.
Yeah.
So if you do like weakly interacting particles, does it give you
It's-
something that deviates?
Yeah, so it's a bit tricky, right? So it's so it deviates a little bit, right? Which is it's not exactly. So this is better than weakly interacting. It's a bit tricky because you're in a weakly interacting regime, but it's not the free boson, and so there's a bit of your initial the fitting of the temperature is not so clear. Like you can fit how to fit the initial state is not so clear. So it's a bit tricky to do, but you could just naively take the free GHD equation,
Right.
like,
Yeah.
and it deviates a little bit. Not a lot, of course. Yes. So free is much closer than the conventional hydro.
Right.
Yeah. Yes. In fact, the GHD is not too far from free particle actually. Yes. Let's say yes. Yes. Okay. In fact, yeah. Okay. That's what it is. Well, maybe one thing to say about free particles: you can apply all this formalism to free particles, which are integrable, and you just get the Liouville equation of conservation of phase space, right? So Liouville equation can be seen as an Euler hydrodynamic equation. Kind of conceptually interesting. Okay, so yeah, so I think I said that there's no shock, and the equations are very special. They are linearly degenerate, and this GGH equation has Hamiltonian structure, actually has integrability structure. There's a lot of structure within that equation, which I don't have time to explain. Okay, other questions before I pass to next step, which is diffusion. So diffusion is a rather tricky, and as we go along in time, it gets trickier and trickier. So now you just you think, okay, this is a derivative expansion, so you could add the diffusion term, and this diffusion term you could maybe calculate it using Kubo formula. So very naively again, right? I do things naively eventually until they stop working, right? So this DIG has been evaluated in the hard rods some time ago, and it's been proven rigorously that this equation, by the way, I put the sign of T there because it breaks time based on variance. So think of that positive time, let's say, if there's no sign T. So this equation is correct infinitesimally in infinitesimal time, infinitesimal macroscopic time. So you have to take large time then small time, right? From an initial state which is locally entropy maximized, where you have slow variation maybe, but locally it's all some thermal or something like that, or GGEs, and you evolve in time enough to relax, but not too much to go too far. And that's a correct equation. It's been proven, okay? But nothing more than that been proven. So okay, and we have calculated this thing using Kubo formula in multiple models, and there's a general formula that is applicable again universally in principle. It's a universal formula that just depends on properties of the integral models. Here, there's one more property that you need to know is the filling factor. Like you need to know if your asymptotic excitations are bosonic, fermionic particles, changes a little bit. So there's a bit of quantum coming, but not very much. Right? So you have an equation for this. Now there are many questions about that. Here, one question that I wanted to ask, and because this connects to what people have talked about in previous talks. Okay. There's an ambiguity in this equation, right? Why? Because you could, I defined my earlier equation by talking about conserved quantities, right? The conserved quantities, they are QIs, right? Which are integration over all of space of conserved density, right? But the conserved density is, of course, not uniquely defined by the conserved quantity. I can add a total derivative, and it's the same conserved quantity, right? It's just one meter. But if I add a total derivative, it will not change, turns out, the earlier bit, but if I add some total derivative, it will change the diffusive part. This bit will have second derivative that will mix with that. So there's a question of what is the right conserved quantity to have the right equation, okay? So it turns out, what we think is the right conserved quantity, because that gives all the right results, is that you have to impose PT symmetry. And this is something that was talked about, or maybe I was the one kind of asking the annoying questions about PT symmetry in the other talk. So here's why. So PT symmetry, what is PT symmetry? So the precise definition that we're thinking of here, PT symmetry, okay? the symmetry of the algebra of observables, if you want to talk about it mathematically, so it's a summation of the observables, which preserve your observables and how they multiply with each other, okay? Which is such that when you apply it to conserved densities and currents, it just changes space and time, but otherwise keeps the conserved density and current the same. In particular, you could expect there might be a minus sign there. In general, it's an evolution, there could be a minus sign. No minus sign, should be no minus sign. And that's an important point. If you do have that, then this uniquely fixes your densities up to this one derivative. It uniquely fixes them. And these are the right ones. So why they are the right one? Well, from this, you can calculate on Sager matrix, essentially the variation of current with respect to force, this L, okay? And this on Sager matrix takes the form of Einstein's relation. If you have PT symmetry, take the form of Einstein's relation. So diffusion times covariance matrix. This is the general form of Einstein's relation. Further, it is positive semi-definite and given by the Kubo formula. So the PT symmetry tells you that everything you know and love is correct. Okay? If you don't have PT symmetry, then it's not so clear the identification. Okay? In particular, if you don't have PT symmetry, it might not be positive semi-definite. Okay? And the other thing is that then the hydrodynamics is irreversible. I mean, nicely kind of provably, because you can construct this entropy and you see that its time derivative is positive semi-definite. So you can only create entropy by the diffusive equation from the positivity of this matrix. Okay? So so these are the right thing. And okay, just comment here. So PT symmetry is broken in active system. There was some discussion about active system, right? So if you think about there was a talk yesterday, I think about foxes going after rabbits, right? So foxes go after rabbit. You have some kind of symmetry where you change time and exchange foxes and rabbits, right? But that does not preserve the density of foxes and the density of rabbits. So it does not preserve the densities. So it's a breaking of PT symmetry, right? So it's not PT symmetry. And when you have breaking of PT symmetry, all kind of things can happen, maybe negative velocity, viscosity.
Do we have integrable systems?
Not yet.
Break PT symmetry?
Not yet, I'm working on that.
I see, you think you might have found one?
Sorry? Yeah, so I'm thinking there should be some integrable active system, yes. And hopefully we can.
But none of it found yet.
Not yet. But hopefully you'll have this phenomenology and then you can control well because we can be something like that. Like, I'm not sure if it would be like very like physically, applicable in the real world, but at least control. Yeah, that's the idea. Yeah. So as far as I understand it, yeah. Okay. Now we have these talks, lots of talks about diffusion also, and seeing hydrodynamics as a field theory. You see, there's no field theory at all here, right? Well, it's true that you must add noise, right? In general, at the diffusive order. Right? And then things change a lot. And if your hydrodynamics is not integrable to the usual type, so in particular, if the ballistic mode, there are ballistic modes which are self-interacting, such as the sound modes of typical Galilean system. Okay, sound mode. Then what happens? Well, you add noise equation to that equation there. You think you should add noise, right? Some noise there, and it becomes unstable. In fact, it becomes just wrong. In fact, what you get is KPZ in the static glass. At least for correlation function, you see KPZ, not diffusive. The question is just wrong, even at linearized level. Okay, I come to you. And you have super diffusion. Kubo formula, you can try to calculate it. It gives infinity, which is diffusion, super diffusion. Okay, so this whole thing that I've talked about is just wrong. There's a new theory that should come into play. Yes.
Related to this question, why do we always expect PT symmetry when?
Yeah, we don't. So I don't know. I don't know. So many physical Hamiltonian systems are PT symmetric. It's actually an interesting exercise. You try to construct a model of many particles interacting with two-body potentials. Very basic stuff, right? Okay. You write the Hamiltonian, you can do that. Then you derive the equation of motion, you can do that. Now you take this equation of motion and consider a potential there that is arbitrary. So if you ask for PT symmetry, that constrains the potential to be symmetric on the space reversal, and that makes sure that you have a Hamiltonian for that. If this PT symmetry is broken, then you can write the equation of motion, but there's no Hamiltonian. So it looks like there's a relation between these two things.
You mean like the Hamiltonian will be Hamiltonian?
Yeah, exactly. Something like that. In quantum field theory, you have a CPT, it's a general theorem of QFT, relativity quantum field theory. Actually, when I say PT, I should use CPT, but okay. And so somehow it looks like it's a very fundamental property of macroscopic physics, non-active macroscopic physics. And I would say definition of activity is breaking of PT symmetry. That's my
You
definition.
want the two body because of this like relation that it reduces the two bodies down.
Yeah, so somehow you take like you can have two body particles by interaction. Now, if you break this reciprocity, so a particle, that right particle on the left is to repel, want to go away, particle on the right is towards it, something like that. Then you can write equations for that. It's not Hamiltonian. Or I don't. It doesn't look Hamiltonian, but you can write equation. It makes sense. It's also not PT symmetry. And in this very simple little calculation, a bit naive, you see the relation between PT and Hamiltonian.
There could be examples of PT symmetry not Hamiltonian.
Yeah, so yes, I think so, yes. So it's not, yeah, exactly.
So
I think breaking PT is probably more important. Yes.
sorry, P is just parity, so why can't I just consider a one-dimensional system where each unit cell has A and B atoms? And
Yes, yes.
there's a directionality here.
Yeah, exactly. So exactly. So you can have that. It's like the Fox rabbit system. So two particle tie or something like that. So,
But it doesn't have to be active, I'm just saying that I can just consider a.
yes, but
system lattice.
if you want to write, if you write some Newtonian equation or some Hamiltonian or something like that,
That's how we
I mean,
teach.
yeah. I mean, I don't know, but I don't know the full thing, right? But
Okay.
it's too wide. But you ask something like this, right? Of course, you can imagine you break naive PT, but maybe there's some other PT, right? So some transformation that does that. Right? So yeah, 5 more minutes. Yeah, no problem. So okay, what I want. So yes, okay. So you can add noise for usual hydrodynamics. You add noise. It break in 1D. It's unstable. KPZ. It breaks this. So actually this. So this is just wrong, right? You just this is not good. But at the linearized level, you know what is correct. It's KPZ. It's fine. For linearly degenerate hydrodynamics, such as GHD, then it's okay. And the Kubo formula is finite. We get an answer like for the hydro. This answer for Kubo formula. Okay. But the GHD noise is actually correct. It's not a standard noise that you write in your noisy hydrodynamics. Different. It's a recent result. It says that actually this is a bit of a not very precise formulation, but it says that it's correlated in space. So is here the expectation, the product of noise that you would add in your hydro, there's no delta x minus x prime, just delta t minus t prime. As long as your x and x prime are close enough, like within the diffusive range. Okay? It's not very precise, but these are mathematicians, and they proved something like that. They looked at kind of tracers and how they go and what their noise is, and they extract the noise precisely from the macroscopics, and you see that it has this information. So noise is very different. So still linearized physical equations should be correct, but in addition to noise being different, in fact, in the ballistic Euler hydrodynamics, there are long-range correlations that develop over time. It's like this I will not have time to go to, but it's okay. I'll say like very quickly. You have your initial state that is homogeneous and evolve in time. Okay, so you can think of, if you think in the nonlinearity, at the nonlinear level, you will have kind of sound mode being emitted continuously everywhere, everywhere in space-time, emitted always, right? With some kind of density of emission in the sound mode. And these sound modes, not at the nonlinear level, they will be correlated. And they give rise to non-trivial correlation of observable at large space separation. More precisely, if you look at the limit when, say, L goes to infinity, I'll finish with that, of A of Lx, B of y, okay, and so multiplied by L, this limit of the connected correlation function, after time evolution, Euler scale, after time evolution, there's also an L of the initial state, okay? Time evolution from large solid variant initial state. This is finite. This is greater than 0. It's a function of some x and y, which we can calculate for the hard ones. There are no long-range correlations, and these long-range correlations appear to give extra contribution in here, some extra contribution from long-range correlation. So even this seems to be not completely correct. So I'm not even sure if this general diffusive equation is correct in any one-dimensional system at all. So I'm not sure why we calculated that, but anyway, we did. Questions, yes.
How would the failure of the diffusion equation show up in experiment or numerics, like a current
It-
correlator?
Yeah, so this is,
Energy density.
If you look at,
sorry?
it would show up if you look at fluctuations, if you look at higher moments.
For sure, fluctuations, for instance, these long-range correlation, you know, you can calculate them, you know, two-point function. We did a numeric simulation of correlation of densities here and there and things like that.
So it's still diffusive as far as a 2-point function.
Yeah, but say, so for this, what you can do, but we'll have looked into that now, just calculate the current, the local current, you can find local current. It should have the form of the Euler scale plus diffusive derivative, right? But it doesn't. It has the form Euler scale plus diffusive plus something. So you see it. But it's a very small effect, and probably bigger effects will come in the nonlinear response and all that.
So, I mean, yeah, do you think that diffusive, I mean, we can chat after, right?
Yeah.
But do you think the diffusive term is there at all? Like, because we know microscopically diffusion comes from the fluctuations, right? So if
Yeah,
you think of like the picture over there, like, you know, diffusion comes from you have fluctuations.
Yeah, it's a
And
discussion about
then there
this.
will be ballistically correlated, right? Like if you take a tracer, it's like the same sound waves. Like,
Yes.
Impact, you know.
Yeah, if you have the
So-
same noise.
So if you think of noise in that way, that's, you know, in the indicable system.
Then you
know
don't need
that
to put the
you-
diffusion, just put the noise, and with that noise in that form, yeah, I agree. I
That's
agree.
what gives you diffusion, right?
I agree that this should be the case, okay? But so I'm not too sure. But what I can say is that so my student has been doing these calculations, huge computational hard runs, looking back at old papers and correcting them, finding mistakes in some papers that I cited.
Yeah.
And finding some extra contributions due to long-range correlation that he can calculate exactly. So he finds extra contributions. So diffusive term plus extra contribution. But we're not looking at noise, right? We're not looking at
So you have the-
where that come from. We're just looking at what is the current or what are efficiencies in space-time given initial condition and what did it look like? Not fluctuating, but what did it look like on average? And it's a 1/L correction type of thing. And then we see this 1/L correction, and it probably can be obtained from this configuration of just noise.
Right.
You can
Just
correct
like,
all of that.
maybe another question, if I can, like, in the,
Yeah, maybe you can say, negative 2 minutes.
Yeah, they get
Yeah,
the minutes,
yeah,
so I finished, yeah. Sorry. Okay, so yeah, so then I will go very quick. So please have a look. Okay, very good. Now, conclusion. So okay, so what I was saying was just about the long-range correlation, but it's not too much. So conclusion. So GHD has been looked at in many models. This is a list. It's not up to date right now, I guess. But the models we have looked at, there's many more that's been much more that's been done. So exact solution to GHD. There's the spin chain that Romain talked about. With super diffusion, there was a lot of work in that direction, starting from GHD, but going much beyond this basic GHD thing that I explained now. There are some lecture notes and overviews. And from the point of view of hydrodynamics more generally, right? So Euler hydro is very general. Structure is based on fundamental properties, but diffusive is a bit more, much more complex, let's say. PT symmetry seems to be essential. If you break it, what happens? Can we, like your question, can we have integrable system of active matter or something like that? And the last point was my last bit of the talk, where you look at fluctuations and correlations at the Euler scale, which are completely determined by the Euler equation. But again, going beyond that to diffusive scale is a bit more complicated. Thank you for your attention. Yes, thank you.
Last thing, right here. Euler hydrodynamics is not reversible.
Yes. That's the strong saying, which I didn't have time to kind of do.
Because as you presented it earlier, it was reversible.
It is totally
So
reversible, yeah.
there's something
No,
else you
yeah,
put
there's
in?
something else. This isn't cold, yeah, there's something else. So because we look at the correlations, these type of correlations that I explained. So we start with the state, which is
Yeah,
locally thermal now that negative volt. These correlations grow in time. So Euler hydrodynamic equation itself is reversible.
Okay,
But
so
you
you're
might
adding,
place
but
for the
what
correlations.
are you adding? You're adding just.
Yeah, so somehow you see you have.
So you're going a little bit beyond Euler.
Yeah, well, it's still completely it goes a bit beyond, but it's completely determined by the Euler equation itself.
Yeah.
It's kind of the sound mode and all that. But the effect it's smaller. It's not just the average of the curve. It's some small correlation. And in the end, the effect has in conflict with the physics. Okay, but at the level of correlation, it's just that. So you have to even put a time there. So LT1 and say LT2. And so these things, large L, they are non-zero. I can calculate them, and they depend on time. To start with something that is uncorrelated, then it gets more correlated with time. And so,
Nice.
and there's some
And so-
equations for
and in
that.
some sense, is one way of saying it, with Euler, you assume some independence.
Yes, and that is not true anymore as time goes,
And
exactly.
that's not stable.
Correct.
It generates,
same, yeah.
it generates correlations.
Yes.
You've made an assumption, there's no correlations in deriving the
Yeah,
Euler.
yeah.
But the
But-
Euler will generate
Yes,
correlations.
exactly.
And so
In
it,
fact, the
so
very.
it kills itself.
It kills itself. Yes, the derivation
But
of
is that,
that I presented is actually
you
not
say it's
correct.
not reversible, or is it more,
Why?
it's not self-consistent?
So,
In some sense,
yeah,
is
so.
what you're saying. That's what you're saying.
One thing I'm saying is that the derivation I provided is not self-consistent, that's correct,
Yeah.
but still works, right? So
I think you should.
Can I start?
Yeah.
Okay, good, yeah. Good, thank you for joining after the coffee break. For a begin, I'm very grateful to the organizers for putting together this workshops. It's been so far a very great experience with very good talks, very interesting discussions. I'm based not in the US, I'm based in Sweden. If you're interested where this is here in Gothenburg on the west coast of Sweden. And I want to use this talk to discuss transport in Fermi liquids. You might think that everything that there is to know in these Fermi liquids is understood by now, but I want to convince you that there are some interesting novel effects that are so far been overlooked or not completely understood, or that remain to be understood, for example, in the form of such long-lived excitations that might impact hydrodynamic behavior. But before I start, I want to nope. Acknowledge my my collaborators here. So in order of appearance, the work I'm presenting is based on a collaboration with Ulf Grahn and Eric Knudsen, who is a PhD student at Chalmers in Gothenburg. In the second part, I'm talking about collective excitation system. That's work in collaboration with Shankar Dasama. And the last part, I will refer to work with Habib Rostami from Bath in the UK, and also Jeff Markey, who is based in Trento in northern Italy. Yeah? Okay, so I have a few introductory slides. I will talk about transport in Fermi liquids. And the basic picture of transport that we have is based on a quasi-particle picture where we explain, for example, the current passing the resistance in the metal by having these quasi-electrons that are accelerated, move through wire. And then there's a dissipative process by which this current is braked. So these quasi-electrons bump into impurities or phonons or device constriction, which relaxes the current. And that is the microscopic underpinning of Ohm's law. That is something that we can, yeah.
It seems like that little black box is blocking your thing. You want to draw it that's on the other computer.
This one here.
Yeah.
Let me see. Does this? Yes, perfect. Yeah, and that connects something that we measure, like the resistance to an intrinsic scattering rate of these quasi-electrons with some impurities or phonons over them. And typically, as we vary the device parameters, such as temperature, we can access different regimes in which different relaxation mechanisms are dominant. So this is the sketch of the resistivity of such a system at low temperatures. This resistivity is set by impurity scattering. So that's the density of impurities that plays a role. That's then roughly temperature independent. As we increase the temperature, we go over to a regime where phonons start to proliferate, and the scattering rate, that's the equipartition theorem, starts to increase proportional with temperature. And the question I'm interested in is, how do electron-electron scattering affect these properties? So at which point can we say that interactions between the quasi-particles themselves, for example, through a screen-Coulomb interaction, become important. And it's a famous result in Fermi liquid theory that this rate of scattering is strongly suppressed by Pauli blocking. Yeah? So an electron will not interact with any other electron in the system, but is constrained by the quantum statistics, and this rate will increase with the, or is suppressed with the square of temperature at low temperature. Yeah? And the increase, so this increases with temperature, but the increase is very slow because it's suppressed by a factor of the Fermi temperature, which in conventional metals is extremely high. Yeah? The way out is, so if we look at systems with very low doping, this increase can be sufficient so that with Fermi temperature on the order of, say, 100 Kelvin, so I'm having in mind two-dimensional systems like graphene or gallium arsenide, then this rate of electron scattering can dominate or can become important before other mechanisms like phonon scattering kick in, provided that these materials are produced in a very pure, clean fashion. And this is the regime. So in this case, we have an intermediate temperature regime in which the material properties are dominated by electron interaction. So where we overcome or dominate over impurity scattering before other mechanisms like phonon scattering kick in. And that's the regime that we're interested in. This is the transport regime that was proposed in the 60s. By Gershey, and were experimental evidence first in the mid-90s in the Molenkamp group and others, but this was not followed up. And this, the picture is then that as we increase the temperature, we cross over from such a collisionless regime, with respect to electron interactions, where with very infrequent electron interactions with a large mean free path, to a hydrodynamic regime where the electrons scatter very frequently and build up a hydrodynamic flow profile, which, for example, can show vortices or flows through constrictions on the pipe with properties that are governed by the fluid or the electron fluid viscosity. Yeah? And this regime is now experimentally explored, starting with 3 foundational experiments in 2016 and many more experiments since then. We have heard of some of them, for example, in Aaron's talk on Monday. So for example, the first one measures in graphene at finite electron or hole doping an intermediate temperature regime precisely between roughly 50 and 200 Kelvin. They observe anomalous signatures that they interpret in terms of vortex formations. This sees anomalous signatures of flow in a pipe, so small capillaries. And this one, as we've heard, measures anomalous signatures in heat transport, also at such an intermediate temperature regime. So that's the introduction. And what I'm interested in is to understand this process of relaxation on the microscopic level. So this is then a standard Fermi liquid picture, where we want to understand the time evolution of the quasi-particle distribution, the electron quasi-particle distribution. What I'm looking at is a simple parabolic conduction band, for example. And in equilibrium, this distribution is just a Fermi-Dirac form. So at low temperatures, this is just a fixed Fermi surface, which I indicate by this black ring. But at finite temperature, of course, this distribution will broaden. And at high temperatures, when we're in this strongly hydrodynamic regime, possibly we'll have something like a classical electron gas that's described by Boltzmann distribution. And I sketch a deviation from equilibrium, for example, induced by some external probe, a velocity profile, or some electric field by the screen plot. This can be a rigid deformation of the Fermi surface, can be some smoothing. And in Fermi liquid theory, we know exactly how to describe it. This is a kinetic picture that tells us the time evolution, where we have kinetic equation that consists of a streaming term that tells us the free phase space evolution of the individual quasi-particles. That's the bit where also external forces enter. So that's the part that deviates our distribution from equilibrium. And then there's a complicated part, the collisions that bring it back and relax this distribution back to the Fermi-Dirac. And I would like to describe this. Before I tackle the full thing, I want to analyze collisions here and convince you or prevent a simple argument why there's some novel effects in these systems. So what I will look at first is the behavior at low temperature, where we have a somewhat simplifying assumption that all the excitations are restricted to like close to the Fermi surface, in which case I can describe relaxation as an effective dynamics where I transport particles from one angle on the Fermi surface to another angle on the Fermi surface to relax. So, and I do this by two particle scattering. I fix two excitations at the Fermi surface, momentum P2 and P1, and I want to scatter them under a different angle to relax this distribution at low temperature. I have to do this under the constraint of total momentum conservation. That's the red arrow here. And you can immediately see that this simple argument will not help you to relax this. It will not move these momentum states to a different angle under the Fermi surface. You either stay the same or you exchange them. The only exception is if you have head-on collision. So if the two particles scatter with equal and opposite momenta, no? In which case you are free to rotate this pair under any angle. And this is indeed the mechanism that tells you, that gives you the quadratic Fermi liquid relaxation rate of these modes. So you have initial states in a sliver or annulus of width T over TF, final states in this annulus, and that gives rise to the quadratic temperature decay that I mentioned earlier. But you can already see that there is a caveat in this argument, because this mechanism affects opposite points on the Fermi surface equally. You have an excess of quasi-particles here and here. You transport them into a depletion that has to be at opposite points as well. So it's a parity symmetric effect, if you want. You want to expand this more formally. You can distinguish 3 separate modes. So on the one hand, 2 modes are special. These are 0 modes. By binary scattering, I will not be able to change the total particle number. So if I squeeze my Fermi surface, nothing will happen. Likewise, the total momentum will not be relaxed. And then I have these blue modes, right, with an equal number of peaks and valleys at opposite points. These relax according to the Fermi liquid scaling. These odd parity modes, however, cannot relax in this way, by the simple argument. And this was something that was more or less known or noted in the literature. Here, 2 earlier references before. And by this argument, it would simply have 0 relaxation rate. And this was picked up then by this very nice paper by Patrick Ledwith and Leonid Levitov, who considered small angle corrections to this. So the leading order correction to this result, and predicted that this odd parity mode should, at low temperature, decay with the 4th power of temperature. And what I want to present is in the following, is how this extends across the full interaction dominated temperature regime. So where we go from low temperature, where these types of arguments should be valid, to a higher temperature regime up to this non-degenerate classical gas, where we would expect that the Fermi surface vanishes, so the effect should also vanish. And this would be interesting, because if we fundamentally have at least 2 vastly separate relaxation timescales in our system, so this would be at low temperature T squared and T to 4 would be a vastly different timescale, then it could imply that this crossover from collisionness to hydrodynamic scaling would be very different. It means that at low temperature, any deformation in my system would evolve freely. All of these modes would contribute. So it's a collisionless evolution. Then at finer temperature, these even parity modes have a sizable relaxation, and they would go from my system. And then I have a residual dynamics that is mixed between the dynamics of these 0 modes and these odd parity modes, potentially. This would give rise to novel interaction dominated hydrodynamic effect. Before that, at higher temperature, these modes go as well. And they cross over to standard hydrodynamics, which is the dynamics of these conserved densities. And so I will sketch first how this generalizes to finite temperature, make context with this prediction here. And then in the next step, I want to discuss some ways where this could possibly be observed in electron systems. Okay, and to that end, I have to look at the full collision indicator. What I discussed earlier was this pictographical description of relaxation on the Fermi surface. What we're interested in is the full expression here, which is this Fermi golden rule expression that describes the rate of relaxation of the quasi-particle distribution for one fixed momentum here due to binary scattering. That's a standard expression that we've all seen. So we sum over all the remaining phase space momenta that participate in scattering. There's a quantum mechanical scattering matrix element. Typically, this is taken to be a constant or a Coulomb interaction between the particles. We impose energy conservation and momentum conservation that we have discussed. And then we have a loss term where the initial states have to be occupied, and these Pauli blocking factors here that prevent scattering from taking place if the final state is occupied. That's the bit that restricts the dynamics at low temperatures to be close to the Fermi surface. And then there's a reverse gain term for the case where one of the final momenta is the initial momentum state that we get fixed. And typically the way that we deal with these systems is to not solve it, right? Usually when we describe kinetic equations, we often work with a relaxation time approximation, where we, for example, assume that every mode decays with exactly the same time scale, which of course goes counter to the simple argument that I just presented, and take this, for example, from a calculation of the self-energy. That's not appropriate here, so we want to do a bit better than that. And also at low temperature, we know how to handle this, dating back to works on liquid helium, so we can exploit this argument that I just presented, where we place all the excitations at the Fermi surface. But in principle, it's no extremely way so what mathematical structure such a collision integral has. Yeah, and this was worked out over 100 years ago by people like Boltzmann or Innsbruck or Chapman for the linearized collision integral. And the idea is that we expand the general distribution function around the Fermi-Dirac equilibrium, in which case this operator is a linear permission operator, very much like a Hamiltonian in quantum mechanics. Right? In this case, you can expand any deformation in terms of eigenmodes of this operator. So characteristic modes or deformations that decay with a particular eigenvalue, a particular relaxation, right? So this is a negative semi-definite operator. So these are negative eigenvalues. It always goes back to equilibrium. It doesn't blow up. Of course, different from quantum mechanics, the underlying equation is not a simple differential operator. You have a highly multidimensional integral equation. But numerically, it's possible to tackle this using some methods borrowed from high energy physics where people evaluate highly multi-loop Feynman diagrams. Similar methods can be applied to this. Yeah. And also, like in quantum mechanics, of course, we have the freedom to expand these eigenmodes in an angular index. And if I have a circular Fermi surface, I can expand this in precisely these angular harmonics. So I have a residual function that can have a radial dependence with some nodal structure. Yeah? So higher eigenvalues typically have higher nodes, as in quantum mechanics. And here I indicate the symmetry of the deformations for the low temperature case. But of course, at high temperature, this will not be a strict Fermi surface, and this is more to indicate the symmetry. Yeah? If you do this calculation, you get something like that. So this is an example of a spectrum or relaxation spectrum of such an electron gas at high temperature. So here I put myself at a temperature much higher than the Fermi temperature, where there is no Pauli blocking effect. No? So what I color in, there are these gray modes corresponding to these modes. In this channel, there are 0 modes. Yeah? So here there are 2 modes that are 0, so at negative infinity, they correspond to change in particle number and energy. And there's also 0 mode corresponding to this center of mass shift. Higher modes can have higher nodes, and they have finite relaxation time. These are, for example, nodes that contribute to heat transport in the system. And I color in also the odd and the even parity mode successively in different colors. I don't want to discuss this thermal gas spectrum in great detail. So the overall scale of all these is set by the Coulomb matrix element. So it will go up and down with temperature. But you can clearly see that there is no particular odd even effect, right? There's nothing that distinguishes the odd parity decay rates from the even parity decay rates. Yeah? This is as expected. You don't have a Fermi surface. It's a classical gas. Yeah? So if we repeat this calculation now at lower temperature, here, so I'm showing you 3 excitation spectrum. This is a little bit squeezed because I'm using the same Y scale so that you compare different plots. Here I dip just below TF. The effects of Pauli blocking start to become important. This is vastly as 1% of TF, and this is much below TF. You can already see, so here for this spectrum, the spacing depends on temperature. Yes.
It's like perfectly screened Coulomb.
In this case, so this is done with a screened Coulomb interaction.
Zero.
While the interaction potential I'm using here is this. You have a momentum transfer in your interaction, and you have a Thomas Fermi screening vector. The precise results don't depend too much on the type of interaction. You can tune this effect with interaction, but you can also repeat it with a constant interaction matrix element. You can add a frequency dependence. It makes a qualitative difference, but the basic effect that I sketched initially doesn't depend too much on this. That's the kinematics.
You just use a finite frequency to interaction kind of divergence. I mean, if you restrict the Fermi surface, but it's not perfectly screened, so it becomes like long range.
Yeah, but you can also have, yes, if you have an unscreened part, you can, that doesn't destroy this integral, so it's still finite.
The pictures were 2D, or the calculations 2D?
The calculations are for the 2D collision, yeah, 2D electron gas.
Is it qualitatively different in 3D?
I haven't done it. So the original argument that I showed is
defined in 3D.
Yes, but the same argument is not as restrictive, right? So the same center of mass sketching would be able to relax at least to a limited degree. It restricts your phase
So you
space.
think 2D is special?
That's the assumption. So I would expect that there is some difference in 3D, but I don't know if it's as pronounced.
Like, these spherical harmonics, there's another.
Yes,
degree of
okay, yeah, then
freedom.
you
So
would do that,
There
but-
would be one mode presumably that's special, but there's like a sea of other modes.
Yes, it would be a little, but that's a
Yeah.
perhaps
No,
technically.
no, really just asking about the odd even effect, whether
Yeah,
that strong odd even effect that survives in 3D.
one would have to check. yeah.
So you don't know
No,
for
no.
sure.
I would assume that something remains, but not as strong as in.
Sorry, I think I missed, what are
Yes.
the different? M is the angular momentum, but
Yeah.
what are the different traces?
The different traces.
Like at a given temperature, why do you have all these bands?
These are different relaxation modes. So you have the angular symmetry, that's the
Radiant modes.
exactly.
Oh, the radii, I see, you're doing.
You could plot the density of this deviation and you would have one that is no nodes, then the first one has one node, two nodes and so on. It's very much like
I
that.
got it. Mhm.
And of course, it continues indefinitely, but what we're interested in are the low energy or the ones that decay slowly because we assume them to be relevant for the long-term dynamics. huh? Anyway, so what you see, this is different temperature. Fermi Pauli blocking becomes increasingly important. As you dig below, it's almost similar to this thermal gas. Then you have some strong effect of Pauli blocking for the low M modes, and that increases. And of course, the striking effect that we're after are these modes here. Right? You see that there's an overall scale that is set by quadratic in temperature. If you want, you can eyeball this and see that it decays quadratically. But this band has a single mode in this odd parity sector, not in the even parity sector, that decays or drops much more rapidly. And you can check that this roughly, I will come back to this at the temperature scaling here. So overall, yes, as I said, you have a relaxation that decreases with Fermi liquid scaling. So there's a restriction of the phase space due to Pauli blocking. And then you have a successive long-lived set of these parity modes that decouple from the remaining spectrum. And the number of these modes you can actually check increases with temperature. So the lower M modes, they decouple earlier, and then at lower and lower temperature, more and more go away. That scales roughly with temperature, square root temperature, consistent with the prediction. Huh?
So the M dependence is M squared or, sorry,
This,
there's clearly curvature.
yes, wonderful, thank you. You can now fit the M dependence of this and get some intuition of this at low temperatures here. This is at extremely low temperature quadratic, or has a fairly slow M dependence, so it intervals between quadratic and linear or constant. This is very accurately M to the 4. Yeah? And that's also as predicted in the analytic works by Leonid Davidov. And you can convert this to dynamics and get some intuition into the behavior of these modes. Yeah? If you now sum up the even and the odd parity modes to get some time evolution effect, the Fokker-Planck dynamics of the angular dependence of the even and odd parity part of the distribution, where this would now be the angle under the Fermi surface, then this would be a diffusion equation if it's M3 or just exponential decay if it's constant. And this would give rise to a fourth power of this, so subdiffusive dynamics, where any perturbation on the Fermi surface, we're now at low temperatures, we have an effective angular dynamics, would decay spread very slowly, with 1 over the 1/4 in time. So just to illustrate this, and that's also consistent. So if you illustrate this, what I'm showing here, the green blob is a low temperature Fermi surface. We are here at this was a low temperature example. This is a Fermi surface, and I just dump a lot of quasi-particles on top of this. Yeah? And what you will see if I let this evolve in time is that the even parity component of this will, so that's the blue part here, will decay very rapidly, and the odd parity component very slowly. So we have a two-step relaxation here that looks like this. Yeah? So very quickly, the even parity modes have gone. The odd parity modes, so that's the even parity initial station, and with the slow dynamics of the remaining odd parity. And the idea is then, could this not affect the hydrodynamic behavior if in addition to the zero modes of the system, we have these additional odd parity modes that start to contribute at low temperature? Okay, and you can be more quantitative and discuss the temperature dependence as well. So by taking just the low, assuming that for an effective zero, the long-term dynamics will be determined by the lowest energy modes here. And what I do here is I take these modes, which is done for one temperature, plot them as a function of temperature here in the same plot. So this would be M3, M5, and so different harmonics, just to get the temperature scaling. So this is the high temperature regime. No? So we have no Pauli blocking. This is a constant interaction here. So these modes are pretty much the same. No? Then I go below TF. Pauli blocking becomes important. There's an overall decrease in this relaxation rate. The lifetime increases due to Pauli blocking. The even parity modes with very small logarithmic or even quadratic spread go down. This is the quadratic Fermi liquid scaling for comparison. So that's a double logarithmic Floating temperature. And then one by one, these odd parity modes here, this one would be this one here, drop down one by one. Yeah. And the hydrodynamic window typically is around TF in experiments. So this is 1 or 2 TF, so 100, 200 Kelvin, standing probably below down here, depending on how pure this is. Yeah? So you can put some bounds on it, so that at least this odd parity effect that you have enormously long-lived modes, maybe not in this asymptotic T4 scaling regime, they are expected to exist in these, in a simple electron use. Yeah?
Up to TF, it's a collision.
Up to TF, it's no, this is all collisions. Right? So this is just the collision of a thermal gas where every particle interacts with every other. So this would be proportional to the density, and then it doesn't increase any further. You can only interact with every other particle in the system. Yes.
So you talk about this quadratic and high order dependence on M, but is there like intuitive understanding why the lower the M, the decay is faster, or why actually it's slower?
Intuitive in the understanding why here this decay is slow. But the intuitive interpretation, as I said, here is connected to the subdiffusive motion, where you have an intuitive picture that at low temperature, the even parity modes have electrons undergoing individual diffusion on the Fermi surface, but this would be.
We just talk about the parity modes, right?
Yes.
So why M equals 1 is slower than M equals 3?
M equal 1 would be 0, but 3 is the slowest mode. In this picture, it's because it's a subdiffusive motion where you think of a correlated motion where one electron moves in lockstep with other electrons. That's the intuitive picture that is proposed for this at low temperature. And then this translates to a strong M dependence of this mode where the lowest symmetry modes has the longest lifetime. In these Fourier components, beyond this, I don't have a good intuition why a more corrugated Fermi surface would decay more slowly.
It's only there's some kind of a matrix element.
Oh yes.
You look at the collision.
Yeah. Okay. That's what you compute. Yes. Yeah. So that's
Collision involves 4 states on
Yeah.
the Fermi surface, and presumably it's like the dipole's conserved in some sense, and that's why it's m to the 4th.
yeah.
One particle scatters.
Yes.
In a way that
Yes. Exactly. That's the picture that.
dipole conserved.
Probably yes.
Quantum conserved.
Yes.
Presumably.
Yeah, but it's a nice effect. So you have a very simple system, right? This is not a special, anything special. You don't have a complicated Fermi surface. It's a box standard 2-dimensional electron gas. You can, of course, discuss more complicated Fermi surface, and I will do this. The interactions give a quantitative change, but the effect is really the Fermi statistic that enters here. And it's something that should, in principle, be well observed experiment. And of course, you can go into the details and take the spectrum, look at effects of interactions and so on. But what I want to do now is discuss various ways how this could show up experimentally. Yeah. Oh yes, okay. You can also make a logarithmic derivative and get the temperature scaling extremely accurately here. We get the 4th power of scaling, temperature scaling here at low temperature, and the Fermi liquid scaling for the even parity mode. Yeah? But how do we see it? Yeah? The basic problem is that we don't have a way of directly addressing these odd modes. Yeah? What we can do is we can induce some external perturbation to the system, and that will generate some response of my system. So if I go to the Fermi liquid equation, and this is the streaming term that we discussed, there's some external forcing that will induce some deviation from equilibrium. And then there's a collision integral, some relaxation mechanism that brings it back to equilibrium. Yeah? And what will happen in linear response is that there's some stationary state, so some drive and some relaxation. If you think back of the first slide where I showed the relaxation of the current that led to the resistance. And the susceptibilities or the response function it measures are typically proportional to some thermodynamic quantities times the relaxation rate of this particular deformation. And that will be a vast superposition of even and odd modes. That doesn't necessarily have to be one of these anomalously long modes. What we want is, of course, a response that is proportional to the fourth power of temperature, something that is the signature of these anomalously long-lived modes. And typically in linear response, we have a problem. If you think, for example, of the conductivity, where we induce an center of mass deformation of a Fermi surface by an electric field, then this doesn't relax at all. That's one of these zero modes. And it has a very low symmetry to boot. No? If I look at heat conductivity, the same. It's an energy current that can relax by binary collisions, but also we expect that this is one of these higher gray modes that I showed you, that decays with the square of temperature. If I look at shear viscosity, which is the central transport coefficient of these electron gases, again, I couple to an even parity mode. So I have this quadrupolar deformation. Again, that's Fermi liquid scaling. So you can miss this effect. No? What you can do instead, however, is you can look at the probe at a finite wave vector. That would be one way of circumventing this. For example, what is discussed is how the shear viscosity could behave in a small channel, where, for example, the channel width would set you a characteristic wavelength. Yeah? And then the collisionless regime would correspond to a very short wavelength. So we probe the system at very short length scales where collisions are not important yet. And then at long wavelengths, short wave vectors, we go over to a hydrodynamic regime where we have such a coarse-grained view of the system that all the modes should have decayed and only the hydrodynamic modes should contribute. And the conjecture would be that in between, we have some knob by adjusting the wavelengths, for example, in surface grating or the wavelength of a collective mode, that would allow us to see some signature of this. No? Yeah. And one way to do this, I mean, of course, you can go back and solve the full Fermi liquid equation with the full eigenmodes. In a simplified model, you would discuss some deformation that only assumes the lowest eigenvector of the collision integral. And in the simplest form, you assume a rigid deformation of the Fermi surface. This is something that would become accurate at low temperatures. At finite temperature, maybe this would be a bit suspect, but it's a very good start to get some intuition. So I expand the general deformation in terms of these rigid deformations, the lowest eigenmode, in which case the Fermi liquid equation take a very simple form. So this is the time derivative in the streaming term. This is the gamma here is the inverse decay rate of this, where I have essentially reduced the system to a tight binding model, where I have an on-site to energy term, which is the frequency, and some imaginary term that gives me the damping. And this is the external force term, something potentially with a low symmetry. And you can see if I have a finite wave vector in my response, then this couples in higher angular harmonics. So this would be a way for an even mode to talk to its neighboring odd mode dynamic. And you can solve this to your heart's content. So the way you solve this is not by just taking a giant matrix and inverting this. You can present this as a continued fraction expansion. And essentially for any assumption on the relaxation time, you get an exact numerical solution that's discussed in this paper. You can have a strict odd even ansatz for this, in which case you can even solve it analytically. And one thing we looked at here was the collective mode spectrum. For neutral Fermi liquid, we have collective modes that are sound modes. In a charged Fermi liquids, these sound modes become plus modes, at least for longitudinal modes. What I'm showing here is the crossover from collisionless to hydrodynamics as I change my wavelengths for a mode, a longitudinal mode, so one where the current is directed along its direction of propagation. What this thing is the characteristic Fermi surface deformation that's involved in such a mode. This is called the zero sound mode. It has a velocity slightly higher than the Fermi velocity, and you can see it's very similar to single quasi-particle excitation. You have a small excitation on top of your Fermi surface that's strongly localized. If I expand this in these harmonics that I showed you earlier, then of course all of these contribute, right? You have this at 0 and plus and minus 1. These are the hydrodynamic density and current modes. And then these are the blue and orange modes that I showed earlier. As I increase my wavelength of this mode, then what happens, I don't see a direct signature of the odd-even effect, but all of these even parity odd modes uniformly damp out. There's some subleading correction density, but what I end up in the hydrodynamic regime is this first sound, standard hydrodynamic sound, which involves an oscillation of density and current. So that's this. You can see it's only contributions in the density and current channel. And that's, of course, the lesson here. So this can be obscured. Sometimes when you have a response that involves even and odd parity modes, the even parity modes can win out, and we have no particular signature here. Yeah? One alternative, slightly more exotic here, are transverse sound modes. Yeah? So transverse mode would be one where the direction of the current is perpendicular to the direction of motion. These are a bit more exotic, but they were predicted for three-dimensional Fermi liquids already by Landau in his 46 paper. And they are now discussed also for two-dimensional Fermi liquids. Soderman, Villadiego, and others, they have.
tend to be overdamped.
Yes, there I come. This is in the strictly collisionless limit. This is a propagating mode. There's no damping. It involves this anti-symmetric superposition of these modes. Then as you increase the sketching, not the sketching and the wavelengths, then they damp out. You get diffusive modes.
I guess what I remember is that for zero sound, as long as F naught is repulsive,
Yes,
you get it.
you need a
but
Fermi liquid parameter that is above a certain
which
threshold.
Oh, I see. So for small Fermi liquid parameter zero, I just remember that they're generically overdamped.
Yeah, Gina, if you don't have any Fermi liquid parameter, then they're
Both
overdamped.
parameters.
Yes, there's a threshold. Yes. Yeah, so that would be above that threshold. And then as you increase the wavelength, you get diffusive mode. So one sound mode goes to two diffusion modes. And you can see that there is a signature, right? So you have indeed this superposition of odd modes. So there's a current mode and the 3 mode to 5 mode, whereas the even modes are completely gone from the system. No? Of course, this has
At that point, is it underdamped or overdamped?
Sorry?
Is that, at that point, is this?
That's
model-
over then, so that's a
It's over
diffusion,
then,
yeah,
yeah.
so that would be, yes, so that would be the characteristic that would then decay. Yes, so that would be one way, and there's a lot of work in this direction. How am I doing for time? Do I have 5, 10?
Fine.
Okay, good.
I don't know, sure.
Okay, good. Yeah, so sometimes the problem is that sometimes, in many cases, the coupling to even parity modes can obscure the subtle effect, and then this wins over and we don't see. And that might be one of the reasons why we haven't observed this yet. No? So that motivated us to think a little bit differently. So what if, instead of looking at the finite wave vector response that couples different modes to each other, if one could have a response that exploits the symmetry of the system, that I have only the odd parity modes, but not the even parity response. No? And to that end, what I presented before is only for the circular Fermi surface. So that's a simple system, but the basic argument that I have a parity, a distinction parity between relaxation time, that applies whenever I have a parity symmetric Fermi surface. So it could be something more complicated than circular. As long as I invert my momentum, I end up at the Fermi surface again. I should have this odd even effect. Yeah? And the symmetry that buys me this is time reversal invariance. Yeah? And I can break another symmetry in my system, which is inversion symmetry. Yeah? In that case, if I break inversion symmetry, I need to modify the Fermi liquid description to include topological terms in the form of this Berry curvature. Yeah? So that's a vector for this two-dimensional system that points out of plane. And this Berry curvature has odd parity by symmetry. Yeah, so the idea is if I could couple or engineer some response that couples to this odd parity Berry curvature, then I would be sensitive only to odd parity deformations, which then should decay with a much longer lifetime. Yeah, that's the idea. And what we had in mind, for example, as an example, is this topological insulator surface state. Yeah, this is like in bismuth telluride, where I have a surface state that are described by Dirac cones. And here I showed 3 contour lines, which are the Fermi surface at increasing doping. So it starts off with a circular Fermi surface, so the one that we have discussed, and then there's increasingly stronger hexagonal deformation. Yeah? And the density plot here is the Berry curvature computed for this. So red would be out of plane, blue would be in plane. And you can see that there's this tetragonal symmetry. Yeah? And Fermi liquid theory gets modified. In the presence of such a Berry curvature and an electric field, you can think of this as something like a magnetic field in momentum space. So the velocity gets an anomalous push, a transverse push. This is encoded in this anomalous velocity term if there's an electric field in plane. Okay. Yes, yeah. So that would have to be in plane, so you accelerate your electrons, and then there's this Berry curvature out of plane. You have a right-hand rule that pushes this in the direction transverse to the velocity. Yeah? Yeah, and of course, this expectation here, for example, if you look at the electric current, that would vanish. No? In equilibrium, this is an odd parity term that has odd parity, but the Fermi-Dirac distribution has even parity. Yeah, so this is not a Hall effect or an anomalous Hall effect, but this would contribute. But it's known that you can look beyond linear response and discuss what happens if you induce a deformation of your Fermi surface, which might have an odd parity component. For example, this is done, this was proposed by Suderman and Fu and Joel Moore before that, that you could deform or induce a current in the system by applying an electric field, which would then conspire with this term to generate a transverse current response at second order. Yeah, look at this transverse current at second order in the electric field with some coefficient that encodes then properties of the Berry curvature and Fermi surface. That's known as the Berry curvature dipole in this literature. And some characteristic lifetime that describes the relaxation of this induced mode back to equilibrium. No? And this is something that's been proposed. It's a non-story, has been measured in transition metal dicotyledons and also in these things. So this involves a time-dependent electric field. There's a story about frequency doubling of the current, and this has been precisely for these types of systems. No? So we want to do something similar, but the caveat here is that, of course, here I induce a simple current response, which decays by impurity scattering at most. I can't go back by binary collisions. So I need to, and so this would not be a lifetime that would be sensitive to this odd parity enhanced rate. But what we did was then to think if we have on top of this electric field a thermal response, I can generate a deformation of my Fermi surface in combination with this anomalous velocity term that has a higher parity symmetry, which would then enter with a static gradient of the temperature and an electric field. And if I neglect the Berry curvature, the thermal response of a system in response to temperature gradient takes this form, which is still the Fermi liquid, standard Fermi liquid description that is proportional to this heat capacity term, which involves this temperature derivative of the kinetic energy. Yeah? And if I naively now replace this by the not just the band velocity, but the band velocity plus this new anomalous term, then I generate a response. So first I have a deformation of my Fermi surface that follows this induced Berry curvature symmetry, which is an odd parity mode and decays slowly. And that gets picked up by the Berry curvature term of this of the anomalous current. So this would be then a response that is proportional to this anomalous lifetime by symmetry, and it's proportional to this something that depends on the Berry curvature squared. And if we do this for setup where we have circular light, so this would be a second order in the electric field, one to generate the perturbation, one to in the anomalous current, then this would be a transverse current at second order in the field with a static gradient that depends, is proportional to this and has anomalous long lifetime. We pick up a similar current as well if we look at linearly polarized light, where we have this induced higher order deformation in combination with the band velocity term, which gives us a longitudinal current. Okay, and I think I'm right on time. So this is the summary. Then there's a wonderful prediction that simple Fermi liquids have anomalously large lifetimes, or that they're odd parity modes that have a strongly enhanced lifetime. It's interesting to describe, and what we have done is to quantify their effect not just at low temperatures, but across the full interaction-dominated window, which is the one that's experimentally relevant. We found that they should exist, and I discussed two ways in which they could potentially be observed, in the form of collective mode spectrum, and then in the form of a nonlinear, so which has a finite wave vector response that is sensitive to this odd-even effect, and a nonlinear electrothermal current in the system. With this, these are some of the reference that this is based on. Again, the collaborators, and thank you very much for the attention. Yes.
So in this last thing you
This one.
gave, apparently this is producing a m=3 distortion of the Fermi surface.
Yes. Well,
But you didn't manage to draw that. I just wondered if there's a way to see that.
no, I didn't draw. Yes, so the Fermi liquid equation. If I can go back a few slides to the.
You're driving it with what is
Yes.
first order in the temperature gradient.
There's a term that involves the Fermi I dot and some position derivative of this. This is the bit that would be sensitive to the terminal gradient, if I have some terminal gradient temperature. And this would induce that's a band velocity term. And it has this term that is proportional to the Berry curvature. Huh? And if I then follow, there is no finite wave vector. So the symmetry of the Fermi surface deformation, which would be gotten at by converting the collision integral, then follows the symmetry of the Berry curvature. Yes, in this picture. So if this has this, at least if we have a circular Fermi surface that has this third order deformation, then it's such a deformation that we would generate. And that's something that we wouldn't get. That's why I need the terminal gradient, because otherwise I only have a term that's the electric force that would generate such a response. So that's the idea. The experimental challenge is, of course, to measure terminal response, as we have heard in previous. But the advantage is that here's something, at least on principle, you'd expect it couples only to these odd parity modes by symmetry. Yeah. Okay, let me go back. Any other?
So,
Yeah.
whilst we're setting up the next book, I have a general sort of a question. If I take a snapshot of a fermion material.
Yeah.
With ARPAS, for instance,
Yeah.
I can tell the shape of the Fermi surface, right?
Yes.
So, the way I learn zero sum modes is that you take that thing and you write it in the real space, and the zero sum has this very unusual egg-shaped deformation, and you drew the
That's
J11, right? And so the idea is then that suppose I set up a standing wave
Mhm.
on a big piece of metal with some well-defined lambda. And I think what these lifetimes that are M-dependent mean that you can locally look at it. In principle, if I have a space, I have a big patch of a sample where I can just look at it.
Mhm.
You will see that the local Fermi surface, if it's sufficiently strong enough,
If you do-
like, you can actually look at it, right, in principle. Right?
If you strongly
That's why I
deform-
learned it. You can just locally look at the Fermi surface.
Okay.
Is this something that's, because I know they have spatially resolved ARPAS. I don't know.
Possibly.
The magnitude has to be large enough.
Probably, yeah, that's probably the problem.
What this basically says is that.
Can your effect be bigger than the thermal broadening?
Well, of course, you have it exists if you're beyond this low temperature limit. Not sure what,
Well, yeah, I guess I imagine the
So you're
standing.
making an M=3 deformation.
yes, so,
With some amplitude.
Right.
yes, yeah, so that would be
And
determined
that
by this.
amplitude get big compared to the thermal broadening.
Well, that's dependent by the electric field, right? So I guess you take a stronger laser, in theory,
Right.
take a
The
stronger laser.
calculation, would it remain valid?
That would be well, yeah, that's a nonlinear response, and maybe you get higher orders on top of this. That might, of course, be.
Yeah, I guess we don't need to have steady states in your
Yes,
last slide,
exactly.
which I already started with on that. Sorry. So here, that's actually a
This one.
steady state, right?
Yeah, this is a time-dependent electric field.
Okay.
What we had in mind was light or some high frequency response. So if in this nonlinear response, usually you talk about a rectified current where you have a static response in response to frequency dependent field and a frequency doubled response.
Nice.
So certainly if you think of light induced currents, then it has to be frequency independent, quite heavily so. Yeah. But there are many, so
Okay.
hasn't.
Yeah, no,
been
but
seen
that's the question. What's the amplitude? Because we want some signal.
Yeah.
Okay.
Okay.
Okay. No, that's all right. I'm just killing time because next speakers.
Yeah, Leonid is probably stepped out.
Oh, okay.
Yeah, so I'm from the optic community, so
Yeah.
my question here is what frequencies of light are we looking at here? So it's infrared, visible.
You haven't thought that, so this would be, I don't think you would need any other setup than for, frequency doubling experiments that they have in this Telluride or.
I think as we were discussing, right, you probably want the light to be pretty intense, right?
That's the big difference.
So then is there a way to actually include the thermal effect of the light as well?
You can, so you have some heating, it's, right, you can quantify it. We haven't done it, but on the heating can be.
Actually, question is this, so do you, even without the Becker Wacher case, if you shine just circularly polarized lights, won't you be able to observe this in the previous system?
Well, but it would not give you a transverse current. You want to have the transverse be distinguished from the standard trouble. Direct way of distinguishing from the longitudinal. You might get a response in combination with that.
Right.
Well,
Because the circularly, you can change the polarization direction and then.
yeah, so, but it might actually vanish. I have to check, because it's a cross-term contribution. Yes.
Okay, so thanks.
Okay, thanks. Okay.
There he is. I think you're all set up. It's just.
Oh, okay,
so you
yeah,
have to
yeah,
just share
sure,
the screen.
sure. Okay, good. No, no.
I think these are not commuting. Sure. Okay, so our next speaker is Leonard Levtov from MIT. He's going to talk about the linear conductance from Hegel.
All right, great. Yeah. Yeah. Thank you, the organizers, for putting this together and inviting me, letting me to describe what I'm working on. Want to talk about two things. I mean, I looked at the participants and interests are so diverse that I thought telling two different things may be a good plan. Let me see how time goes. So I will start with, I'll start with the work that is related to previous talk and not the same, but related, and then talk about something that will be for interest for people who like integrability, and that will be Hofstadter quasicrystals. Right, so let me talk about electron hydrodynamics. Yeah, so so different people have different reasons for being interested in electron hydrodynamics, and for, you know, including myself. So let me give a reason, one reason to motivate the discussion for this talk. So hydrodynamics of electrons is known to show a counterintuitive behavior, which is carrier collisions, when they become more intense, they help conduction rather than impede conduction, they help conduction. And so that's surprising. It's been predicted a long time ago by Guruji, and then, you know, people tried to realize it, and then recently they succeeded, and we'll talk about all of that. But it is a surprising prediction, and you can compare it to other surprising behaviors of the same kind, like motional narrowing in spin resonance, famous work by Van Vleck and Anderson, where, you know, noise and randomness help make spin resonance more coherent, or the decay effect and collision narrowing in optics enhancing optical coherence. So what we're dealing with in electron hydrodynamics is of a similar nature, and because of that, I think it's interesting. And then, of course, I don't want to spend too much time on that. I mean, one manifestation of collisions enhancing, assisting conduction is that conductance is observed to be growing with temperature, or resistance is observed to be decreasing with temperature. And so that's something that, you know, when you see that, as all solid state physics people know, it's usually a signature of something interesting happening in the system. And again, there are examples from previous years that we can mention, like it is the case for Condor scattering or weak localization. In this case, negative resistance temperature dependence reflects some peculiar dynamics in the system, spin dynamics, or quantum coherence being, you know, being suppressed by temperature. So this talk will deal with a similar behavior in two-dimensional electron gases, which has been predicted and observed, and we'll talk about it in detail. In particular, it turns out that the temperature dependence is just what I said, that resistance dropping with temperature. And the surprising thing is that it's dropping in a non-Fermi liquid way. I mean, you would expect naively a t-square dependence based on Landau quasi-particle lifetime argument, but in practice, it's linear in T, and so that again, linear in T dependence in transport usually raises interest because it's something that non-Fermi liquids are supposed to show. So here there is a linear temperature dependence over a different origin that, or maybe the same origin, we don't know, but it's observed. It's, you know, and I think we understand it, and I will explain why, explain how, and we'll deal with trying to explain it. So the whole thing started maybe about 10 years ago when people trying to see this hydrodynamic effect, negative temperature dependence, and not so successfully, and then it was realized in this paper, joint work with Grisha, that it is beneficial to change geometry to constriction rather than doing experiments in the whole bar or in a wire. Switch to constriction. The reason is that it allows to avoid issues related to phonons interfering or disorder interfering. But from, for this audience, maybe a good way to describe it is to say that when you make make a constriction geometry, it allows you to measure, measure conductivity with a fixed wave number. Take conductivity, non-local conductivity, and measure it not, not a response due to uniform field, but a response due to field concentrated in some spatial region characterized by wave number, and the wave number will be defined by the size of the constriction. And so this was a prediction, and that after we published the paper, immediately after that, there was an experimental realization in Manchester, and they observed that yes, indeed, resistivity and constriction in graphene drops a function of temperature, and conductance grows, and then continues up to 100 Kelvin, and then beyond 100 Kelvin, there is a phonons take over, and you see a different sign of temperature dependence. But up to 100 Kelvin, it's in this hydra regime. And then later, there have been realizations in gallium arsenide electron gases and nice experiments at ETH and Klaus Ensslin group. So now I think this is well established, and everyone agrees that there is a hydrodynamic behavior here. What is surprising is that if you look at the temperature dependence here, it is linear. It is linear at low enough temperatures, and from simple Fermi liquid estimates, you would expect a T-square dependence, and so that's something that puzzled us, and that's what we would like to understand. So that's my yeah. So that's kind of the topic I want to talk about. I don't want to talk about the positive resistivity part, negative conductance part, because that would allow accounting for phonons and for other effects. So that's future work. So now we're going to focus only on the low temperature part, which is not so low temperature in graphene, from 0 to 100 Kelvin, right? Okay, so that's I mean, please stop me and ask any questions if there are any questions at this point. Happy to. Yeah.
A bit confused because you're saying the hydrodynamic regime is at 100K, and then the conductance goes. It looks like it's linear 0 to 5 Kelvin on that plot.
Yeah, that's because in graphene and in gallium arsenide, the range of validity. Yeah, sorry, I forgot to. Apologies. So first of all, this is resistivity. Resistivity drops with temperature. This conductance, it goes up with temperature. These are different systems. This is graphene, and that's gallium arsenide. Electron phonon interaction is very different, and various other, and the band dispersion is different. These are Dirac electrons. These are parabolic dispersion electrons. So that's why. Then the other thing I forgot to say is that in both cases, it is known, not only sign of temperature dependence, but also that in the hydrodynamic regime, conductivity is very high. In case someone wonders, how does it compare to conductance quantum, h of v square? It's much greater, as you can see from the scale. So nothing to do with weak localization, if you wonder. And furthermore, it exceeds the Landauer threshold, the fundamental conductance limit set by ballistic transport. And so here in Manchester experiment, that's the horizontal line shows the Landauer ballistic conductance, and in this ETH experiment, they show the excess conductance above the quantized value. So they go on a plateau where conductance is quantized at 0 temperature, and then raise temperature. Normally, you'd expect conductance to go down. Here, you see it go up, and that's the excess part. That
Last question: what are the 0.5, 1, and 2? The three different colors on the left.
Oh, they're cheating. I mean, they're checking that it's not T-square. They're checking. So the purple line, the parabolic.
No, not that one. On the left.
Oh, these are constrictions of
This is N several units of centimeter to the -2. That's just the
Sorry.
density.
Yeah.
Doping density.
So that's the gate.
These gates.
Okay.
Okay.
Yeah, several different carrier densities. So there is a
Yeah.
particular constriction geometry, and then they vary in carrier densities, and showing results for different carrier densities. I think we also have results for different constriction widths. That's carry density. Okay, good. So let's go to theory. So theory that we're going to describe relies on something that has been mentioned in previous talk. So if you have a two-dimensional Fermi gas and collisions in two-dimensional Fermi gas, then it is, it's been looked at by many people in the past, and I'm going to skip literature review in the interest of time, but one thing that has been overlooked and I think was brought up in these papers is that there are energy excitations in the Fermi gas, which you can think about as modulations of Fermi surface that have a very different scale for their relaxation, depending on their parity. And the reason for that is basically the kinematics of two-body collisions, and I think that was covered in previous talk. Thank you very much, Johannes, describing that. And so it turns out that the even parity modulations relax at the normal Landau Fermi liquid rate, t square, and the odd parity modulations relax much slower, and how much slower, that's what these papers dealt with. So it turns out that there are these many long-lived excitations in addition to the ones which are protected by microscopic conservation laws. There are many of these odd parity excitations that have abnormally long lifetimes that are t square over t Fermi slower than the normal Fermi liquid time scales, pardon me. Normal Fermi liquid time scale. So it's the same factor by which they're slower than the Landau Fermi liquid lifetimes are longer than the naive estimates, not accounting for Paul exclusion, for fermion exclusion, right? And so these are slow modes, and they are slow as this says. And so from that point of view, the hydrodynamics in this case is interesting. It's not really described by velocity field, it's described by Fermi surface shape evolving in space and time. And so from that point of view, it kind of connects to the active fluids part of this workshop. And I'm not joking. I mean, one can think of it's not part of this work, but it will be a future work. Come back in a year. You can excite some of these modes, and then you will see a Fermi liquid behavior in which Fermi surface vibrates and it flows. Yeah. Next paper. So anyway, so these are 2017 papers. Now recently, and I forgot to say that in this papers, the behavior was derived in a semi-quantitative way, kind of hand waving. I mean, we trusted it, we published it. Turned out that it's right, but there was no definitive microscopic proof, and the microscopic proof came relatively recently. Sergei Krykhin did direct simulation using two-body collision integral, and there is this is a similar work to what Johannes described in a previous talk. So maybe let me skip that, just show the results that indeed you see diagonalizing a linearized collision operator. You see that different harmonics, even an odd, have very different eigenvalues, and the even ones are t square scaling with temperature. The odd ones are something like t to the fourth, and furthermore, there is a hierarchy. I mean, different angular harmonics with different angular momenta, they have dependence on m, which is basically m square, and then the harmonics, the even harmonics don't do much as a function of angular momentum, and so we are going to focus on the odd ones because they're the ones of interest, and so there is an interesting. So once you understand that there are these excitations with very different lifetimes, and that there is a very large family of excitations with abnormally long lifetimes that is growing in number when temperature becomes lower, simply because, imagine how t square, t to the fourth scales with t square. Then you see that at low temperatures, you want to understand hydrodynamics, which is governed by all of these modes together, and they're coupled. They're coupled. They're coupled by streaming term, and so you, in order to understand the hydrodynamic response, you want to understand their contribution to conductivity. And so contribution of these modes to conductivity can be handled very directly, and there are some nice exact results that I'm going to show on the slide. So first of all, as I said, we're interested in non-local conductivity because all these experimental probes that are now used to probe hydrodynamics involve probing conductivity at a certain wave number. So the quantity of interest is current response to electric field, which you think about as a non-local conductivity, would be conductivity as a function of a wave number if Fourier transform that equation. And then if you now start very generally saying that there are these relaxation rates for harmonics with different angular momentum, you can derive a general expression for conductivity, which generalizes a Drude formula that you see here. And so this formula would look conventional Drude-like if there was no this term, but that term is all that all that matters for us. So momentum relaxation rate I put here just for making it familiar, but I'm going to ignore it. So you get momentum relaxation due to disorder of phonons out. Then this quantity is a k-dependent quantity, which one can explain in various ways. But for my purpose, the convenient way to write it is to put it in the form of a continued fraction that depends on k, and it involves all relaxation rates for all harmonics, the odd ones, which are slow ones, and the even ones, which are fast ones. So all of them together. But then, of course, if you when you try to do analysis and evaluate it, you end up focusing on the odd ones, and then when you focus on the odd ones and look at this quantity, focusing on the odd ones, you find out that the non-local conductivity as a function of k has a linear temperature dependence, which is surprising because these rates, even and odd, as a function of temperature, they are t squared and t to the fourth, the previous work. From that, it's immediately clear that there is some non-perturbative going on, because by perturbation theory, you can't get linear.
Which is this linear dependence of this continuous fraction?
Yes. Next page. Yeah. Yeah. So you just plug in these quantities that I introduced here. So what is not? Yeah. So take these quantities, t squared. Sorry, use my mouse. You don't see my fingers. T squared and t to the fourth, put in the continued fraction, and when you do that, you derive analytically this behavior. So there is a linear t dependence, and the k dependence. That's for you, Grisha. Looks like Kolmogorov 5/3 scaling, accidental or not, probably accidental, but we can debate it at dinner. Yeah, but that's an analytic result, and no joking. No other question.
Yeah. So I see that you're writing the transverse production for the conductivity. Why are you ignoring things like bulk viscosity here? Or is that an assumption, or is that just coming out?
So transverse is because I'm interested in DC conductivity. So in DC conductivity, because of space charge, if you try to run, apply electric field to run current, the longitudinal conductivity will try to produce current, but then charge will pile up and can cancel it. So to avoid thinking about it in the first place, you can just focus on transverse conductivity. Longitudinal conductivity is easy to incorporate, but then, it won't do anything in the DC limit. It will be interesting collective excitations of finite frequency, but let's leave it out.
Your initial argument about non-Fermi liquid behavior, that applies to all Fermi systems, right?
Yeah.
So then where did the electron gap enter? Like sometimes connectivity is just E squared, so where do you?
So electron gas enters in a way that it introduces the degrees of freedom which are relevant for this hydrodynamics. I mean, Fermi gas, the way we learn about it in school, is just a Fermi C shape which is round, or maybe not so round if it is in a crystal. But then once you start thinking about dynamics in a two-dimensional electron gas, the Fermi surface vibrations turn out to be particularly important, and you want to think about these modulations time dynamics, and that's what we are doing here. Is that what you're asking?
Why would you conclude that everything that's non-Fermi liquid is part of it? Why would you always get? Okay.
So this is not a question about Fermi liquid versus non-Fermi liquid.
You have initially had an argument that one has this even on parity, so you do not expect to get exactly Fermi liquid behavior. Then I'm just asking, so something just.
Feature of Fermi liquid theory.
Yeah.
That is a feature of Fermi liquid theory, the odd even effect, right?
It is a feature of Fermi liquid
Yeah.
theory, but the prediction for conductivity is linear in T. If you show it to anyone, including yourself, and ask what's going on, is it a Fermi liquid, not Fermi liquid, then you know.
But I think.
But you're not leaving Fermi liquid theory.
I'm not leaving.
You're just
Right.
evaluating.
Well, okay, so we can.
Isn't that right?
It's a little bit terminological sounds to me, no?
Yeah,
It's like an
it's okay.
outside-
So maybe we should maybe say that there is this notion of non-Fermi liquid introduced by Phil Anderson, and there are many. As it turns out, there are many different kinds of non-Fermi liquids. There is Fermi liquid number one, non-Fermi liquid number two, and non-Fermi. Probably the reason, so people constantly argue about it. Probably the reason people argue is that it's not very good to define something by what it is not. Right, saying that it's non-Fermi liquid, I mean, not a good way to define it. Right, so there are many different kinds of non-Fermi liquid. If you can say that this is not that non-Fermi liquid, it's some other non-Fermi liquid. It's philosophical discussion. Let stop it.
So
Sorry.
just formally, I think, at least the way I learned it, school, maybe
Yeah.
different schools, different biases. You know, Fermi liquid fixed point is not interesting enough to describe conductivity. Conductivity is just infinite,
Yeah.
right? And so because you need.
So we are
perturb away.
talking about non-Fermi liquid effects, so that's not a non-interesting fixed point.
Right, no, but the point is that because the zeroth order, the fixed point does not have that information.
Yeah.
You have to be very careful in specifying how you move away, so you
Yeah.
move away. at
Yeah, I
Fermi
mean,
liquid
there will be,
state.
I mean, there will be in the few years, there will be a non-Fermi liquid version of it. I mean, there are already some preliminary results, but I mean, I don't think that was the question. Let me just move on. So it was yeah, time to wrap up.
Maybe this discussion was liquid is not really philosophical, but semantic. But maybe you can explain briefly, if it's possible, what do you mean by hydrodynamics?
well, that was the first talk this morning. It was an hour-long talk, very
It's
useful.
not hydrodynamics anyway.
Yeah.
I mean, let's not.
Let's,
I just want to see how you derive this.
yeah, anyway, so let me, so Grisha, that's for you. So the derivation, the result of the derivation was already shown on the previous page. You basically take this quantity and evaluate it. You can either do it numerically, or you can exploit the fact that in that region of interest at low temperatures, there are many relevant harmonics that play together. And so here you can take that coupled equations for different angular harmonics that briefly appeared in Johannes' talk. It's a difference equation that couples different harmonics by streaming term. And then in that low temperature regime, you can transform it from difference equation to a differential equation. And then we're doing it, you get a Bessel equation where m angular harmonic is treated in a continuous domain. And then you solve this Bessel equation, very elementary, all know how to do it. And then out of that get this asymptotic behavior. That's the result. I mean, there is a range of applicability where all of that works. I mean, if you take k's which are too small, then you will be in a conventional hydrodynamic domain because you will be perturbing and by very long wavelength perturbation. If you're going to k which is very large, then it will be ballistic response. So you want to be outside of that. Now, if you do numerics, you see both of these responses very clearly. You see that, so this is that non-local conductivity that I introduced, and if you plot it as a function of k, you see that there are three regimes, two conventional. There is a conventional hydrodynamics here, and then ballistic hydrodynamics here, and then there is this k to the 1/3. I scaled out the Navier-Stokes k² to make it clearer. K to the power 1/3 regime that shows up here, and it widens with temperature. So everything I told you is now confirmed. And the dashed line, by the way, shows what would happen if we would have ignored these odd parity modes in the first place. Then would have like the ordinary hydrodynamic behavior similar to the one we observe in helium-3. So helium-3 is a benchmark from a liquid. It's free from all of these complications because it's 3D, not 2D. And so these collinear scattering effects don't apply there. And there, I would do a similar calculation. I would find something like what the dashed line shows. There would be hydrodynamics governed by Landau collisions at long wavelength, and then ballistic behavior at short wavelength. And if someone would do the experiment, would see that. Yeah. Anyways, so I think we're done. So the conclusion is that there is a power law. There is a linear T dependence, call it Fermi liquid or not, your choice. And then there is a power law in K, and linear T dependence is what we're interested in because that agrees with experiments that I showed, which are published, and also with a few that are not published. I think this is now becoming widely acknowledged. And so there is this interesting hydrodynamics in this regime, which is governed by Fermi surface modulations, some of which are very slow, and they govern conductivity and transport in an unusual way.
So enhancement, let me just get the physics right. So enhancement of conductivity is because of backscattering, so it will really go back and forth rather than doing this one in 3D.
Okay, I mean, I don't want to talk about microscopics here because it's not. It will take us. I mean, I only try to do it, a very short version of it. So there is that picture as well. I don't want to get into that right now, but one way to understand it based on what we discussed today is that you have more than one hydrodynamic mode. There is velocity mode, which is hydrodynamic, but then when you go to lower temperatures, other odd parity modes also become hydrodynamic modes because these odd parity stations so long-lived that their perturbations move around over large distance before they relapse. And so these odd parity perturbations is ultimately what is driving it. And the lower the temperature, the more of them you get. So the number of these perturbations form some kind of a cascade in wave number, in angular momentum, or maybe also in wave number and angular momentum. I think that's very clear, and that's what we see here. That's what we see in this analysis. Form a cascade in angular momentum. And that, because they all coupled by streaming term, and so out of that cascade, you see some flow in M from low to high. So it's like a wave turbulence. Don't shake. Yeah, okay, so that's done. Now let's see how much. Do I have 10 minutes?
Yeah.
Okay. Good. So yeah, so then the other thing I wanted to talk about maybe very briefly is this paper that we published recently and explain the general background, Hofstadter quasicrystals. So what it is about how Landau levels are perturbed by quasi-periodic quasi-crystal potential. Do you see a potential which is a sum of several harmonics with some high order symmetry? It is well known that if you take Landau level and perturb it by periodic potential, it broadens into a fractal. Hofstadter problem that people are very familiar with here, and you know, so our question is what happens if you perturb it by quasi-periodic potential? And so maybe in the interest of time, I'll skip the introduction. So it's been widely studied, you know, what happens to electrons in periodic potential, then you get Bloch waves, what happens to electrons in magnetic field, you get Landau levels. And now the question is what happens if you take the combination of the two? Take the combination of the two, then there is a lot of literature on the topic. Many people were interested and contributed, but basically there are two main things to mention. So first of all, when you have Landau level perturbed by periodic potential, there is this Brown-Zach symmetry arising from magnetic translation. In periodic potential, there are translations by periods of your potential, and they don't commute in magnetic field. Their commutator involves a phase of the flux through period, and then for magnetic field values for which they do commute, or for which the flux is equal to a rational number. Then, if it's a rational number, then you can build a supercell. You can enlarge your periodicity and get a larger period unit cell for which the translations will commute. Then the problem will fall in a category described by Bloch theory, and then you expect, in this case, you expect Bloch states and ballistic transport for these special values of magnetic field. And for magnetic fields for where this doesn't happen, Landau level broadens into a fractal known as Hofstadter butterfly, and you know, has an interesting structure governed by number theory. At all rational feelings, you have Brown-Zach mini Bloch bands, and then at irrational numbers you see what is shown here. And this has been widely studied, and many interesting results have been derived. I mean, Thouless proved that it's a zero measure fractal, and Wigman solved it exactly in terms of beta and Zatz. And then there've been work on Chern classes, but I don't want to get into that discussion. So maybe just mention that there are also experimental realizations nowadays, and they're available in graphene. You take graphene electrons and then create a superlattice by putting graphene over HBN, which is nearly commensurate with graphene. Then you get a superlattice, and then you see spikes in conductivity associated with the Brown-Zach mini bands, and they're known as Brown-Zach oscillations. They are periodic they happen to be periodic in inverse magnetic field because if you take the rational values for that flux, it turns out that denominators matter more than the numerators, and so you see mostly periodic dependence due to P over Q and Q changing like 1, 2, 3, 4, 5, and P being 1. But then if you zoom in or go to change parameters, you start seeing some other peaks, and so that's this fractal structure appearing. But anyway, so there is experimental realization, and so I think that now this is all kind of under control. Now my problem is trying to generalize this to a quasi-periodic potential. So I take quasi-periodic potential, which is a sum of several cosine harmonics, and ask how that perturbs Landau level. Now that problem basically boils down to a Hamiltonian that you write down like so, where x and y are taken to be as non-commuting variables, with the commutator being I divided by magnetic field, fundamental constants. And so in this, that's my problem. Want to solve this Hamiltonian for in the simplest case for two Hofstadter cosine potentials rotated by 45 degrees, as shown here. And so what you find in this case is that the Brown-Zach symmetries don't apply, because now there are no matter what magnetic field, there are no periodicities that would encompass all your potentials. So seemingly everything we know from Brown and Zach fails. However, if you now look into that carefully, you discover that there is a new hidden symmetry that creates something very much like Brown-Zach mini Bloch mini bands, and they appear recurrently in some sequence on that parameter beta, which is inverse magnetic field, and at these values you see conductance spikes, but also you see something else. So let me show you what you see. So first of all, it's very easy to solve this problem numerically, because you just write down the Hamiltonian and then do the same thing you do for ordinary Hofstadter. You take this part, and then because x and y don't commute, you can rewrite cosine as a sum of two translation operators, and then you get the Harper's Hamiltonian on a square lattice. Now, if you have that Hofstadter rotated by 45 degrees, then you can take a square root 2, which appears over here, and then take some rational approximant to that, and continued fractions turn out to be quite useful here too, because they provide very good low denominator approximates that work very accurately. So you can pick any of these square root 2, and then if you replace it with a rational number, then you get a Harper's-like problem with long period hopping. And then you just take, it's one-dimensional, so it's almost as easy as ordinary Harper. Take that, diagonalize, and you see, of course, you do a sanity check. You check that you reproduce Hofstadter, ordinary Harper's, Hofstadter, Asbel, whatever you call it. And then you try it on the quasi-crystal. You see a very complex spectrum that has many. So you see a lot of intricate details in it, and we don't have time to discuss it. Also, we don't understand it at this point. What I want to show you is just one aspect of it, which we now understand. So if you take the spectrum over a long range of beta is inverse magnetic field, then it doesn't look very irregular. It looks locally, it looks pretty irregular. But if you step away, or if I can do it, just taking off my glasses and blur out the structure, then you start seeing some periodicity. And student noticed it, and he empirically found that this periodicity is described by these red lines that you show here, that you see here, and they go at a period which is 1/√2 smaller than the period in the Hofstadter case than this period, right? So it's not explained by Brown-Zach symmetry or anything like that, but you can confirm that that's true. You can take that picture and make sure that your eyes don't fool you. Can take a Fourier transform. If you take Fourier transform, you see main peak in the Fourier transform, that spectrum, that entire spectrum, comes at a wave number which is exactly 1/√2, and then also there are some high order peaks at other values, but that 1/√2 thing is definitely there. So there is this periodicity, strange periodicity that we don't expect based on magnetic translation symmetry, but it shows up. So the origin of it turns out to be somewhat unexpected. You can take these two. You can write the Hamiltonian, take the two Hofstadter parts rotated by 45 degrees, and then take their commutator with each other. If you take their commutator with each other and work it out using magnetic translation algebra, you find that these two parts, H1 and H2, they commute at special values of magnetic field, which are exactly the values I showed on the previous page. So there is a discrete set of points in magnetic field where some hidden symmetry emerges, and so that irrational period coincides with that periodicity, and so that clearly, indication that we're on the right track. And so this is basically all we know about it at the moment. I mean, clearly there are many other interesting questions here, but this is all we understand. Or maybe there's just one more thing which is unpublished, not published yet, but these mini Bloch mini bands, excuse me. So if you now take that problem and compute Thouless conductance, as a reminder, for those who haven't seen that, Thouless at some point introduced an ingenious way to test system for localization versus no localization by looking at the response of eigenvalues to quasi-periodic boundary conditions, and argue that when system has a strong response to quasi-periodic boundary conditions, there will be no localization. There will be extended states. And so if you take that and apply, so this shows Thouless conductance for Hofstadter, and so these red spikes that you see are so this is some response function like change in energy in response to quasi-periodic boundary condition, and you see that it's very strong at all rational values of beta. Beta is inverse magnetic field, and at high order denominators, this response is smaller. At low denominator, it's faster. So there is this hierarchy that you see here, that we understand based on Brown-Zach Bloch miniband formation. Now, in my case, it is kind of similar. You see these spikes in Thouless conductance at every. You see the spikes at every magic magnetic field. I mean, they are not the same. They are not the same amplitude. I mean, some of them are small, some of them are not so small. But at every magic magnetic field, you see a spike that can be small or not so small, but definitely it generalizes in this way. And so if you actually look at the actual wave functions, which is what we did, but I'm not showing it here because it's too messy, you do see that at these points, the Bloch wave functions become very much like ordinary plane waves, and if you detune from a magic magnetic field, they become like multi-scale, similar to what you see in the Hofstadter case at irrational filling. Okay, so that's all. Thank you for listening for extra. So what we see here is that there is a highly complex but nevertheless ordered spectrum, and we understand it as being due to hidden symmetry and Bloch-like states that I already mentioned, and Yeah, so clearly there are many questions for the future, understanding that phenomenon. In particular, what I'm intrigued by is the symmetry origin of it, because clearly there is some framework there that may exist, unless this is sheer accident and there is no deep explanation. But I think in other cases we know there is a symmetry framework when something like that happens. So that is missing at the moment. Thank you.
Thanks, Leonid, for representing all the words of the title of the conference. Turbulence, hydrodynamics, quantum. Okay.
Even active.
Yeah, that's active.
So suspicious.
Okay, so any questions?
Actually, so this square root of this is like irrational magnetic field kind of compensates for your fractality and gets just simple plane wave propagating.
Yeah, that's what you see numerically. Yeah. Yeah, I can show you.
Bizarre.
I can show you wave functions. They look like Bloch waves.
Like regarding the twist in between your two layers, you picked a very special angle of 45 degrees.
Yeah.
Right. And is that crucial to this like emergency you see in this? So if I pick some random angle that's irrational.
Yeah.
What happens?
The period will be not square root of 2.
Or does this entire structure just gets destroyed?
Yeah, no, I'm sure it will get, much of it will get destroyed. I mean, you can. So my interest was, basically because quasi-crystals are high symmetry structures where we expect extra symmetry to do something, and surprisingly, here it works. That extra symmetry is actually key for that effect. If you rotate by some angle, then this fact that two parts of the Hamiltonian commute, that breaks. But then your more general question, how it generalizes to arbitrary angles, that we don't know.
Right. So like if it was a nice angle at 30 degrees, we
Yeah.
still accept some.
Oh, 30 degrees, maybe there is something. So there are these quasi-crystals that are now studied with graphene, dodecagonal 12-fold symmetry quasi-crystals. So they are available, and we did calculation for them, and pretty much everything I said generalizes. But
Square root of 3 period?
That's in the same, no, different period. I mean, but that's in the same class because they're also high symmetry objects, and so you would expect that everything you learned for Hofstadter will apply.
You can make a smaller change than what he's proposing is you rotate it 45 degrees and then you just translate it by a little bit. You've got all of them. There is a center of 8-fold rotation.
Yeah.
Which there doesn't have to be. And I wonder if that's important. Did you think of that? Because you can have those two lattices and put them down so there is no center of 8-fold rotational symmetry.
Oh yeah, okay. You're asking about the role of phase and
phase.
Yeah. Okay. It wouldn't matter for what I talked about. It would probably matter for nothing.
So when you say the two things commute, that would be true.
That
if I
stands. Yeah.
translated them with respect to each other. That didn't have anything to do with mine.
Yeah. That stands. I mean, various details would change, but I think that one wouldn't.
Can I just, sorry, with the.
No.
So, sorry, I was distracted by Sharon's question. But the conclusion is that if you go away from 45 degrees, you don't know if the symmetry is preserved. Is that right?
No, I'm sure it doesn't. It's not preserved. But then maybe something else emerges instead.
But the other, I guess, obvious question is that if you if there's a semi-classical regime where you twist by a small angle, so that it's more like, is there a superlattice?
Don't know. Don't know.
Yeah, because there may be a way to.
But I don't think it's related. Maybe there's some other game one can play.
Okay. All right.
With Hofstadter, people played this game. I mean, Michael Wilkinson.
Exactly.
In particular. Yeah. So there may be a way to handle that.
Then you have some classics. Sort of
Yeah.
deform.
Yeah.
Sorry, technical question. Could this lattice be set on the torus, put on the torus? Can this lattice be put on the torus? No. No. But then what's a boundary condition? You know, all this stuff of business, the sentence is basically a function of boundary condition. So which boundary condition do you like to mention?
Yeah, so it's not so simple already in the Hofstadter case, because in the Hofstadter case, if you do, there is a paragraph in the paper that I flashed on the front page that discusses it, but in the Hofstadter case, you have to be careful about boundary conditions, because if you take the system certain size, then your values of magnetic field, which are related, which are allowed by periodicity, become constrained, and you have to be careful about not using, illegal values of magnetic field for a fixed system length. It becomes more stringent in this case because now you have two different periods. So you have to, when you pick your rational approximant, you have to be careful about constraints on magnetic field which are Harper-like, and also additional constraints because of your approximating the rational number by continued fraction. So there are constraints, and we take care of all of that.
But in practice, which boundary condition do you have?
So it's a 1D problem, like Harper's. It's a 1D. Yeah, so it's a 1D problem on the slow line that you obtain by taking that and then reducing it to 1D the same way you do with Harper. But then you get translations by incommensurate periods. They become commensurate but long period after you do this approximation, and then from that some constraints follow. You have to follow that through.
I have a question related. There is no Landau gauge like projection. So
Yeah, so this is done all in Landau gauge. Yeah.
Landau
Oh,
gauge.
yeah. But we do exactly what Harper did to derive his equation. Landau gauge, and then going from 2D problem to 1D Hawking model. So that they explain exactly the same way.
Because that term looks like if you're doing it in the symmetric gauge, the x plus y term.
Yeah, that doesn't lead
But it's all Landau.
doesn't lead anywhere.
Okay, so before lunch, we break for lunch, there are like a couple of announcements. So there is a public lecture in this room between 6 and 7 p.m. given by William Irvine for general audience, but William Irvine. So he's going to talk about turbulent blobs and weaving vortices, weaving knots. So, but there will be general audience, but then I don't know how many general audience will show up, but please show up. And then,
From 6 to 7.
From 6 to 7. And then the idea is to kind of around 7:30, we can walk to dinner somewhere. Like, and the precise location I will announce after lunch. So, but it will be nearby, somewhere walking distance in Koreatown or somewhere we can sit together and have dinner. So this will be the banquet equivalent of the conference. And okay, so now let's break for lunch. There's a computer there that is doing all the hard work. So you can just yeah. So you have to just log in.
I think he was saying that it's special.
So there is a go to
So I cannot use the stick I have.
No, you don't need. So we are not even connecting. Okay, fellow. Okay, welcome to the afternoon session. So our next speaker will be Dimitra Karabli from CUNY Lehman College.
Okay, thanks for the invitation to talk here. I'm afraid not much of hydrodynamics. I think I'll give a kind of an overview of our results, work we have been doing on and off for many years now on higher dimensional quantum Hall effect. And much of this work is with Paramesur and Nair, who is there. Now, when we started this, it was of purely theoretical interest, but we have been very pleasantly surprised by the fact that over the last few years, there are a number of groups that have experimentally realized higher dimensional quantum Hall effect, and I will say a few things later about that. So the conventional two-dimensional quantum Hall effect deals with non-relativistic electrons in the presence of strong magnetic field, and the hallmark of the effect is, of course, the quantization of the Hall conductivity. It's quantized in units of E²/8. Nu is the filling fraction, and it's integer for integer quantum Hall effect, and takes particular fractional values for fractional quantum Hall effect. It's very important, not just for experimental importance, but also a lot of interesting ideas. So what I'm going to do is I'm going to go over the basic features of two-dimensional quantum Hall effect and then see how these extend to higher dimensions. Okay, and in the whole talk, I will focus on integer quantum Hall effect, where I can assume no interactions among electrons, and also we can freeze the spin degree of freedom. So we deal with charged particles moving in a two-dimensional space in a strong magnetic field. So we have to solve the Landau problem. We know that the single particle spectrum decomposes into Landau levels, and which are separated by an energy gap of the order of the magnetic field. Each Landau level is degenerate, and in a particular gauge, the lowest Landau level wave functions are essentially holomorphic functions up to this exponential factor. Now, the many-body problem gives rise to the so-called quantum Hall droplets. The degeneracy of each Landau level is lifted when we have a confining potential. The particles try to localize around the minimum of the potential, but there is, because of exclusion principle, they form an incompressible droplet. So if we plot the profile of the density is constant inside, zero outside, and at large end, these droplets have a sharp boundary. So because of incompressibility, the low energy excitations concentrate on the boundary of this droplet. So this corresponds to transitions of outside electrons. So the excitations are essentially area-preserving boundary fluctuations, which can be described by collectively by one-dimensional chiral boson, and the action is of this form. Okay, now in the presence of electromagnetic fluctuations, we have also bulk dynamics. One can integrate out the fermions, and the bulk dynamics is described by a Chern-Simons action of this form. This captures the response of the system to electromagnetic fluctuations. Variation with respect to the gauge field gives a current of this form, and from here one can read the Hall conductivity, which is essentially nu/2π. Now, this action is not gauge invariant if there is a boundary, the system has a boundary, but on the other hand, on the boundary, we have a gauge chiral action, which is anomalous. So if we put the two together, the system is gauge invariant, anomaly cancels. Okay, what about other transport coefficients? For example, one question is, how does the system respond to stress and strain, metric fluctuations? So one has to calculate the stress tensor. So we have to couple the theory to gravity. And as far as I'm concerned, the first people who did that calculation in the context of quantum Hall effect with Abanov and Gromov back in 10 years ago. And after integrating out the fermions, they found that there is a bulk effective action, which in addition to the ADA term has now omega, which is omega is a spin connection and carries the metric fluctuations. And this index S essentially indicates which Landau level you are. So from here, one can derive the stress tensor, and the part that is proportional to G dot, where G is a metric, there is a coefficient here, which is a new transport coefficient, and this is the so-called Hall viscosity. And this calculation has been reproduced by other people using other methods. Okay, so these are the effects now that I would like to see how they generalize to higher dimensions. So the first attempt to extend quantum Hall effect on S4 was done by Hu and Zhang back in 2001. They introduced an SU2 magnetic field. And shortly after that, we generalized this to arbitrary even dimensions, even spatial dimensions, by formulating quantum Hall effect on complex projective spaces. And this introduces two new features. First of all is the higher dimensionality. There is a systematic way to introduce quantum Hall effect for every even spatial dimension. But also, as you will see, it introduces the possibility of having both abelian and non-abelian magnetic fields. Now, since then, a lot of people have extended quantum Hall effect in a variety of different spaces, but I will mainly focus on the work we have done in the context of CPK and deformations of that. Okay, so the simplest, of course, CP1 space is a sphere, and the quantum Hall effect on sphere was analyzed a long time ago by Haldane. So we wanted to have a magnetic field which is perpendicular to the sphere, and this is done by a magnetic monopole at the center of the sphere. Because the magnetic flux is quantized, there is an integer n, which is related to the magnetic field B, and the spectrum is given in terms of this integer in the following way. Now, S2, of course, can be locally parameterized by a holomorphic coordinate Z, complex coordinate Z, but we can also think of this space as a coset or group coset, SU2 mod U1, and in that case, we can parameterize the space in terms of this SU2 matrix G, which is given in terms of this complex coordinate Z. So thinking about this as a group coset, translations in this space correspond to right rotations such that G and G8 are identified if H is in U1, which is had to be cosseted out. So we define these right translation operators. The coset ones, R1 plus psi R2 and R1 minus R2, essentially correspond to holomorphic and anti-holomorphic covariant derivatives that move us into that manifold, into that space. And because the commutator of the covariant derivatives is related to the magnetic field we put, it turns out that this R3, the R3 rotation on the wave function takes a particular value, which is minus n over 2, which is essentially related to the magnetic field we introduced. Okay, so a complete basis for the wave functions on SU2 are given by the Wigner-D functions, where now this m prime takes a particular value, is fixed to minus n over 2. So that means that all the wave functions, the spectrum, the single particle spectrum, decomposes into discrete SU2 representations, which contain the state minus n over 2. But there are many such representations. So if this state, for example, is the lowest weight state, then this SU2 representation is the lowest Landau level. If this state is S steps away from the lowest weight state, this corresponds to the S Landau level. And now it's very easy to count the degeneracies within this Landau levels. So this is n+1, just from SU2 algebra. This is n+2s plus 1, and stuff like that. And further, one can look at the Hamiltonian. It's very easy to calculate the spectrum. These Landau levels are degenerate, and consecutive Landau levels they have an energy gap of proportional to n, which is proportional to the magnetic field. Okay, so now let's see how this generalizes to the CPK, which is a 2K dimensional space, and it's locally parameterized by K such complex coordinates. So these spaces have a so-called Fubini study metric of this form. And in fact, from there, by replacing the dots with a wedge product, we can construct also a Kähler-2 form. Again, these spaces can be thought of as group cosets. CPK is SUK plus 1 mod UK. And this is very important in our analysis because it gives a systematic way to construct a single particle spectrum. Now, because of this is UK now, we can have the possibility of both U1 and SUK magnetic fields. And as before, these correspond, they're degenerate Landau levels, they're separated by a gap, energy gap, which is proportional to the magnetic field, to the U1 magnetic field. And each Landau level forms an irreducible SUK plus 1 representation whose degeneration and energy is easy to calculate, very much analogous to what we saw for the sphere. So let me say a few more things about the single particle spectrum. Okay, so as before, the space can be parameterized now by a K plus 1 by K plus 1 matrix G. And there is a relation between this G and the complex coordinates that parameterize the space. Don't have to look at it. So there are the translations now correspond to right rotations again, such that G and GH, if H is UK, are identified. So in terms of these right translation operators, the UK ones, that they do not move us into the space, correspond to case transformations, while the coset ones combined into the complex combinations correspond to covariant derivatives. And because the commutator of the coset ones brings me back to RA, how the wave function transforms depends on what magnetic fields I choose for these RAs, or the UK transformations. Okay, so in this case, as I said, we have a choice. We can have either just a U1 magnetic field, such that the field strength is proportional to the Kähler-2 form. This is exactly what happened for the sphere, in the case of a sphere. But here there is a possibility also of having SUK magnetic fields, such that we choose the field strengths. Yes.
I can understand the last point. So I understand why, because you're taking the course of, you said UK, and those transformations are like H transformations.
Yes.
Then the covariant derivatives.
Well, the covariant derivatives move me in this space, so they correspond to the coset right transformations. But the commutator of the coset ones brings me back into UK. And this depends on the values of the magnetic fields I choose. I can have a U1 magnetic field, or I can have UK magnetic fields. And this fixes how the wave functions transform under the case transformations. Okay. Yes.
This is perhaps an naive question. On the slide before this, you mentioned that the wave functions are Europs of SUK plus 1, but shouldn't they be Europs of CPK? Not. I'm just confused because you modded out by UK.
No, it's the same thing like in the sphere. Each Landau level is an SU2 representation.
Right, but I mean,
the same thing here.
yeah, so then I would have thought it would be Europs of CPK, not like.
CPK is not a group.
Yeah. Oh. Sorry.
Okay,
I have a question as well.
yes.
There are these topological invariants, additional topological invariants in higher one. Like second channel.
Yes, yes, everything is here.
How do you see them?
Okay, so far I'm only looking at the single particle spectrum. Okay, but I can, for higher dimensional spaces, I have second Chern class and stuff like that. Maybe, yeah, I'll show you a little later, maybe. Okay, so similarly, the wave functions now form an SUK plus one representation where this state now has a fixed U1 charge, as in the case of the sphere, but also if I have SUK magnetic fields, it also transforms under a particular SUK representation. Okay, so for example, the U1 charge for this is of this form. It has to do with the normalization of the SUK generators. So for k equals 1, this is minus n/2 that we had before. But if I have SUK magnetic fields, they also can transform under a particular representation under SUK. Okay, so we can have lowest Landau levels. The lowest Landau level corresponds to the situation where this is the lowest weight state. And we can create higher Landau levels and stuff like that. So we know essentially the single particle spectrum. Okay, now I want to move away from that for the single particle spectrum and try to present a very general way to characterize the dynamics of the quantum Hall droplets. So let's say in general that we can have a quantum Hall effect on a compact space M, and we focus on the lowest Landau level that defines an n-dimensional Hilbert space. So I showed you earlier that in the presence of a confining potential, we have these incompressible quantum Hall droplets. And let's assume that out of the n states, k states are filled, and I start filling from the lowest energy and go up.
Are you making a droplet on a sphere?
Yeah, not on a sphere, on these big spaces now. And it can be of any dimension. I have in mind CPK spaces. Yes, but you can do also a sphere.
I shouldn't think of that as a sphere in higher dimensions.
Okay, yes, of course.
Type of sphere, right?
Yes,
You're not in a flat.
not in a flat.
Flat.
Yes, yes, yes. Okay, so the most general transformations that keep me within the lowest Landau level are unitary transformations, n by n matrices. So under time evolution, this rho 0 goes into this. So these U's, which are n by n unitary matrices, can be thought of as collective variables describing excitations within the lowest Landau level. So we want to write an action for this collective degrees of freedom. And the action is of this form, where this V is the analog, the matrix analog for the confining potential. This leads to the evolution, expected evolution equation for ρ. And this is essentially the cojoint orbit action, or the Kirillov action. So far, this is a matrix action. So there is no explicit dependence on properties of space on which quantum Hall effect is defined, whether Fermions are abelian or non-abelian, whatever. But now we would like to introduce the space-time information, and this is done in a way which is familiar in non-commutative field theories. So this is the original matrix action, and this is also equivalent to a non-commutative field theory in the following sense. So we replace the matrices up here with classical functions, which are the so-called symbols corresponding to this. And a symbol is defined as taking this operator O and sandwiching it with the single particle wave functions. So from the operator now I go into a classical function. Further, the product of matrices are replaced by a star product of the symbols. And the trace is replaced by an integration over the volume measure of the space you work in, whatever is the space you work in. So this action is a bosonic action describing the dynamics of the Lois-Landau fermions. It's a universal. This is starts from a universal matrix action, but depending on the space, the star products differ. So this was used by Sakita back in '93 to calculate the effective action in 2 dimensions by these people in the context of C1 string model, but it can be generalized to arbitrary dimensions.
But before doing treatment, it's just like arbitrary Landau particle in a magnetic field. And then putting star and just projecting.
No. This is the Lois-Landau. Okay, this is Lois-Landau level. Depending on what is the single particle spectrum, you find the appropriate star product for the space you are in. So this is a non-commutative field theory on the Lois-Landau level itself. Now, something interesting happens when we take large N limit. Okay, so this action essentially is reduced to a chiral action on the boundary of the droplet. And let me show you how this happens. So let's look at the abelian case first, where I have an abelian magnetic field. So this matrix U, which is the collective degree of freedom, is essentially to the I phi, and the action will be expressed in terms of the symbol of phi, which is a boson field. Now, there are some important ingredients, and one of the important ingredients in reducing the action into a chiral boundary action is the fact that the symbol of the commutator of 2 matrices is essentially a Poisson bracket. So I'm reducing this to a phase, it's like I have a phase space. So quantum Hall effect becomes a phase space of a lower dimensional space of system. Further, the density, ρ0, the ground state energy, for large n, essentially becomes a step function, which defines the boundary of the droplet. The derivative on ρ0 is now a delta function that has support of the droplet boundary. And if we put all these ingredients together, we find that the original action becomes just a boundary action of a higher dimensional theory. Now, if I had started in 2 dimensions, this operator here will be just the tangential direction along the droplet, along the boundary of the droplet, which is 1-dimensional. However, here I have a higher dimensional droplet. So in principle, there are many tangential derivatives to that boundary. However, the theory chooses a particular tangential derivative, which is Poisson conjugate to the radial direction. So although this is a higher dimensional theory, the propagation is along a specific direction. So this can be considered as a collection of 1-dimensional chiral fields put together into this fashion. Okay, so that's a very special effect that appears in the experimental realization. I'm sorry?
But that's like a gauge choice?
No, it's not.
What picked that direction?
What picks that direction is the omega, the symplectic structure of the space, and the original confining potential. The confining potential picks up the radial what is the radial direction, and the symplectic structure of this theory picks up this direction, which is related to the magnetic field, to the Yuan magnetic field. So this was in the case that I have only an abelian magnetic field, but it can be generalized in the case where we start with a non-abelian magnetic field. In that case,
The alien magnetic field is, you just picked the field, it was just a number. And is that true?
It's related to the number n, yes, but I'm writing a 2 form because it's a 2 form So it has to do with the symplectic structure of the problem. You know, the field strength is n omega, where omega is the Keller to form.
So the field has that structure.
Yes, yes, but yes. So, but we generalize this to the case where I have non-abelian fields. Now, in this case, the wave function, as I showed you before, is a non-trivial representation of some SUK. So let's call that the dimension of that representation n prime. Then we can write the action in terms of this non-abelian field G. And what we find is that the effective action is essentially a generalized Gates-Vezumino term. So if you forget this term here, this looks like a three-dimensional Vezumino term, but because we are in higher dimensions, we have to saturate with higher powers of this form. And again, the same feature as before. This now is a covariant derivative, but it's a covariant derivative along a particular direction. So although the theory is higher dimensional, the propagation is along a particular direction, which is chosen by the system. And this can be thought of as a collection of non-abelian chiral fields. Yes. 5 minutes. Oh my God. Oh, okay. So I'll skip a lot of this. So we can extend this in the case where we have Gates fields. So if we start from a matrix action, we can covariantize this. So there is a non-commutative field theory like that. The issue is what is script A have to do with the Gates fields of the theory. So we notice that the action is invariant under these transformations, but it also, we know how S changes, S describes the original system, so there are Gates interactions. It has to be invariant under these user Gates transformations. So the strategy is to write the script A as a function of the user Gates fields, and so that if we do a Gates transformation on the right-hand side, induces this transformation, this particular transformation on the left-hand side. This is a kind of Seiberg-Witten map. If we put the expression of script A in terms of the Gates fields, and take the large N limit, the theory decomposes into two parts, a chiral Gates-Vezumino action on the boundary and a Chern-Simons action in the bulk, so that the two together are anomaly free, and because Gates invariance is automatically built into the theory. Okay, so this way of doing the effective actions, however, has used the particular ingredient of the single particle spectrum, because we use the star products and stuff like that. So now what we want to do is deviate from CPK, because we want to introduce metric fluctuations. So how can we do that? We cannot use a single particle spectrum anymore. So we do that by using an index theorem. So the lowest Landau level obeys a holomorphicity condition, which is essentially the anti-holomorphic covariant derivative on psi 0. Now, for complex manifolds, the number of these solutions is given by the so-called Dolbeau index. So a Dolbeau index is written in terms of Todd class and Chern character. Okay, Todd class is just powers of traces of the curvature, and Chern character is powers of traces of the field strength. The important thing is that this is an integer here. So even if we introduce fluctuations of the curvature and fluctuations of the strength field away from the background values, this will remain the same index. So that's how we introduce the fluctuations. So the idea is that we consider a fully filled lowest Landau level where each particle carries a charge 1. So in that sense, the degeneracy for the lowest Landau level by definition is given by the Dolbeau index, and this is the charge of the theory. Now, if we look at the unintegrated quantities, the Dolbeau index density is the charge density, but I know how to construct the charge density from an effective action. If I take the variation of the effective action with respect to A0, that is J0. So what we do essentially is integrating up to find the effective action. we covariantize the expression, and after we do that, we find the effective action. In the case of CP1, this is the effective action we find, which is the same like people found by integrating out fermions. But now we have general expressions for all dimensions, all higher Landau levels and non-abelian magnetic fields. Here I'm giving you just an example for CP2, the lowest Landau level, abelian gauge field. But as I said, we can generalize in all dimensions and higher Landau levels. Now, having these effective actions now, we can calculate the electromagnetic response functions. For example, this is the usual current in 2 dimensions. By the way, a whole current can be generated from time variation of the metric, even if we don't have an electric field. But this is in 4+1 dimensions, including the curvature. This is in 6 dimensions, and so on. We can find these things for higher dimensions. And also, we can find the energy momentum tensor and identify this viscosity tensor. And from that, we can identify the whole viscosity. Now, in 2 dimensions, this calculation has been done because the effective action was known. This is the whole viscosity, but we can do it in higher dimensions, and we did explicitly in 4 dimensions. We found the viscosity tensor. It's a very complicated form. However, if we take the flat limit where CP2 goes into 2 complex planes, then we find this whole viscosity and can be generalized to.
Time reversal breaking is not consistent with isotope. So you're picking one certain direction.
Okay, this is the part that is, there are G dot, we isolate the term that is proportional to G dot, but there are derivatives acting on G dot. So there is, the tensorial structure is very complicated. I'm only writing the coefficient in front of G dot when this decomposes into 2 complex planes. Of course, there are also higher other response functions because we have non-abelian gauge fields and stuff like that.
Switch the magnetic field, this doesn't seem to change.
I'm sorry?
Switch the magnetic field, it doesn't seem to stay in sign. Typically, the all coefficient depends on the sign of the magnetic field. Right?
Well, not in 4 dimensions. Because yes, the 2 complex planes have the same magnetic field. Okay, I had some results on entanglement entropy, which I don't have time to go over. I only want to say that in that context, if the entropy is expressed in terms of a phase space area instead of the geometric area, one finds a universal expression for the entropy in terms of the phase space area, which is true for all dimensions and whether you have abelian and non-abelian magnetic fields. And I'm happy to talk about this with people, but there is no time, so I will skip it. So I come to the conclusions. So this quantum Hall effect on CPK and its variations, as I discussed, they give a nice platform for arbitrary even dimensions. And it bridges also theory and experiment, because as I mentioned, over the last few years, there have been experimental realizations of 4-dimensional quantum Hall effect in optical and cold atom systems using synthetic dimensions. So essentially what is done is, in the case of the cold atoms, we have a lattice of cold atoms, but each cold atom has many internal states. So by shining a laser, one simulates transition in these internal states, which is like hopping in an extra dimension. So they're using this. For example, this group used, if I remember correctly, used 2 real dimensions and 2 synthetic ones. 3 real dimensions and 1 synthetic one. And also on a lattice, you can create artificial magnetic fields by introducing a phase factor as you go around the plaquette. Okay, so there are interesting things that they find in these experiments that we can relate to. For example, they calculate the analog of a Hall conductivity, which is now related to the second CERN class of the electronic band. And another important feature, which is very prominent in our work, is that if they look at the edge degrees of freedom, they propagate. It's an asymmetric behavior in the sense that they propagate along a particular direction. And this is something that was prominent in what we did. That's what we find. Now there are proposals of extending it to 6 and higher dimensions, and also maybe in these systems try to calculate the Hall viscosity, which is something that has not been measured yet. Now, from our side, as I said, everything was formulated in terms of integer quantum Hall effect. We are trying to see whether we can extend fractional quantum Hall effect to higher dimensions by using maybe some flux attachment or the Parton picture. We have not been extremely successful yet, but that's the proposal. So thank you. Vile semi-metal? Why? I don't know. I don't know what exactly vile semi-metal is.
Maybe I missed this. So at some point you went to non-commutative geometry and then came back down, to write the effect. When you came back to the final effective theory, you came back out of non-commutative space. Like just at a high level, what was the motivation for going into non-commutative space?
No, it is because it's a matrix action, so it's a non-commutative field theory. If I keep all the terms, now if I take large N limit, it becomes this edge. It gave me that the dynamics for the edge.
So you took large N.
Yes, yes, yes.
Let me try.
Sorry for being late.
You're getting the card.
Yeah, that's fine.
And what should I do? Just share your screen.
Okay, our next speaker is Paul Goldbart from Stony Brook.
Figure out how to change. There we go. Good. Thanks very much. Well, it's great to be here, and I really appreciate the hard work of the organizers for putting together a really stimulating and enjoyable meeting. So thanks very much. So I'm going to talk about some work that is squarely in the world of classical physics, but it borrows techniques from quantum physics. And so in some sense, it's an interplay between classical and quantum physics. What I'm not going to do today is talk about active media, although I think you'll see that some of the ideas can connect to active media. This is work that has been really a joy to do. It's actually some time ago, at least the initial phases. Zeb Rocklin was a graduate student of mine, now professor at Georgia Tech. Sheena Tan was a colleague at Georgia Tech and is now at the International Center for Quantum Materials in Beijing. Benjamin Loeber is a professor now at the Catholic University, Pontifical Catholic University in Santiago in Chile. And Anton Suslov has recently moved to be a professor at Cambridge University. So the work that I'm going to talk about was inspired by some experiments in biophysics. And the experiments were done in a research group of Jennifer Curtis, who's particularly interested in mammalian cells. And here's a picture of a mammalian cell, a few microns across. And it turns out that many of these cells exude kind of a polymer brush out from the surface. So this layer here, this green layer, actually is a set of polymers whose structure and properties, especially the viscoelastic properties, are controlled by the cell, and they influence the ability of the cell to move, that's cell motility, and the ability of the cell to stick, that's cell adhesion. And they're particularly important, for example, in your knees. You have cartilage in your knees, or you have some left, and these cells play an important role there. So how does the Curtis group study these so-called pericellular coats, these polymer brushes? What they do is they embed a dielectric sphere in the medium, and then they pull and push on that sphere through the polymer coat. They reduce the entropy of the polymer coat by obstructing the polymers from passing through the regions where the beads are. And the forces and responses to forces that are measured teach you something about the structure and properties of these very important coats. And so the general idea is to try and understand the role of what I'll call topological obstructions in polymeric media, particularly focusing on the impact of the strong polymer-polymer interactions, because as you all know, if you have a pair of polymers or even one polymer bent back on itself, it can't pass through itself. And those interactions play a very important role in the properties of the coat. So that was the sort of broad inspiration. As you'll see, we've deviated fairly far from that. And I want to begin just by reminding you of a couple of very well-known and important consequences of interactions between polymers. So here's a picture of a polymer, this long green wrapped up coil. The polymers typically come with a length scale called the persistence length, which tells you essentially how far you need to walk along the polymer before your orientation has changed. And so what this length does is it defines for you essentially a statistically independent segment of the chain. If you walk along the whole chain and measure it in units of the persistence length, you get this number n, which is sometimes called the degree of polymerization or the index of polymerization, and it really controls essentially how long the chain is. So the characteristic size of the chain is usually called its radius of gyration, and I just sketched it roughly here. And that radius of gyration is a length, so it goes with the persistence length, and it scales with the number of statistically independent segments, the length of the chain, with some exponent. And as you all know, when the chains do not interact with themselves, when there's no excluded volume, that exponent is a half. This comes from just simple ideas connected to Brownian motion. But as you also know, at least in 3 dimensions, if you turn on interactions, so the chains can't pass through one another, something quite dramatic occurs. The chains actually swell. The exponent that used to be a half, 5/10, now becomes 6/10. Doesn't seem that dramatic. But when you bear in mind that it's quite reasonable to make chains that have 1,000 steps on them, then you can see that for such a chain, when you turn on interactions, the length scale, the radius of gyration will actually double. So the interactions can have a very dramatic effect. So that's an equilibrium example of the role of interactions. Here's a non-equilibrium example. So this is chewing gum or silly putty or some other viscoelastic fluid. It's this tangle of polymers. They're not cross-linked to one another. Nevertheless, they entangle so strongly that the media exhibit timescales on sort of human kind of timescales, as you know very well, from pulling silly putty slowly versus pulling it quickly and having it fracture versus having it flow. And the characteristic timescales involved are associated with chains wiggling their way out of a kind of cage that they exhibited, or that they inhabited, I should say. And that timescale is certainly very much dependent on the fact that the chains can't move through one another, and in fact grows like roughly the 3rd power. Experiment gives about 3.3, simple theory gives about 3 for the rate at which this timescale grows as you make the chains longer and longer. So those are just 2 examples of the role of interactions, one in equilibrium and one out of equilibrium. So what are our key themes for today? we want to think about fluctuating objects, low dimensions, and interactions, and we want to think about them in the context of topological constraints. So we're going to see what role topological constraints play. We're not going to study the pericellular coat ideas of the Curtis group. We're just going to look at a theoretical question that is a spin-off from there. And we're going to see if there are any qualitatively new phenomena. And we'll see that there's at least one, which is a kind of version of tearing. It's hard to imagine that a fluid would tear. One thing about fluids that one thinks of is that one might displace, but the fluid backfills in. But we'll see nevertheless that there is a kind of tearing. Everything I say today is really inspired by a beautiful paper from 1968 from Pierre-Gilles de Gennes, who showed how it's possible to use the Pauli exclusion principle and in fact non-interacting electrons or non-interacting fermions, I should say, to understand the implications of a rigorous self-avoidance of random walks. Many other authors have picked up on these ideas from de Gennes from 68 and run with them. We'll see a couple of settings here and there. In our papers, we've tried to be rigorous about citations. In my talk, I shall just say that many workers have made a very nice use of these general ideas. So we're going to begin with the simplest possible setting, and that's one of these polymer fibers. It's now directed. We imagine a flat table with a polymer on it, and you hung weights on either end to create a tension. So this is a polymer under tension, and it costs energy to bend the polymer, because when you do, you increase the arc length that I'm indicating here, and these are fluctuations to different configurations. When you increase the arc length, you lift the weights, and that costs you potential energy. So that's the source of energy that we are thinking of when we consider Boltzmann weights for these systems. We're going to think about sort of almost straight polymers with rather small deflections, and everything is going to be thermally excited. There are a number of realizations beyond this sort of toy idealization that I mentioned here. One can think of polymers in a pneumatic background. The rod-like molecules that have organized into the pneumatic state provide a kind of guide for the polymers to move in. One can consider step edges on crystal surfaces. You're now looking down on a crystal with a plateau, and below the plateau is a plane, and this is then the wandering step edge associated with the motion of atoms on the surface. One can think about vortex lines in a planar type 2 superconductor, or a type 2 superconductor sandwiched between two sheets, a type 1 superconductor, for example, and there are connections too with the KPZ growing interfaces. So there are a number of realizations for this kind of fluctuating line. So we're going to think about that line under tension, as we've just discussed, and simple Pythagorean ideas allow you to see that at least for small deflections, here's the path of the wiggling polymer, here's the tangent vector telling us the slope, W will be the displacement in this direction as a function of lambda, the distance in this direction, and W of lambda will tell you the precise semi-microscopic configuration of the polymer. And it's easy to see that the potential energy is then associated with this kind of integral, the tension, and the excess length coming about from the wiggling. So we want to understand polymers under these circumstances. And so now it's evident that if you'd like to understand the free energy, you focus on the partition function, which is obtained by integrating over all configurations of the polymer with this simple Boltzmann weight. So now let's ask ourselves what happens if we put in interactions. So interactions, for example, might count the number of times that the polymers pass through one another. That's the simplest form of interaction. One needn't restrict oneself to the simplest form of interactions. In fact, here, we haven't even put interactions yet. We've moved from where we were with one polymer and its fluctuations just drawn in thinner lines to several polymers with no interaction, so they're perfectly at liberty to cross one another, and the Boltzmann weight is just a simple product of Boltzmann's weights, one for each polymer. Now let's put in interactions. So now we can imagine summing over pairs of polymers with an interaction potential that just counts how often the polymers are close to one another with some interaction that I'm thinking of being short-ranged. It can even be very short-ranged. So now we have the energy coming from wiggling and the energy coming from interacting, and we want to understand the implications of these interactions. Now let's move to a superficially completely different question just to build up some technology. So we're going to instead look at a single quantum particle moving in one spatial dimension. And you know everything I'm going to say, but let me just introduce the ideas for notation. So in quantum mechanics now in one dimension with one particle, we might very well be interested in the question, let me suppose I prepare the system at some initial coordinate Wi for initial, and I ask for the amplitude to be at this final position at some later time t. You can address that question, of course, with the Schrodinger equation or with the Feynman path integral, and we're going to think about it in the language of Feynman path integrals. So now the transition amplitude from the initial position at time 0 to the final position at time t is given by, as you all know, the sum over paths, the Feynman path integral, weighted by this phase factor that involves the action s as a functional of the path. Real time here, not imaginary time. We're going to need imaginary time versions. And here, not just the stationary value of the action, but of course, the fluctuations around the stationary value. So Feynman path integral, you all know. We can, if we wish, consider this Feynman path integral in imaginary time. And if we do, we end up with this Boltzmann weight rather than the usual unitary time evolution operator. And it's very useful, and we shall need this to understand the role of this analog of the transition amplitude in imaginary time now at long times, when in fact this quantity ends up being dominated by the ground state owing to this exponential factor. So at least for long evolutions, we find that this transition amplitude ends up being given by ground state wave functions and then an exponentially small Boltzmann weight. And that's called ground state dominance, and that's going to turn out to be good for long fibers. So we've built the technology that we need. We've looked at the classical problems we're interested in, and we've looked at simple quantum mechanics ideas that you're all familiar with. And de Gennes' elegant idea was to harness the Pauli exclusion principle in order to implement strong repulsion. And so that's exactly where we're going to head. We're going to use Pauli to ensure that the polymer trajectories don't overlap with one another. So let's go back to Feynman and ask now questions about two particles. And we can ask the question, given that we had two particles in this initial pair of positions, what is the amplitude for finding the pair of particles at this other pair of positions? And we know, because of quantum fuzziness, that we don't know which part. It's not even meaningful to ask which particle ended at which green spot. And Feynman says what you have to do is consider the path integral for one permutation of the final positions, and then at least for just two particles, subtract the path integral with the twisted boundary condition. And then there's a simple combinatorial idea, which I'm sure is widely known, although I am not sure who wrote it down first, which goes like this. Suppose you wish to look at the difference between the path integrals with the untwisted and the twisted, or unpermuted and permuted boundary conditions. You can organize the pairs of path integrals into configurations that I'll say kiss once or cross twice or kiss twice and so forth, and end up with these boundary conditions compared with crossing once, and kissing once and so forth. And it turns out that those contributions all cancel except for the contributions that come from paths that never cross one another. So this is how the Pauli principle, if you like, implements the inability of the polymers to cross one another. So the upshot is that if we have a gas that can even be non-interacting of many quantum particles in one dimension, the path integral representation provides us with a strategy for fully including the strongly repulsive interactions of thermally fluctuating polymers, at least in this anisotropic two-dimensional situation. So let me give you a couple of examples of how this plays out. And so this is a sort of central to where I was headed. Here is now an assembly of polymers. Here they are, 1, 2, 3, and so forth, running up this channel. Imagine that there are hard wall boundary conditions that don't let the polymers escape. Now we're going to ask the following question. Suppose we come to this two-dimensional polymer fluid, and we do the analog of Jennifer Curtis's group inserting a bead, which provides an exclusionary region that will not let the polymers into it. Now we're doing something different. We're going to put in a knitting needle this way that stops the polymers from fluctuating across it. So now, however many polymers are to the left, all the configurations that contribute to the partition function have exactly that number of polymers to the left and complementary number to the right. So it's a topological constraint that limits the configurations of the polymers. So let's imagine that we put this pin in, and let's imagine that we close our eyes, put it in, and we'll call the position it goes WE for equilibrium, because when we put the pin in, the chances are that it will be in a situation which is balanced in the sense that the distance to the left is proportional to the number of polymers to the left and similarly to the right. And so we would have a balanced situation and the pin is not going to feel an average force one way or another. So that's the starting condition. Put the pin in into some equilibrium configuration, equilibrium position. Now what we're going to imagine doing is pulling the pin to the left in at an equilibrium position, WE, and stop at a position WP for pin. So we've pulled the polymer fluid to one side, and we're going to ask, what are the implications? If this were bath water, you know full well what would happen. It would just fill in, and there would be no residue of what you have done because there's no topological constraints associated with the point particles and the knitting needle-like topological obstruction. But for polymers, things are different for obvious reasons. And we're going to ask ourselves, how do we work out the equilibrium density of this sheet of two-dimensional polymers now that we've subjected the ensemble to this condition or topological constraint? How do we do that? We use the technology that I introduced in the language of 1 and then 2 fermions, and we consider then the ground state. We're considering a long system, so ground state dominance turned out to be acceptable in certain parameter regimes. And we take the equilibrium, the quantum ground state of the many fermion system, and we're then obligated to compute an amplitude, and it's an unusual amplitude. It's an amplitude to find n left polymers on this side of the pin, given the location of the pin, and n right polymers on the right side of the pin. And this actually connects to lots of beautiful work done in the group of Sasha Abanov and others to do with what are called Red Sea problems, because you're talking about quantum fluctuations that open up a gap in a fluid. So once again, one needs to understand the quantum amplitude for making a transition from the ground state to a state in which n left particles are in the left part of the strip and n right in the right part of the strip, regardless of where the polymers particles are, as long as they're on the correct side of the strip. So it's an unusual kind of measurement, if you like, but it's one that one can analyze essentially by going to collective coordinates that replace the coordinates of the particles by a certain density, and then trying to construct the equilibrium value of that density. Probably not a good idea to go through the calculational details, but let me show you what happens. So once again, you put in the pin, you drag it to the left, you wait for equilibrium to set in, and you ask yourself, what is the structure of the fluid to the left of the pin where polymers have been scrunched up, and to the right where they've been diluted? And what you find in what is essentially a semi-classical computation is that over on the right side, the less where the fluid is now less dense than it was before you put in the pin, the density has a constant value that then shrinks down like this to 0, not at the equilibrium position where the pin first started, but rather, not surprisingly, the fluid sags in towards the place that the pin is. So you put the pin in here, you drag it this way, the polymer fluid sags in, but it leaves behind a gap. And so this is on the left-hand side. On the other hand, now the density is higher than in the equilibrium state. And what happens is you have this square root divergence of the polymer density on this side, in the dense side. And so you have, in a certain sense, torn the fluid because you put in a pin, you dragged it to the left, and the fluid didn't just come with you, it left a kind of gap. And so let me show you what that gap looks like if you look down on top. This requires a kind of hydrodynamic calculation. what you see is this singular region in which the polymer density over here is not very far from what it was before you put in the pin, and then it drops at this edge down to a exponentially small, sort of semi-classically forbidden region, if you like, over here, which closes off at the location at which you finally held the pin. So that's the sense in which the polymer fluid is now torn.
Can you clarify what you mean by the density divergence? Like physically, you know.
Well, it surely gets cut off,
Yeah.
but in the simplest kind of mean field theory, it diverges. And there's a picture over here, and you can see that divergence. So here you're falling into this void and then rising out of that void at this singular point.
The tearing only happens beyond some transition, you can tell us about?
No, not as far as I know. This is the equilibrium state. So you need strong interactions for the calculation to be valid. You need high density, but that's more or less it.
You're saying if I just move epsilon away from the
Yes,
equilibrium.
yes,
here,
yes. I'll show you that result coming up right
if
now.
I move only a fraction of the spacing between the fermions.
Then you will get a very, very small gap, and I'm not sure what happens at those length scales.
Okay, so but it doesn't even make sense at that length scale.
So that's right. That's
You're
right.
saying there's no actual threshold.
Not that I
There
don't
just
think
might
so.
be A regime of validity of this description.
Thank you. I think that's the right way to put it. Yes. Yeah.
Put it in the quantum particle language, what would this gap cause?
This gap would correspond to saying when you compute the amplitude in question, namely the amplitude to have a certain number of particles on a certain side, then there is the amplitude for finding individual particles on the other side is small.
You link it to some scattering length or time?
I haven't thought about that. Quite likely, but I'm not sure how to do that.
Large deviation property of the wave function.
Yes, exactly.
The quantum problem, there is no pin that you are moving down, right? You just find the impedance region.
That's right. I'm just asking for the amplitude for n left particles to be on this side, n right particles to be on this side, and I'm looking for the dominant contribution in terms of a continuum density description.
Precisely the position of the pin, I see that the distribution has a cusp. That means that there are polymers there that have a large angle, which is beyond the small angle approximation that
Yeah.
have been using.
Yeah, and I think, I'm not sure the theory has anything to say at that kind of scale, at the persistence length scale. I need to check on that, but I think that's right. So back to David's question, you can ask, for example, the following question. So here was the original position, the equilibrium position. I pull the rod this way and I stop. The polymer fluid sags in, and I can ask for the relationship between the displacement, how far did I move the pin, and the size of the gap. And the answer is almost linear divided by a logarithm, so slightly sublinear. That's what happens when you move the pin away. The factor here is associated with the impact of doing the process close to a boundary where things change. You can also ask about the force law. So you can ask, for example, what is the force on the now displaced knitting needle? It's come over here, and of course there's a force pushing it back. Is it Hookean? No. The increase in free energy is quadratic, but not quite, because there's a logarithmic correction. So slightly sub-Hookean. Yeah.
Just, I'm sure you said it more than once. Am I over interpreting the zero? Because I kind of feel like you have a semi-infinite liquid to the right.
Yes.
And semi-infinite in both directions.
Yes.
Right.
Infinite in both directions.
Why does it?
Why the sample width there?
This direction here.
That's fine.
That's fine.
That's fine.
Oh,
It has to be
okay.
finite.
Yeah.
Otherwise.
So if I take this.
Otherwise, they'll just move away. So yes, otherwise they'll just follow by. I mean, if you put this on the outside of a cucumber, then when you move the pin, everything's just going to move around with you.
Right, no, what I was more worried about, you know, zero, like, why isn't the continuum just fill in?
I see.
Because the thing would be
Yeah.
compressible,
Yeah.
right? And what you were saying is that somehow it's finite size.
And I think one way to think about this is to imagine integrating out the polymer tails and leaving yourself with a 1D gas, which has then long-range interactions by virtue of the forces mediated through the polymer tails.
Yeah.
That's where the long-rangeness comes in to enforce this almost electrostatic-like phenomenon. So you could imagine putting in an obstacle like this, for example, and now if the obstacle is wide enough, wider than the gap that we just saw, you would have divergences on both sides. If you shrink the obstacle down, eventually you get inside the gap, and then you have a gap just like before. What's harder to do is to look at interactions between an obstacle here and this obstacle or an obstacle higher up, because under those circumstances, you would need the finite time propagation of the wave function and not just the ground state. So that's a more complicated calculation. How am I doing for time? Okay, so let me just touch upon three-dimensional polymers, and I'll be brief. So here are three-dimensional polymers. There they are running up from a sheet. You can think of this as being something like a polymer brush. And now we can ask the same kind of question. Suppose we put a collar into this system, put the collar in and have the polymers coming through on the inside and around the outside, and now tighten the collar or expand the collar away from the equilibrium configuration. And now the same kind of question arises, but how do you handle it? Handling it using fermions right from the outset doesn't fly, because you really need to provide an equilibrium distribution of the boundary conditions top and bottom, and they're positive, and so you better have bosonic, not fermionic wave functions. But this can be managed, and one can use, just as in the previous talk, Chern-Simons gauge fields in order to turn these hardcore bosons into fermions. You can then make the kind of smearing approximation that's typically made, where you release the flux from the tubes and smear it homogeneously, and now you have a Landau level problem, and the appropriate ground state wave function is a certain van der Waals determinant that's not too hard to calculate. The upshot is very similar. So here's the collar that you put in. Of course, I'm imagining many, many more polymers, not just these handfuls like this. But you can ask what is the consequence of either tightening or expanding that ring, and that's shown here. The effect is not quite as pronounced, but what you can see here under a tightening circumstance is an increase in density. Here is the ring. Here is the depletion zone, if you like, outside. And on the other hand, if you expand the ring, you can see this increase in the density, leaving a depletion zone behind. Let me wrap up by just asking the following question. We've talked about these polymers whose classical Hamiltonian has conventional quadratic kinetic energy. Well, let's suppose we replace the Schrödinger equation by the Dirac equation. What would we find? So many of you will have seen the little throwaway homework exercise in Feynman and Hibbs, in which the path integral for the Dirac equation to ask the following question: what is the amplitude to go from a certain position with a certain sign of the velocity to another position with a given sign of the velocity? And that amplitude for the Dirac equation, at least in 1+1 dimensions, is associated with a checkerboard path integral. So now you have paths that are zigzag like this, and they have weights associated with turning. Here's the weight associated with turning. Not surprisingly, if the mass goes to zero, then this turning weight goes to zero, and you just propagate along the light cone just as you'd imagine. On the other hand, if you have a mass, then there are opportunities for the contributing paths to bend, and you fill inside the light cone. So you take this Dirac equation and work instead in imaginary time and with an imaginary mass, and you get back to the polymer problems we've been talking about with these kind of zigzagging polymers. And you can ask what happens when you pack those polymers together and you make their bending more or less flexible, and you make the system more or less dense. And what you find is a phase diagram, and this is presumably just approximate given the low dimensional nature and the unlikelihood of spontaneous symmetry breaking. what you find then, as a function of how strongly the polymers repel, and now you need authentic repulsion built in because the Pauli principle won't work for you when your spins are opposite. And you can also imagine increasing the density, so repulsion strength and density, and you find, or at least you get signatures of a transition between an unaligned phase where you get as many zigs as zags to a collectively tilted phase in which the zigs or zags are biased towards. A number of authors have elaborated, I have to say, very nicely on this kind of general strategy to understand what happens if you have substrates that are grooved, mimicking a crystalline potential, or even substrates that are not aligned with the time axis but go off at an angle and tend to encourage tilts or not tilts and so forth. And so there's very nice work from Vincenzo Vitelli's group in Chicago and Jason Paulos' group at Harvard and others taking these ideas in a number of directions. So I think I'll stop there and thank my co-workers and happily take any questions. So here, I'll get you in charge, not me. Alan, go ahead.
So what about polymer membranes? Is that where you have sheets and maybe layered together? Are there applications and can you apply this same kind of like approach?
Yes, but it gets complicated quickly. And in fact, in particular, there are manufactured structures that look like leaves. I mean, LTS, so they're vegetable. And so they're like onions, but they're not spherical, they're linear onions and they fluctuate. And so now you can imagine these fluctuating membranes. Of course, the challenge is that what you really then have is a string, and you have to worry about these nestled strings in the plane and their world lines looking like travel legs and so forth. And although I sort of imagined going in that direction, I haven't. I'm not quite sure how to implement the Pauli principle in that situation. I don't really know if the right strings can be constructed to have this kind of cancellation. I don't know that. I have actually tried. There's another problem that one can work on, which is actually important technologically, which is called a polymer brush, where you have a surface of polymers coming up from the surface. And now you actually need to have the polymers stop at a certain arc length, but that arc length is really associated with their proper time. So there needs to be, if you like, a kind of bomb that goes off and kills the polymer when it runs out of proper time. And again, I haven't figured out how to implement that yet. Yeah.
I was just curious if you could do this, like people have seen these kinds of things experiment. If I just take silly putty, I put a pin in it and move it, do I see exactly the shape?
Yeah, I have not seen experiments aimed at this yet. The one class of experiments that I know of is actually the class that inspired Dugen more than 50 years ago, where you have these polymer fibers on a substrate, and now you do X-ray scattering in which the momentum transfer really is in the direction from one polymer to the next. And what you see is actually a kind of Fermi edge-like singularity in the scattering function, really telling you that the correlations of the polymers are much stronger than they would do if you had free polymers.
Okay, maybe we can.
So
Can we have a sure, yeah, in during the coffee break. Okay, yeah, let's thank all.
Screen. Okay. Yeah. Then go to the full screen.
I have my own.
Okay, so the next speaker will be Parmeshwaran Nair from CCNYG.
Okay, very good. So thank you to the organizers for inviting me. And it's been an interesting workshop. I have to perhaps apologize a bit because what I'm going to say is a little bit different from most of the talks you have heard. It's going to be a little more focused on the high energy side. But other than that, I hope you find something interesting. So I'm going to tell you about fluid dynamics, and I have rather been unhappy about most of the formulations of fluid dynamics that you read about. So I'm trying to tell you about a group theory based approach that I've been trying to develop over the years. And the whole idea is fairly simple, that, you know, the conventional way of formulating fluid dynamics, you would start with the idea of constituent particles and then build up some coarse-grained description or whatever, and thereby obtain some sort of aerodynamic description. But that is not really how we think about point particles anymore. Really, if you think about it from the point of view of quantum field theory, a point particle is a unitary irreducible representation of the Poincare group. So therefore, one should be able to use that idea and build up a fluid dynamics starting from that basic idea. And then, of course, if one would also like to start from the other end, rather than the particle point of view, we know that we can also think of quantum field theory either as multi-particle dynamics with the possibility of creating and annihilating particles, or you can simply think of it as fields, as the dynamical variables, and start from there. So one would also like to start from there and arrive at a similar description. So this is what I would like to talk about. Okay, so the key idea is you start with some irreducible representation of the Poincare group and develop fluid dynamics from this point of view. Of course, once we write it in terms of what think about in terms of group theory, there is a great potential to extend it to other contexts. And in fact, one of the things that started me on this is the idea of looking at non-abelian plasmas, like what they do in the Brookhaven lab. If you have a quantum plasma, underlying constituent particles carry non-abelian charge degrees of freedom. And how do we write down a heterodynamics for such cases? That is sort of the general idea. Okay. And of course, then one can read off several effects like spin effects, anomalies, chiral magnetic effect, things like that. Okay. I'll say a few more things about it. This has been work going on for many years. But what I want to talk about today is to ask the question, how do we come to this formulation, the group theory formulation, if we start from the gauge theory, the field theory side, and try to get that? Okay. The problem is highlighted by this following question. You see, if you have a non-abelian gauge theory, we do not have a gauge covariant and conserved color current. There is no definition of it. There is no gauge invariant definition of a current in a non-abelian gauge theory. Therefore, we do have a problem when we talk about hydrodynamics and color flow equations and things of that. Okay. By color, of course, I generally mean any non-abelian degree of freedom. Yeah.
The usual thing that people say that you write down the energy momentum tensor and an expansion, and that way you can do hydrodynamics.
No, but you could have color flow independent of mass and charge flow. I mean, mass and spin flow, right? So, for example, you can have single gluons. I can have a bunch of gluons here forming a color singlet and moving along, which would be mass or spin transport, but no color transport. But color transport is an independent entity, so we should be able to do separate. So energy moment tensor by itself doesn't give me what I meant.
And so people who do hydrodynamics of the proton plasma, what do they do?
They have to, so usually what is done is to write down color currents. One doesn't ask too many questions about where it came from, then try to kind of find some conservation laws with which you can work. But what I want to do is to go further and just ask fundamentally, can I formulate it in a meaningful way? Okay, so that's the main question. And the insight into how one can proceed comes from some old work, because we know that in general theory of relativity, we don't have a covariant and conserved energy moment tensor, an extremely similar property. The energy moment tensor for the gravitational field itself is a non-covariant entity if it is conserved, and therefore we have a similar issue here. And this, of course, has been noticed, and there is a very beautiful solution due to Einstein, Infeld, and Hoffman, if you have many gravitating centers, masses moving around in a gravitational field, how do I describe that dynamics of these particles, starting from the general theory of relativity? Okay, unless you can do a multi-center solution of Einstein equations, it becomes very difficult to do. So these gentlemen found a way around it, and that's what I'm going to use here as well. And the strategy is fairly simple. Every point, every mass point, you think of as a singularity of the field, you excise a small sphere around it, and then you say, now I am on a space which is no longer simple, topology. It has, if you like, word lines, tubes around these things. And so you remove them, and on this remaining space, I simply ask, what does the Einstein equation tell me? Okay. And that should suffice because there are no sources left once you have excised these tubular word lines. Then you can just use vacuum Einstein equations. Okay. And they were able to then use that and obtain equations and motions for the masses in general theory of relativity. It's actually quite remarkable work because this includes general relativistic corrections and in fact produced a set of equations which actually can be used in astrophysical context with multiple, dynamics of stars and stuff like that. Okay. So we're going to use something very similar. I'm going to look at surface states or edge states of the vacuum theory to define the particle-like excitations. And of course, unlike the EIH work that I mentioned, we need an action formulation rather than equations of motion because we would like to do it from a more quantum point of view. Okay, so the idea is we're going to talk a little bit about fluid dynamics using group theory. I'll say what the edge states are, and it'll be related to a cojoint orbit action. There is something, if I get time, I'll talk about it, what I call peripheral gravity. And then I will give some examples of how certain things at least are much easier and more transparent once you look at it in terms of group theory. Okay. All right, so let's talk about the group theoretic way to think about it. So we need a unitary irreducible representation of a Lie group. Could be Poincare, could be something more elaborate. So you first ask the question, is there an action which gives me one and only one unitary irreducible representation of the quantum? And the answer to that question is yes, there is an action. For any Lie group G, such an action is given by what is called the cojoint orbit action. It's very simple. U is a group element. You take its time derivative, you inverse, you don't. H's are diagonal generators of the algebra, say in fundamental or defining representation. W's are a set of numbers. So only the diagonals occur here. And if you take this action, this is sort of the mother of all topological actions, if you like. If you take this and quantize, then one knows that this gives you exactly one irreducible representation of the group. And which representation is picked out by the set of numbers W's. Those W's will form the highest weight of that particular representation. Okay? So this is a theorem due to Borel, Weil, and Bott. It was used in the physics context by Kostan, Suryo, and Kirillov, and on the mathematical, I think I got it the other way. Oh no, that's right. Wang, Bhattachandran, and so on in physics. So that's the general idea. So there is such an action. And what we can do is use this, say, for example, for the Poincare group, coarse grain it, we should be able to get relativistic fluid dynamics, okay? Add in some kind of QCD group or something, you can do quark-gluon plasma with that, and so on. Okay, so that's a general strategy. So how does one proceed with that? We take a whole bunch of point particle actions, copies of the ones that I just showed you. We do a coarse graining, replace the W's by a density, and it looks like this. So we can add in a Hamiltonian. This will be the general structure. And of course, if you write it in a more relativistically invariant way, which means you borrow some terms from H and put it over here, then you can make it look like this. And that's a general fluid action in terms of group theory. Okay. And depending on the group you choose, pretty much you can get anything in fluid dynamics out of this. Okay. The function F, of course, encodes specific properties of the fluid, such as pressure, energy, density, various other quantities. The J's are transport currents for the diagonal generators of the group. And in the case of Poincare, there'll be mass and spin transport. Okay. Or in the case of other things, it could be more general. Okay. So that's basically the structure. But before I go on to tell you about what are the interesting effects we can read off from there. I was going to change track and talk a little bit about how this might arise from the field theory side. Okay, so this is building up from the particle side. I want to come at it from the other side. Okay. So let's talk about edge states. So if I look at a gauge theory, then we know that there is a Gauss law constraint on the physical states, which is of this form. And thetas are some test functions, which are group angular parameters of the group, if you like. And the consistent implementation of this on all wave functions will require that theta goes to 0 on the boundaries of the space. Okay, so that's a very important result in how Gauss law is implemented. However, we can consider the similar operator, but without requiring that the test functions go to 0, which is this operator here, which differs from this Gauss law by this extra surface term, if you like. And these operators actually commute with the Gauss law. So therefore, they qualify as physical operators in the field. And so these things, which are primarily characterized by the boundary values of these test functions, they generate physical states. Those are the physical edge states of the field. They're really physical degrees of freedom in gauge theory. And if you think about it, we do use that in some contexts. I guess, I don't know, I was trying to invent something where the context could explain it, but I guess if you look at Josephson junction, the phase value on both sides, those phase values are dynamical parameters. Those are exactly like the analogs of the sides on the boundary. If you look at the theory in the middle, in a normal state. Okay, so this is a very physical context, actually. So what do we have? Therefore, these edge states are characterized by a group valued element, because this psi is a group parameter. It's on the boundary of your space, and it is a map from the boundary to the group. Okay, so that is what defines the edge states of the theory. Okay. Now, to use the strategy that was developed by Einstein, Infeld, and Hoffman, by the way, this is some current work I'm doing with Raju Venugopalan. What we do is we excise spheres or tubular neighborhoods in the space-time picture, remove a bunch of spheres, if you like, if you're in three-dimensional space. And then we ask, let's take an action like a Yang-Mills theory, and what happens when I do the variation? Okay. So the answer is well known. We know that there is a term that is going to give me equations of motion, but there is also a surface term that can bound. Normally, we don't worry about the surface term because we're looking at spaces without bounds. But effectively, I mean, most of the time that's what we do. But in this particular case, we have to include the boundaries because they're crucial to our analysis. Okay. So what do we do? So what do these tubular neighborhoods I excise look like? They can be some curved trajectories, slightly thickened, surrounding the charges, if you like, in any kind of way they can go along. But to simplify the problem, I'm going to do a coordinate transformation so that all these are straightened out. So if I do that, then the boundary term that I showed you looks a bit like this. Don't worry about how complicated it looks. It's basically that I can write a boundary term, and this is the equation motion term that usually arises. So what we want to do then is to say, to formulate the theory correctly, and we want to introduce a boundary action which will cancel this boundary variation so that I can freely vary my gauge potential or whatever dynamical variable. Okay. So I had to introduce a boundary term for that. And by just looking at this, we see that the boundary term, because there is if you diagonalize this value of the field in terms of some diagonalizing matrix U, which is some group element, then I can see that to get delta A naught and delta AI, I had to write an action of this form. This would be the boundary term. If I vary this is like the A naught term. We cancel this. K is related to this quantity here, diagonalized. And similarly for this term, this one. Okay. The second term will not be important for most of what I say because I'm going to assume that the cubes can be made very small in diameter. Okay. So what do we get? We find that what emerges from this analysis is precisely of the form that I showed you before. The Kostann-Kirillov kind of action that came from Borel-Weil-Bott theory. Okay. So because I diagonalized that boundary value of the field, I only have diagonal generators therefore, and then you can see that this, the total action is this is the angles plus this. The variation problem for this is completely well defined. There is no condition that you need to impose on variations in the boundary. That's taken care of by the second term. And then when you generalize with a bunch of particles, you do a coarse graining, and here is what you get, which is essentially the fluid action that I showed you before, starting from the point particle point of view. Okay, so these two methods indeed converge to the same kind of result. Okay. How am I doing? I forgot. 10 more minutes. Okay. All right. That doesn't say very much. All right. So what I'm going to do is to change tactics. I was going to tell you a little bit about, see, one of the issues that arises is the following, right? Suppose I just don't want to worry about quantum, I don't want to worry about, quantum plasma or anything. Simply want to do point particle there. Right. Then you can say, if I take particles in this, the air molecules in this room, and I want their dynamics, if I want to do it from this point of view of group theory and derive it from a gauge theory, the gauge theory relevant for concrete group is Einstein gravity. Therefore, I would have to start with the theory of gravity and derive it, but that's a huge overkill for something so simple as describing dynamics of molecules in this room, right? So there must be an easier way, and the easier way is to say that there must exist a way of thinking about gravity which discards all the gravitational interactions, simply makes it a topological theory. And in terms of that topological theory, I should be able to describe the dynamics. Okay? That's what I would call peripheral gravity, because that resides only on the boundaries, effectively. There's no bulk interaction. The classic case of that is standard Einstein gravity in 3 dimensions, because 3-dimensional 2+1, 2+1 dimensional gravity has no gravitational interactions. The curvature is localized where the particles are. It's a purely topological theory. Okay, so based on that, we can upgrade that to 4 dimensions. That's a theory that I refer to as peripheral gravity. But let me put that aside. I'll come back to it if I have time. But let me tell you a few interesting things about what is the use of group theoretic way of thinking about fluid dynamics. Okay, so let's take something like the full-blown standard model of particle physics with all the groups that you can think about. Okay, let me focus on for the color group. There is the left chiral group for 3 flavors of quarks and the right chiral group. The standard weak interaction group can be taken as some subgroup of these things here. So therefore, if you want, you can include weak interactions, whatever. Okay. So now here's a question we want to ask. Okay, we have a standard model, we have nucleons and quarks and all that kind of stuff. We say that the quarks are confined, they form hadrons and so on, but imagine we heat up the whole thing so that everything is in some plasma. Okay, all the confinement is gone, everything is in a plasma fluid phase. Now, tell me how I'm going to describe this theory. That's the question. Okay, so in this theory, you would expect independent transport of color, isospin, hypercharge, whatever quantum numbers you need, you will have independent transport of all this. Write down a fluid action for that. And that is then fairly straightforward to write down. Once you have the group idea, you simply use this group, SU3 color, U3 left, U3 right, and you can write down simply the action in this form. Okay. So this action will contain a left group element of U3, a right group element of U3, and then these are the diagonal currents that I mentioned, correspond to diagonal generators. And of course, there is some F function which will characterize in more detail the nature of the plasma. There's the Yang-Mills action. But the important thing about this theory is that it also has anomalies, parallel anomalies. So there must be a term that represents the chiral anomaly as well. And that's what I call the Wess-Zumino term here, okay, which can be straightforwardly constructed from the standard Wess-Zumino theorem. Okay. The important thing though is, you see, imagine that I have the strong interaction sector, and I have a shadow sector which cancels all the anomalies. The strong interaction sector goes in your plasma phase. The theory should still be consistent, and the anomaly should cancel. Therefore, there must exist a fluid expression of the anomalies, which captures all the effects of the anomalies and which renders the theory consistent with you. Okay? So that argument tells you that this will be a fluid expression where the group elements now represent currents, which will be related to currents of various quantum numbers in the plasma. So you can write it down. I won't display this because it's about 2 pages if I show you. But the key point is, once you have this extra term, you simply take the derivative with respect to the electromagnetic vector potential, which is one of these fellows here, and you find what is called the chiral magnetic effect. Okay? That is, if you assign chemical potentials for the axial directions, which are left-right asymmetry, there is an electromagnetic current created in the presence of a magnetic field. This is the chiral magnetic effect that we hope to observe in the Coulomb plasma collisions, because once applied, the passing nuclei create a current and intense magnetic field. So what comes out would create an asymmetry. There's more charge up compared to down. So the charge asymmetry should be below. Okay. So that's a direct effect of anomaly in the fluid dynamics language, which follows basically a couple of lines from this group theory way of thinking about it. Okay. Another thing I would like to say is, what if you simply forget about all the internal quantum numbers and just a mass and spin? What happens if I do the Poincare group and write down the relativistic fluid dynamics for that? One very interesting thing that happens is that, remember, Poincare group means relativistic physics, which means there is always spin-orbit interaction. Okay. And as a result, you find that if you look at the flow equations, there is, of course, the Euler equation, which is a standard one, that P is the pressure. But there is a spin flow equation which shows an unusual feature that gradients of pressure can actually affect spin precession in the plasma. So that's a kind of an interesting new effect that emerges simply from the fact that there is spin-orbit interaction for the relativistic theory. Okay. So that's another thing I wanted to just highlight. And one other thing I wanted to say is to look at the rotating superfluid, which actually goes to by von Wittmann, where you look at rotating superfluid helium, number of individual vortices are created. Each vortex obeys. So this is the state of the chiral flow that Paul has talked about in the past. I don't know if you're going to say anything today, but this is different. Yeah. So if you look at this state of chiral flow in superfluid helium, the vortices obey an equation motion like this, which is standard well-known equation. Omega is an overall angular velocity. Z's are complex coordinates in 2 dimensions. And this equation, of course, is well known. It goes back to the work of Kirchhoff in the 1880s. It's actually the two complex two transverse directions of the vortex are Poisson conjugate to each other, so they become non-commuting when you quantize the vortex. Now, what is interesting is that by considering the state of chiral flow and looking at the ground state wave functions for n vortices in large n vort limit, it leads to an anomalous diffeomorphism algebra with a whole bunch of anomalous terms here. The first term here is a standard diffeomorphism algebra. P and P dagger are the diffeomorphism generators. And this is the result that Paul Wittmann derived quite some time back. So one of the things you can, okay, by the way, this omega is related to these parameters rho here by the equation here, which is one of the constitutive relations in the theory. So what I want to say is that let's think about it in the group theory language. You look at an action, which is essentially the same one that I showed you before. But now I realize if I think about it in terms of groups, topological terms are much easier to visualize. There are additional topological terms one can add to the fluid action. And in fact, this is a particular topological term that I can add. And if I take this theory, this A naught is put in there because this is the constitutive relation that I just showed you here. This relation expressed in the group theory language. This is the vorticity base. Okay. So, by the way, okay, I will skip that expression. I don't think I need that. So if I take this action, then notice that from the time derivative terms here, I can simply read out the canonical structure of the theory, work out the commutation rules, and so on. Okay. There is not much to calculate. Just straightforwardly sit down and compute the algebra of the commutator for the different and you find exactly the same result which is obtained in orbit. Okay. So one way to think about this is to say that in Paul's work, so I make an analogy with the central term in the Kac-Media algebra, which you can derive by a point splitting argument in terms of the fermionic products. That is the analog of what Paul carried out in this context. But you can also look at the Kac-Media algebra as emerging from the Witten theory if I simply sit down and compile the theory. So there is an action way of understanding the same algebra. And that is precisely what I would claim that I am doing here in terms of that action I showed you. Okay. So I think these are just three examples of real physical effects. It's much easier to understand when you think about it in group theory language. Yeah, I think I probably ran over time.
Yeah, you running negative time also.
So I have more time.
Okay.
Now I'll just, if I can take 2 more minutes, let me just tell you about that gravity thing I put aside. Very simple. Take gravity in 2 + 1 dimensions. Einstein gravity in 2 + 1 dimensions with a cosmological constant. That is this action here, the second line. And that is actually the difference of two Chern-Simons terms. Okay. It's a very special property in 2 + 1 dimensions. There's a left Chern-Simons term and right, and the gauge potentials are related to spin connection and the frame fields, the Fierbeins or the Tribines in 3D in this fashion, omega plus E and omega minus E. Okay. If I simply put in what omega is, simplify the first line here, I get the Einstein action with a cosmological term. Okay. This is a known result going back several years, 1980s, I think. Okay. Now, of course, we do the same thing that I was going to do with the gauge theory before. I asked what kind of boundary term should I add to this to ensure that this theory can be generalized to space with boundaries. And once I do that, I can see that the boundary action is exactly of the form that I showed you before. The Einstein Kirillov type action. The H's here are SO21 elements because that's the group theory relevant for the problem, SO21 cross SO21. That's the analog of the Poincare group on a 2 + 1 de Sitter space. And if I then simplify this, you find that this describes representation for the de Sitter group with a mass given by these, these Q's here. These define the mass of the particle, and the spin is the difference of these two guys between the left and the right, and that gives you a complete theory of the propagation of particles in the space-time, where the symmetric group now is the de Sitter group. Okay. In 3 + 1, because this is a topological theory, we are able to do that. There is no real gravitational interaction. So if I want to write down a similar theory, which no gravitational interaction, but does carry the essence of the group theory on the boundaries, then I must take some topological theory, which is a BF type theory. B is a 2 form. F is the field strength as usual for a gauge field. And if I take this theory, there are 2 gauge symmetries here. One is the usual gauge symmetry. But if I shift B by the curl of a 1 form, if you like, or a vector, if you like, that's also a symmetry because of the Bianchi identity of X. Okay. So as a result, this theory has these 2 symmetries. And if you just try to solve the equations of motion, which are rather trivial, you find that everything is pure gauge. You can strip them all away. There is no non-trivial solution. Okay. Now that's true in a space with no boundaries. But if you have boundaries, of course, that's no longer true. And we have to add in boundary terms. And the boundary terms have a similar structure to what I showed you before. And precisely, okay, this is the term I want to focus on. This term is not so important. And if I take this term, then the values of B can be related after diagonalization, can be related to the mass and the spin. Not a problem. Okay. So if I take this for the Poincare, so the group I'm using is a Poincare group. So if I do that, then actually it's a De Sitter, but related to Poincare. And then I can characterize it entirely in terms of mass and spin. And then, of course, if I look at the dynamics, this is what the action you get, and this is the relativistic dynamics for point particles, mass and spin, in order to spin orbit interaction effects I mentioned before, are all buried in this formula here. Okay. It's a little hard to see, but because it's very cryptic, but my whole talk is cryptic because I can have more time, right? So thanks very much.
Maybe we can take the questions over the short. Come back.
Well, so we've been, I think, I mean, I can, yeah, just go there. It looks pretty empty, yeah.
So it will not be locked that one, but it will not be.
Shouldn't, go ahead and time it there. That gives you time to come back.
Dynamically, that means you're moving it out of the moment out of time. So that.
Recording. Okay, so let's continue. Two announcements. After the end of the workshop, we're gonna have a break, and I'm not sure if there's some dinner planning that Shiram is organizing. Did you make an announcement? So that was.
Yeah, I made a half of that.
Okay, good. So there will be an hour break, and then there's a public lecture that William Irvine is giving. You're welcome. I think we have spaces. We're trying to like bring non-scientists to participate. But obviously conference participants are welcome to join in. The other thing is that tomorrow and Friday, we're unfortunately not in this room. We're in fancier rooms that may or may not have blackboards, may or may not have, but they're fancier.
There are windows.
Right. Right. Well, distractions. Like, yeah. So you can look on the website for the precise location. One of them is called Skylight Room. It's on the 9th floor. It has a skylight. And the other one is called something else. I just don't want to mislead you. Just look on the website. Okay, there are specific room numbers. Okay, let's continue. Should I turn this off or is this?
In a second.
Okay. Then do you want the screen? You want me to bring down the screen or is it good enough? Good enough, okay.
Yeah, so before, okay, so what I'm going to talk about, sort of title, is.
What?
No good enough.
No. That was my fault. Oh, shoot, I shouldn't have done that, sorry. Still there?
No. The story which I'm going to talk is it's unpublished work, but it's about to be submitted. It's about emergence of kernels in classical or rather semi-classical hydrodynamics. But before I start, I attempted to do whiteboard talk. But before I start, I would like to expose this, say a few words about this picture. That is actually not real picture, it's a computer simulation of what is called corona mass expulsion. That's supposed to be a sound, and it's expulsed mass in the form of vortex. As you see, this flame rotates around the core of the vortex. Vortex starts from here, disappears there. You can think about it. So, of course, it's not a adiabatic process, but in my mind, it is a slow process. adiabatic process. But in addition, that fluid spinning around the vortex, it's also spiraling. And if you count number of spirals, 1 to angle, how much 2 pi's does it make? This number is integer. I'm not sure about this picture, but it's supposed to be integer. Okay, so integer numbers somehow may appear in classical hydrodynamics. Okay, now the process which is this process when there is a vortex, well, not loop because it's a surface that has a beginning and end, otherwise it's supposed to be loop, but fluid is spiraling is called helicity versus to vorticity when fluid is just going around the vortex, vorticity, helicity. And the number of this twist is a total helicity for this picture. Now I will come to, it will be the only slide I am going to show. Then I would like to come to the subject. And the point is, my point is that I'd like to argue that it is possible to formulate hydrodynamics of almost perfect fluid, where every twist is a fermion, and I explain what it means. So we can we can remove it now. So then I need to blackboard.
Can I ask you, Sean, so we should really think of this loop as a closed object, not something that's coming out.
Yeah, this is was a boundary, but this is only picture.
Okay.
But within the fluid, there are loops, big loops of vortex loops. There are many flying around, and typically the fluid not only rotating around vortex core, but also spiraling. And how fast is spiraling is called helicity. That will be my major hydrodynamic object which I will play with. Okay. Okay. So fermions, is this visible from this side? Right, fermions. The fluid dynamics. And I start from the following first an analog and analogy and then motivation. The analog which come in mind immediately is two-dimensional Ising model, right? Everybody knows Ising model, super simple, spin up, spin down, computer understand what it means, can compute. And apparently a special, very special defect in this Ising model, it's a non-local defect with an end, and end appears as actually Majorana fermion. That is Onsager, 1941. In this example, which we know when fermions appeared out of fluid mechanics, is one-dimensional. So we all know that fermions flying in one dimension can be sort of bosonized. Terrible term, but in fact, fluid in one dimensional form, electrons in one dimension form a fluid. Fluid move according to Euler equation, and this is what people call bosonization, without recognizing that they actually deal with one-dimensional fluid mechanics. So if I take this fluid mechanics, which come out of bosonization of fermions, put a spoon in this bucket, although it's one-dimensional, difficult to put a spoon, but my story will be 3 + 1. So we have space to put a spoon. I put a spoon, I move the spoon according to some protocol, create very special flow, and this flow is fermions. What does this mean? It means the following. So if I take the action of the fluid. I don't want to specify it, but it's an action of the fluid. Before I create this, before I put a spoon, and then put a spoon, move it around, action change. And if it's change in such way that it's acquire Planck constant, some integer number of Planck constant, and if this is integer is odd, it is Fermi. And that would be the best definition of Fermions I can think of. So actually 1/2, so like that. That will be Fermions. Fermion carries spin 1/2 normally, which means that if I rotate it in space-time, and we can think about this rotation, the action change. Will it possible to organize such situation in Euler hydrodynamics? There are several physical indications that yes, it is possible, and the indication is the following. Fluid can make out of molecules, for example, helium-4, superfluid helium-4, the bosons, fermions, nothing. But there is also fluid made of helium-3, which are, and their atoms are fermions. Of course, if I take one fermionic atom out of the fluid, I see that it's fermion. But it's not what I want, because when I remove one particle, I destroy hydrodynamics. Hydrodynamics is supposed to be smooth and it's nice. So instead, I'm looking for a nice smooth flow, like on this picture, created by, not by X-ray, which remove one atom, and I can study what atom it is, but like a spoon, which move things slowly, create some interesting flow. I stop moving a spoon, I see that it's changed. The story which I'm going to talk is classical, although there is a H bar here, so I need a scale. And this scale could become, if fluid considered to be semi-classical, and in semi-classical fluid, due to the same Sager, but now on Sager 1945, in London in London in 1952, I guess. And Sager suggested the circulation of fluid whose momentum is p around a moving material contour which moves with the fluid is not only constant as Kelvin theorem requires, but also quantized in these units. This fixture is observed, of course, in helium, and this integer could be very large. Then we go into classical limits, although Planck constant provides a scale. So the story which I'm going to say is a classical, but scale is coming from. So the question which I would like to discuss is the following. Let me first of all write Euler equations from a book. From here. The fluid characterized by velocity, which has 3 components, and density. And there are several, and there are the following equation. That is one equation, and then this is called Euler equation, and this is a continuity equation. Before I come to this, I forgot to mention one more motivation. Apart from the story with helium-3 and the spoon, there is a current running a story which is called heavy ion collision. When two heavy ion collide, that plays the role of a spoon. So the quarks goes out, a lot of quarks goes out, they form quark gluon plasma, and there is a statement, many people believe that there is a consensus that it's true, that there is some very short time scale when this quark and gluon form a fluid. Once it's formed a fluid, this is equation which fluid must obey, and there is no other equation nature gave to us, which describe how fluid flow. When it's quark gluon plasma, which becomes fluid in some picosecond scale, whether it's helium, whether it's water in the next room, they obey the same equation.
You're missing the last.
Sorry?
Yeah, the last thing. Secondary. First, never mind.
Of velocity missed. Sorry, thank you. No, thank you very much. Thank you. Velocity missed. Missed. Okay. Those equations will not provide you a fermion. So the question is whether it's possible to deform this equation such they will do. And we know from quark gluon plasma, from heavy ion collisions, and from other examples, we know that it's possible. So the deformation of this equation apparently must be possible. But that goes against common wisdom that Euler equations cannot be deformed. And then let me explain that. What these first two terms is basically acceleration of a fluid parcel, and that's a force acting on the fluid, and P is the pressure. Basically, this is a Newton law written for continuum media, which are called fluids. Which is called fluid. That is a continuity equation which says that number of particles in the fluids conserved whether you put a spoon or not. There is a very developed kinematic of Euler equation, basically developed by development start from the work of Arnold in 1966. Maybe I have to write it here. Who explain what actually mean fluid mathematically. And hydrodynamics is motion of fluid. If you want to ask ourselves, what is the hydrodynamics? It's a good question for this workshop. And I'm sure that many people give different answer. Although there is one, and to my knowledge, only one definition. So fluid is a continuum, which belongs to fluid is a continuum media which moves under the action of the group of space-time diffeomorphisms. So M4 is a space-time. That means that if I take a parcel of a fluid, move it, which is located in position X, move it by infinitely small displacement, Aristotelian displacement epsilon, then the media which I obtain is the fluid again. So any flow can be understood as the action of diffeomorphism. This definition makes a lot. For example, fluid by flow cannot make empty space. Gas can. Crystal move for different things. So there are many continuum media, but fluid is very special, and that will be a good definition of fluid. So from Arnold point of view, those equations appears as classical mechanics, Hamiltonian mechanics on a manifold, which represented by the Lie group of diffeomorphisms. And from this geometric point of view, this equation is fixed. There is no way to change them unless you allow it to be to introduce high derivatives, dissipation, but I'm talking about Hamiltonian case. High derivatives requires extra scales, but if no scales, no extra derivatives are introduced, that's almost fixed. And any attempt to deformation will give you some differential equations, may be interested in some sense, but they most likely will not describe things because of this geometrical bit. Actually, the group is acting here is a little bit larger. It's a group of diffeomorphism, which is responsible for the first equation, first three equations, and also gauge group, which is responsible for continuity equation. This group has a dimension of the group. Of course, it's infinite dimensional, but now you can we may count number of parameters. Here it's 4 and 1 extra, it's 5. Where are they here? We have density, it's 1 parameter. We have 3 velocity, another 3 parameters, 4. But also this, where is the 5th parameter? But also actually this pressure is not only function of density, but function of some additional scalar, which sometimes called, in books it's called entropy, although it has nothing to do with the thermodynamics, some scalar, which advected by the flow. And that is the 5th parameter. So 4 here and 1 here, 5. And that is called Laplace adiabatic principle. It has to be added to the equation. When pressure depends on 2 variables, such flow is called barotropic, baroclinic. And that's a flow which I'm going to consider. Now, why is this equation not difficult to deform? Because they are sort of word identity of that group. They must transform under that group. And this is very rigid constraint. If you don't introduce extra degrees of freedom or extra scales or gradients, they are almost, we can't move them. Almost cannot move them. In that sense, they will miss important features of fermions, fluid made out of fermions have. And this feature is anomaly. Or in this case, it will be chiral anomaly. So chiral anomaly has many, many different definitions. And I will present only one. It's the following. Gauge group, let me parameterize gauge group. Let me assume that, let me consider momentum of the fluid, and under gauge transformation, momentum becomes canonical momentum, and psi is the gauge phase. This is how gauge transformation acts. It change momentum. So one good definition of chiral anomaly is the following: equation must be gauge invariant. Equation of motions, gauge invariant. That is a kind of a postulate. And if you write something which is not gauge invariant, an engineer who going to do some plumbing, will laugh on you. So they're supposed to be gauge level. But the action from which this equation follow is Hamiltonian principle. Hamilton principle means that there is a functional which called action, such as that its extrema corresponds to solution of these equations. The action is not necessarily to be gauge invariant, and in the case of chiral anomaly, it is not gauge. So its change under gauge transformation somehow and if this change, if the gauge transformation change by 2 pi and come back to itself, it's always space. And if the action under that process change by h bar times any even integer, those fluids will possess fermions. So there is possible to create a protocol for a spoon which creates fermions. But for that, action must not be gauge invariant. This is called chiral anomaly. However, this gauge phase, although physical object which engineer can measure, does not appear in the equation. That's maybe the best. Sorry? What? No, just it. Just okay. So the question now is this possible? Yes. Is this possible? Yeah, in most cases, if you try to modify this equation somehow, most likely you produce differential equations. They may be very reasonable, but they will not follow from any action. So the best way to be sure that we describe fluid, not anything else, we must better operate with action. We consider an action, apply action of that group, produce some equation of motion, and we guarantee that they obey all necessary symmetries which fluid requires. I emphasize this difficulties of deformation because there is the whole block of literature where people try to deform these equations, attempting implement chiral gauge anomaly. Most of these attempts are not valid. Some, okay, it's difficult. So the best way is to start with the action. So, and this is what I'm going to do. So apparently the action which changes equation slightly, but does not introduce any additional scale, makes these equations diffeomorphism invariant, so it will be a fluid, and provide the property which I just raised, is adding to action of perfect fluid, so this is the perfect fluid, a term which is called Bezzomina-Novikov term, which Nair mentioned a little bit about it, but then I will build on this point. I'm going to explain what that means. In order to do this, I have to introduce two important concepts in hydrodynamics, and then I build on top of these concepts. So just make a pause and say a few things about hydrodynamics. So the first thing is what is momentum? what is fluid momentum? And that's an interesting question, because everything else, all this term and everything else will be built out of fluid momentum. I have to explain what fluid momentum is. Also, fluid momentum is necessary to rewrite this equation in so-called canonical form. So it's a sort of simple but important aspects, which I'm going to spend a few minutes on. Okay. So equation which I wrote is for non-relativistic fluid, Galilean fluid. Now, the first thing to do is to introduce current, mass current, or particle number current. That is simple. Let me use rho as mass times n. N is a dimensionless density of particle numbers. M is mass of fluid atom. So instead of rho, I would use n. And then the current would be 4-dimensional vector field, whose time component is just particle number, and space-like component is particle number times units. Then the action will depend on this current. And action for this particular equation is known, but well studied. But I don't need explicit form. I only want to say that this action depends only on this current. That's enough to describe fluid. And of course, this. Okay. If I vary this action, I will introduce momentum as a conjugate to that current. So for Galilean fluid, this P has 4 components. And P naught is the energy per particle. It could be written through V and N, and P, space-like component is just a standard momentum, maybe NV. For relativistic fluid, of course, this formula will change, but the definition of momentum remains. Using momentum, it's possible to rewrite this equation in attractive covariant form. I will write it down. One is a conservation of stress energy tensor. And the stress energy tensor, canonical stress energy tensor, is not necessarily symmetric. That's pressure. And that's equation of motion. And the continuity equation will be written through divergence-free condition for the current. These equations involved 4 components of the current. This is a vector field. 4 components of the momentum, which is co-vector field. There's 5 equations, 4 here and 1 more here. 5 equations. Say
J, current, you said the current with the old density, yeah.
Oh, J. Yeah, I'm sorry. So, okay. Sorry, I used for the with this rotation. It's okay. Thank you very much. Yeah, this is a 5 equations, and for 9 variables, and the equations will be completed when we write down equation of state. And the equation of state is relation of momentum in terms of the particle current. That equation, which is for Galilean fluid, is that for relativistic fluid is different. For whatever fluid is different equation of motion. This equation of motion converts vectors to covectors and therefore require metric. It could be Galilean metric, it could be Minkowski metric, whatever. But equations written in this form, 1, 2, 3, assume no reference of metrics. It's only differential geometry. It's built out of vectors and covectors. Important, which usually not emphasized in text. Okay. Once we pass through that, my next concept is helicity. I call it H mu. That's also a vector field, but a pseudo-vector field constructed out of momentum. Or to be written concisely in terms of 3 forms. This is a helicity, and the process where helicity, illustrated helicity, is my twisted vortex, which was on the first slide. The meaning of that object is the following. If I take, say, 0 component of helicity, space, time-like component of helicity, and integrate it over 3 space, I will get total helicity. And that apparently be a topological number. Namely, it's equal to linking number of vortex loops. So helicity 1 is a configuration, then one vortex linked to another vortex. In this way. Helicity 0 is when these two loops are unlinked. That's a classical interpretation of helicity. Based on Sager quantization, helicity is also quantized in units of Planck constant and represents an integer. This integer could be very big than the fluid is classical, but it's an integer. It could be 10 to the 8, but important that it's an integer. Okay. So,
well, it's an integer in terms of H bar, which is not defined here anywhere, right?
yeah, so yes, so quantum mechanics, it reduces scale, but it's only what I need from quantum mechanics. The rest is classical. Okay. Then my claim is that the only possible deformation known to me, and maybe I think it's only possible deformation of this equation, is the following. Equation of motion, dynamical equation of motion, namely Newton's law, remain unchanged. But continuity equation does change. Sorry, can be allowed to change. Where K is a parameter, also the strength of the deformation parameter, that's the deformation. And that equation, what does this equation mean? Equation means that number of particles is no longer conserved because helicity is no longer conserved, is not conserved. That means that I assume that the fluid is interacting with the reservoir, which I draw this way. So if fluid is on the edge of reservoir, then there's some collection of spectacular, spectacular media which allow to produce add particles in the fluid is only here, and remove particles here when necessary. And that operation controlled by helicity. Now, because helicity eventually is an integer number, this is also integer. So, how to obtain these equations are perfectly gauge invariant. No gauge transformation is necessary to solve them from engineering point of view, from point of view of differential equations. But two things I would like to say before I end, that these equations do produce Ferdinands. K is the spin of these Ferdinands. Of course, if you want one Ferdinand being in quantum mechanics, then K is not large, but generally it will be very large, so that was possible. And they coming from a particular action, which I'm going to write. And the fact that it coming from the action as a Hamiltonian principle warrants that these equations do describe fluid, not just nice differential equations, but do describe fluids. To notice that they are written without reference of any metric. They are true for relativistic fluid, non-relativistic fluid, for gravity, for metric is not involved, because all operations are in differential forms if we understand that equations are written in canonical form are covariant with respect to different metrics. Now, what is the action? So as I said, I have my phase space of the fluid is 5-dimensional. Although fluid is operates in space-time, which is a 4-dimensional, but phase space is 5-dimensional. If this is a manifold where fluid lives, space and time, the phase space is actually 5-dimensional. One density, 3 velocities, or 4 components of current, and plus this interesting scalar. Yes. Okay. Therefore, momentum, canonical momentum, which is a 4-component covector, in fact has 5 components because the number of arguments in parameterization of this momentum is actually 5, and it could be lifted to 5 dimensions. If I think about this reservoir is one extra dimension and the fluid a boundary of this reservoir, then this gauge transformation is sort of a coordinates which run through this reservoir, labeling the 4-dimensional section. Then, because the space-time is 5-dimensional, sorry, space is 5-dimensional, and space-time is 4-dimensional. It is geometry of the phase space allowed to construct an invariant, which is called Hopf-Novikov invariant. Written as an integral of the phase space, which is 5-dimensional, out of the 5 form made of canonical momentum. This is also integer number and actually volume of the phase space in unit of quantities. Now, it's invariant. If I vary p, pi, but change for example, gauge transformation, nothing happens to this invariant. It's a number. However, if I consider what is called Berzomina-Novikov multi-valued functional, where integral over M entire phase space will be reduced to the integral over the disk, five-dimensional disk, which has a boundary where, and the boundary is my physical fluid. Then that object already depends on variation of pi. If I change, it's a functional, it's not an invariant. But because that is a full derivative, after integration over five-dimensional space, it will be entirely sitting on the boundary. That's a property of it. So Hopf-Novik invariant is when I integrate over full five-dimensional space, which assumes no boundary. It's a phase space, but if I integrate over half of it with a boundary, I obtain a functional which entirely sitting here, and it's a fancy writing. It's like in five-dimensional space, but it's actually four-dimensional object which engineer can measure. However, if I want to write it in 4 dimensions and present it to engineer, I will lose space-time covariance. In this form, it's obvious that it's space-time covariance. It's written in terms of forms. But if I want to integrate it, take one derivative down and produce something which depends on the object which engineer measure, I have to introduce coordinates. And that coordinates is gauge phase times helicity. And I recall that helicity written entirely through kinetic moment.
By helicity now you mean a 4 vector, not just a usual.
Now it's a 4 vector.
Yeah.
And the integration goes with respect to 4-dimensional space. I can start from that. But from here, it's not clear whether it's diffeomorphism invariant. From this form, it's clear that it's explicitly diffeomorphism invariant. But for that, I need this trick with extra dimension, or thinking about fluid as an edge of some big bulk. Okay, now my story is I would like to take this multi-valued functional. For historical reason, it has many names. One of them is Novikov, although it's explicitly written by Novikov in 1980s. And Berzomina wrote similar thing, but in coordinates, but much earlier, not in covariant form. So I would like to take this action and this thing and add to the action of perfect fluid. So I take the action of perfect fluid. Call it S naught, which depends on n, which produce this equation. and add with a coefficient, some coefficient, arbitrary coefficient k, which happen to be integer, that term. Just literally this term. And I can write it in whatever form. If you write it in explicitly written in 4-dimensional objects, it has this form. If you don't mind to write it in 5-dimensional, but it's essentially depends only on the boundary, that it's a little bit nicer and covariant. And ask what equation of motion does this actually produce? And that will be this question. Notice that psi, this gauge factor, which appears in the action, completely disappears from the equation, but it's present in the action. And that phenomenon is called chiral evolution. One out of many definitions or incarnation of chiral evolution. Now, but in this form, I can do my spoon experiment. I take a spoon, put it in the bucket and move it such that psi goes around the circle and come back. Psi goes to psi plus 2. My action then change by integral of the helicity. It becomes total helicity. But that's integer number. So I see that my action will change on the motion of the spoon. So what does physically it means? And then I stop. Just a short one last comment, and then I stop. So physically it means the following. What does gauge invariant mean? If I declare that my action is gauge invariant and the equation are gauge invariant no matter what, then one of the interesting concept of this gauge invariant is that in fluids there are it's possible this equation allowed point-like vortices, namely it's really line which core is a point-like. Strangely or not, it's a consequence of gauge invariant. Now, if I allow to destroy gauge invariance by modifying the action by explicitly gauge non-invariant form, what really happens is that this vortex become a sort of a ribbon, which I can twist. And the ribbon can be characterized a normal vector which attached to it. It's called framing. It's kind of emergent phenomena which causing that modification or this modification. It's framing. And the angle of this vector, angle of the frame, is a gauge transformation. So what happens is that if I take a vortex, and now it's free, and I rotate it around itself, namely applying gauge transformation.
Uniformly rotate or in a spiral?
Locally,
like
locally, locally.
Locally rotate. So
Just
you
locally,
can
take and rotate it locally.
Okay.
According to this equation and perfect fluid, nothing happens. Because point-like vortex has no structure and the solution is low. If under that modification, this vortex is actually has a frame. It's like a ribbon. And the ribbon, when I twist the ribbon, I change something. I produce extra helicity. And under that process, the action also change by the total helicity. So if I take a spoon move it such that vortex sort of rotate around itself, my action changes by the number, the total spiraling which I create, the total angle which I twist my ribbon. This is phenomenon called framing, and it can be implemented by modifying the action dimension and modifying equation of motion this way. So it's all metric independent. It's true for Galilean fluid, it's true for relativistic fluid, because everything reads in terms of momentum and number of particle currents. And before I impose relation between that vector and this covector, it's equally applied for fluid in any metric. So it's entirely geometric phenomenon. And it seems that it's only possible modification.
Okay, so there are a couple of announcements. So Sergey fans have to wait till tomorrow for this talk. So we have moved the last talk to the same time tomorrow, in the interest of the public lecture that's going to happen at 6 p.m. And so the thing is that if you are staying for the public lecture, then we can go to dinner after that from here. I will be leading you to somewhere. But if you are not sticking around for some reason, then you can, this is my phone number. And if you want to join directly at the dinner, text me, I will send you the location where.
Very hard to see that name.
Huh?
Yeah. I think the Shyam's phone number was the email. That
Yeah, but nobody reads email. So,
this time.
So write your name and text me and I will send you the location where we are. And we will be in the Koreatown somewhere because there are, I don't have to make reservation. We can just, there's a food court like area. We can bring our own food and then there's a large seating space there. So that will be approximately, we will be starting from here around 7:15-ish, between 7:15 and 7:30. So if you want to take a break but I encourage all of you to join for the public lecture, which will be a lot of fun. Okay.
Can I have questions from Bigman?
Yeah, you are free, like till 6 p.m. you can continue the. Yeah, you can take questions. So now.
I just want to understand the counting of the traces dimensions. The counting of traces. The counting of traces dimension. Yeah. So you said there were 5 degrees of freedom. 4 are associated with the current, and now the one was the S and R and D.
It's something which in books it's called entropy. But it has nothing to do with entropy, it's just arbitrary objective scalar.
That entropy will also enter the action. And the conjugate to that is also direct.
Is moment. Conjugate to that?
Yeah.
If it is entropy, that will be temperature. But if it could be whatever, then it will be conjugate will be whatever.
Then the counting already answered.
No, but conjugate is counting because equation of state relate conjugate. So I don't count conjugate. So independent variables are 5. But each of them has conjugate, so it's 10. But they are related by equation of state.
No, I mean, the way you argue for the extra density. With 5 as
Yes.
P plus psi,
Yes.
then new psi, that is why you.
Yes, it's this understanding of geometry of the phase space is quite important and very obscure in textbooks. But you so there are 5 variables. This additional scalar entropy.
It's always that one.
Then the gauge freedom could be counted as a 5th degree of freedom. So you could say 4 moments. There was 4 moments. And then it's scalar S. But instead, you can choose gauge freedom psi as a function of this of all five variables and declare this is a degree.
Okay, so S.
Transform to psi. Right, so we have 4 degrees of freedom here with helicity, and then this fixed degree of freedom. Because the phase space is actually 5 dimensional, and that's the crucial. For example, if you remove this entropy, it's called homeotropic fluid or barotropic fluid, nothing like that. We are in 4 dimensional, but there is actually some bulk in fifth dimension, such as a fluid is a bulk. Bulk may interact to fluid, may not. In standard perfect fluid, it does not. In this modification, it does.
Okay, then. And this is the only form that we can use, like phi could not be, phi is equal to P plus W sine. That comes from B.
It's continuation. So the 5 degrees of freedom actually tells you that gauge freedom is physical. But in perfect fluid, it's sort of decoupled accidentally. And my deformation couples them up by this parameter here. So it's very important to understand that fluid is actually phase space is 5 dimensional, but it's operating 4 dimensional. So where is this 5th dimension? How to explore it? The deformation entirely relies on that fact. So you can think about the 5th dimension, call it entropy, but better call it gauge freedom. It's a trade-off.
Also want to understand this modification, it's a relation of density to helicity. Does it tell you that I need to change locally density so that I identify this vortex as something having different densities? They are being twisted. What's the physics of it?
Yeah, the physics is going. So this is my vortex.
Yeah, but
No,
why
just
is it
let
related
me
to
explain.
density?
Let me explain.
Yeah,
Let me explain. Suppose I twist it like that. Just rotate
okay,
by 2 pi.
okay. Yeah, and yeah.
That's actually a good thing to do.
I understand.
So make a rotation, it's 1 extra twist.
Yes.
It's a vortex.
Yes.
Okay. So a particle comes from this reservoir, from this dimension, and sit exactly on that twist, such as the total number is considered. Number of twists, number of particles. Number of particles not considered. Number of twists and particles. Okay. So if I take my ribbon, which is vortex, twist it. Here, nothing happens. Twist because the vortex has no structure.
Okay, I see. So this is really a change of equations.
It's a serious change of equation. So I twist it, and then the system say, in order to minimize energy, I need a particle from somewhere else. If I twist it opposite, it will expel the particle.
Yeah, try to interpret it in terms of figure.
So it's this really this picture, which is coronal mass expansion, which I drew on the slide. It's exactly that. This is the sun. Sun is a reservoir. So you twist a vortex, right? And the sun expels some more mass to compensate this as a twist. Right? So classical fluid misses this parameter. Perfect fluid missing this parameter.
So what is K?
Number of flavors. Number of flavors. K is the number of fermionic flavors.
I mean, I was gonna ask, how does the engineer compute this?
Engineer. I ask a question. Engineer can create works. That's the question. Is this work with a low structure or is it actually a river? Engineer doesn't know, a good engineer, but he doesn't know before he makes.
But what is the measurement, the text? In other words, how do you write thread side from measured flow?
Yeah, I think that should be able to.
How do you compute you're going to?
Yeah,
or to.
Equation says
Yeah,
that if, this. Suppose water line has a.
Yes.
Stuck on the rest of the fluid, but fluid less towards the. And there's this equation.
That's my thought.
So this is number of twists locally, that's number of particles locally. So if you twist, there's a flux of mass toward the twist. And the engineer is supposed to tell me, is this happened or not? If it's not happened, K0, we are in Euler equation. If it's happened, we are in this case. It's very practical, I guess. I mean, practical, there's no usual.
Except the operation of twisting is not good.
Oh, I told you can pump particles along the wall.
I mean, we do this all the time. I think it's well along the vortex.
But then if somehow the tip that what you do it around it spiraling more faster along the wall. You could probably use grading. I think that you could probably get psi of the grading of what's in the. I think it's because you have grading to what is also going to produce a similar rates. Yeah, it's not yes, and you might be able to detect the reason. They will change. If you the new particle find right those streets. It's a bit more complicated. What to say? Another question.
So I was wondering, you can actually modify the exception project, which just your definition to it not to charge. So I can find it hard to believe it. You have to produce particles by but if you produce that in the country, it's not good. Oh, right. That's what me. But not real power. It doesn't even you can people whatever you this thing.
Towards where I here's 4. In equations, everything is 4. It's action fixed.
Yeah, because in the sense that there is the.
The equation is
continuity equation, which means that your number of atoms changes the charge. And I don't mean the result part.
yeah, but it will be very important. But when the spoon is that part, so we take from here
But to me, that means it's actually.
or you can connect it, or you connect it, or you.
I mean, would it be more natural if you entered with some kind of entanglement and then you twisted your spinning actually.
But the best way of saying it is not a bucket with even number of particles, but it's given chemical potential. Then it can suck or whatever.
But purely formally, like entropy, you say it's not real entropy, but in fact, also for higher temperature, it is real temperature. The other thermal degree that gives you what the factor is, not just the factor. So if you go
Do you think
zero
that this,
temperature, it could be entangled.
yeah, you think that this makes a degree of freedom, how, no matter how we name it, you need to interpret.
That's what I want to suggest. Maybe there's another scalar variable that you studied before, not the.
Because I thought the understand what the text variable is how consistent fluid mechanics is fraction of number of particles, well, the number of atoms in the fluid, and number of particles in the reservoir. That's the normal way of thinking about it.
The way I used to, like more practically, is, yeah, pressure is a function of density and temperature or entropy. So it's really that internal energy is just you remove all your discrete degrees of freedom from the Euler equation, but you still have internal energy that can be. So in that sense,
But
you
the
could-
idea is to interpret it as a rectangle.
If you're at absolutely zero temperature, then yes, it could be some kind of entanglement. One thing.
Or are you not, are you looking at this one that you're not
It's not that we're coefficients.
parity rating compared to.
Coefficients.
Right, and that's where it was.
There's number of particles sometimes. But all this quantization comes from Cyber quantization.
Sorry,
Because so instead of quantization, what does it say? It says that the vehicle is directionally compact. But then all arguments are true. Because the whole space.